minus 80. Okay, so these parameters. And so it bounces off the bottom because the brackets. So are we going to assume that it's a parameter per second? Will that make sense? No, it doesn't. It will not make sense. Because what I can do is if now the velocity of this mass is zero. I don't know the velocity of this point because that is after the bounds, which is not going to make sense. It's not going to make sense. But I can get the distance. Since I know from there this maximum height up to below is 4 meters, I can subtract this 3.2. So at the distance I have will be my displacement. Yeah, makes sense. So let's see. So which means my delta one. Let me just put this. Okay, so saying my delta y is gonna be 4 minus the 3.2, which is 0.8 meters. Okay, so that's our displacement. Our initial velocity, since it was now maximum, is going to be 0. Because now I'm looking at the second journey. Okay, from maximum, now dropping down. Okay, if that is true, I need time. I need time. So the displacement should make sense that second of the delta y is equal to VL2 plus a half P.2 squared. Yeah, it would 0.8. So that's going to die out to be just a 0. This is a half times 9.8 and 2 squared. Taking the 9.8 to be positive since now it's the second journey that is dropping down. Okay. So this is going to be 4.9 2 squared is equal to 0.8. Divide both sides by 4.9 and then find the square root of the answer. What making sense, which is my answer, which is 0.4, yeah. What other information do we need about time? So let's see the question. Let's see the question. Because that 0.4 is just for this road, which is for the coverage. The question asks the total time taken from the top. Oops. But then we have to do it back in the class using the change in y. So then what's going to be the displacement? Well, 1.3 up to that. And so it got was 2.7. So it means we can use the 2.7. 4 minus 1.3 plus 2.7. That's very correct. It's 2.7, and then the time as well. So 2.7 is equal to now initial, which was 1.1, there's 1.32. Now I'm subtracting a half times 9.8 to square. Okay, so when I use my quadratic formula, 1.3 minus, I'm just going to say 4.9. That makes sense. Maybe there's something really wrong. See, let's see. So this was a 0.4, this P2. And we need the time from the point of projection to the maximum. Well, now it's the P2 again. And it's that P5 equal to the initial plus A2. Yeah. So this one is a 0. The initial is 1.3. Now minus 9.6, 1.82. So which means our T is going to be 1.3 over the 9.8. 1.3 divided by 9.8, which is 0.132. Okay. So then I can calculate 0.4 plus the 0.3. So that's going to be 0.5. Why are we using 1.3 again? It's 7.27. 7.27. Seven point two seven. So 7.27 divided by 9.3 is 0.74. Okay. So it has to be 0.74 plus the 0.4. 0.74. That gives me 0.1.7. 0.74 plus 0.4. That's 1.14. 1.14 seconds. Yeah. Then 0.3, they want us to stretch the graph of displacement. Before the interaction. We're using the ground as a reference point in the line. Now, remember with the different graphs is the displacement. So how is the displacement? Smaller position. Okay. So when code is the displacement in meters, this is the time in seconds. Okay, so what we shall notice is that this ball is going to start at a height of 1.3 meters. Then it will go up, reach a maximum at a height of 4 meters. That's what we said. Then it will come down after a certain time. It will bounce over that time that we just calculated the 1.14. then to bounce upward to another height, which is below the maximum height. So something of the nature with what perfectly interesting people. So something like that. After that, and that. So this we don't need to know it. But before we need to, for the sake, we need the max, the height from which the ball was released, the 1.3. That is indicated. The maximum height, which is a 4. The height of the balcony, that's the height of the balcony, it's 3.2. Which is that, and then the time it takes to bounce down. So something that can reach out would guarantee you the 5 minutes. Then question number 4, when a ball hits and bounces off the surface, it exerts a force on the surface. So some group of learners investigated how this force varies over time as the ball hits the force sensor and bounces up. We used the 50 grams of force from height of 5 meters above the sensor. Okay. And then the following part is derived. And then the first question comes, what has it else to define impulse? Okay, so when we are defining impulse, the definition is that it's the product of the net force that is acting on an object and then the time. The net force acting on an object and its time. Okay, so we say product of the net force acting on an object and the time that it takes. Okay. Now avoid using the change in momentum kind of terminology because that is more like an application. It's not a definition of impulse. Then they want us to use the information in the graph to determine the magnitude of the impulse as the ball hits and bounces off the sensor. Okay, now remember we said impulse is the product of force and the time. So we are indirectly being asked to determine the area of this triangle. So we know that area of a triangle is given as a half times the base times the height. So that's a half. Our base is 15. So from 0 up to 15. And then our height is going to be 64.13. Okay, so a half times 15 times 64.13 is giving me 480.98. 480.98. But remember, this time is in milliseconds. So which means I have to write that down and this means I have the 0.481 differences. Time as in milliseconds, so divide by 1,000 or multiply by 10 to the negative 3. Then 4.3, can we state the magnitude and direction of the change in momentum of the ball? So what we can see is when the change in momentum mass or change in momentum is the same as interest. We don't need to go back to the mass and the velocity. So this 0.48, since it's positive, we're going to take it to the upwards. Okay. But then, what is the question asking for? The magnitude and direction. So 0.481 newtons upwards. It's upwards, positive. All right, then if the velocity of the ball just before it hits the first sensor is this, downwards. Can you calculate the velocity with which it bounces off the sensor? So then you can use the F net formula. F net times delta T, that's the impulse now, is equal to the change in momentum. What is the question asking for? Calculate the velocity with which it will bounce off. So it is M, V final minus V initial is equal to F net and delta T. So we know that the F net times delta T will give us that 0.48 hours, which is the impulse. Okay, so we shall say 0.481 is equal to the mass, is very close to 5 grams. 25 or 50? It's 50. It's 50 grams. So convert the grams to kilograms. That's going to be 0.05 kilograms divided by 1,000. I'll open this. The final minus the initial, which is 5.14. I'll start by dividing both sides by 0.05. So 0.481 divided by 0.05, I'm getting 9.62 is equal to V final minus 5.14. Then I'll move this 5 to that side, which will be 8. My sense correct, because the final is moving upwards, and then the initial is moving downwards. So it's a minus, that's a plus, so which means I'm going to subtract. So 9.62 minus 5.14. That's giving me 4.2 meters per second. Okay, so that's our final. So the final is going to act upwards. Then 4.5, we've been told that the ball is now replaced with a hard ball. Remember, the previous one was a soft ball. Hard ball of the same size and mass. Will the force on the sensor increase, decrease, or remain the same? Now, with a soft ball, we know that it will tend to take more time in contact with the sensor, whereas with a hard ball to take less time. So in this case, it's going to increase. Why? Because the change in momentum, let's say the hard ball takes more time. Takes more time. It's the soft ball that takes more time. You say the hard ball takes less time to bounce back compared to the soft ball. Okay. So this can be seen under the applications of the airbags of the cars, let's say in car crashes and things like that. So what this means that the force will be inversely proportional. Okay. To the time, and hence the force will increase if the time is less. That is question number 5. Question number 5, the 5 kg body or box moves up and down at a constant velocity in the force F is applied. Okay. We want us to calculate the magnitude of the force F if the power that is used to move up the box is this. So we know that the average power will be the same as the force applied times the velocity. Okay. So we have our power, we have our velocity. So we're going to have the 57.6 is equal to the velocity, which is 1.2 F. Then divide both sides by 1.2. So 57.6 over 1.2. 57.6 over 1.2. and getting 48 newtons. Okay, so this is the magnitude of the force that's pulling this object. Then they want us to state the work energy theorem. So this tells us that the net work done, okay, the net work done is equal. The net work done, let's say by net force, by the net force is equal to the change in energy, which is equal. Okay, so if that is true, then they were telling us that the box now slides down this. So still, since the velocity is constant, which means even the force is kind of constant. So if the coefficient of the kinetic friction between that is this 0.25, calculate the velocity at point C using the energy principle on it. So it all depends on how you want to approach this question. Remember, at point B, this object or this box will have mechanical energy. Okay. We have mechanical energy, which is a combination of the kinetic as well as the gravitational potential. And then at point C, we're just going to have the EK to be maximum, since there is no height. So the gravitational potential will be a 0. That's my argument. And remember, energy in any sort of system will always be conserved. Energy will always be conserved. So what do you think? What do we think? Okay, so saying the work net, W net is equal to the change in kinetic energy, which I will just say EK plus the EP. The change in EK and then the change in EP. So we know that our work done is given as F times the displacement. So we have our power, we have our velocity. So we're going to have the 57.6 is equal to the velocity, which is 1.2 F. Then divide both sides by 1.2. So 57.6 over 1.2. 57.6 over 1.2. And getting 48 newtons. Okay, so this is the magnitude of the force that's pulling this object. Then they want us to state the work energy theorem. So this tells us that the net work done, okay, the net work done is equal. The net work done, let's say by net force, by the net force is equal to the change in energy, which is equal. Okay, so if that is true, then they were telling us that the box now slides down this. So still, since the velocity is constant, which means even the force is kind of constant. So if the coefficient of the kinetic friction between that is this 0.25, calculate the velocity at point C using the energy principle on it. So it all depends on how you want to approach this question. Remember, at point B, this object or this box will have mechanical energy. Okay. We have mechanical energy, which is a combination of the kinetic as well as the gravitational potential. And then at point C, we're just going to have the EK to be maximum, since there is no height. So the gravitational potential will be a 0. That's my argument. And remember, energy in any sort of system will always be conserved. Energy will always be conserved. So what do you think? What do we think? Okay, so saying the work net, W net is equal to the change in kinetic energy, which I will just say EK plus the EP. The change in EK and then the change in EP. So we know that our work done is given as F times the displacement. If displacement can be, let's say, delta X, and then the cos of theta, because that will be now the work done by the friction force. This is equal to the change in H is going to be a half m v final squared minus a half m v initial squared. And then the EP is going to be mgh final. Okay. And then the mgh initial. Something like that. Now we know that the force was 48. But remember, this F is for the frictional force, the work done by the frictional force. Because if you look at the free body diagram of this thing, I don't want to use those things of the free body and the forces and so on, but we can also use that and get the velocity. Okay, so let me stick to this. So we know that the frictional force is mu mg cos of theta. Okay, so our mu was a 0.25. Okay, times now the mass of the body, which is 5 times 9.8 times the cos of 32. Okay, that is just the F. Now the displacement, I do not know it. Okay, I don't know the displacement, but I can get it. How? Since I know this is my H, and then this is my 32, I can use the sign. We know that the sine of 32 is equal to the opposite, which is 1.6 over the hypotenuse, which is BC. So which means BC is going to be 1.6 divided by the sine of 32. What does it give me? It gives me 3, something. Let me just do that right. So my displacement, okay, we get to 1.6 over sine of 32. And then we multiply by the cos of theta, which cos of theta is like cos of 180 since friction is in the negative direction. So when I simplify this, remember this is just the left-hand side. So 0.25, okay, times 5 times 9.8, the cos of 32, okay, times the 16 over the sine of 32, and then the cos of that. I'm getting a 313,665. Okay, but that is negative. Then when I look at the right-hand side, let me look at the B case. It's going to be a half. The mass is 5 into my V final, which I don't know, minus my V initial. What was the V initial? It was 1.2. And then when I look at my EPs, the mass is 5 The gravity is 9.8. The height is 0. Okay. Then I'm subtracting the 5 times 9.8 and then the 1.6. So 5, 9.8, and then the 1.6. So when I simplify this, I'm having 5 over 2 VF squared. This is out. And I open this, what is 1.2 squared times 5 over 2. That's gives me 3.6. So minus 3.6. Then minus 5 times 9.8 times 1.6. That is 78. Okay, so this is what I'm having by my right hand side. This is what I'm having by my left hand side. So now it's time for me to compare the two sides. So 5 over 2 VF squared minus, okay, this is 3.6, I'm getting 82. So minus 82 is equal to the 3.665. Okay, so 313.665. So 82 multiplying by 2 dividing by 5 and getting that. And then I'm getting 9.6. Doesn't make sense for me. Did I do something wrong? We have a visit this and it's, let's see if I did something wrong, something wrong, something. That's not worse. It is a 1 minute. We said 5 times 9.8 times 1.6. That is 72. Okay. The 0 is out. 1.2 squared times 5. We get to 3.6, which is 5. And then we have a half of that. So which means divide that side. Okay. So from to follow through, let me just go back to my previous patterns, which is 0.25 times that. Which is that. So my correspondences are still fine. It's 5 over 2 VF squared minus the 80. They divide both sides. No, not the 82 first. The 82. Dividing by 2 and dividing by 4. No, it's okay. I'm just going to ignore the sign here. Make it positive. What this is going to be. So it's 313,665 minus 82. Getting the 231,668 is equal to 5 over 2 v squared. And I'm dividing this by 5 over 2. Okay, I'm getting 92. And I find the square root, I'm getting 9.6. Okay, 9.63 meters per second. All right, then question number 6. They're telling us that in the diagram ABC below, the wave patterns are shown for the sound. So this is A, this is B, and then this is C. Can we define the Doppler effect? So we know that the Doppler effect is just the apparent, okay, the apparent change in the frequency that is received by the listener as a result of the change in the velocities and so on. Okay, but alternatively, we could just put it as the apparent change in the frequency or pitch of sound as detected by the listener because of the sound and the listener having different velocities. Okay, so that is that. Then 6.2.1 for questions this, we must state A, B, C for each. Okay, so where is the source stationary? Okay, I think it's option A because there's no change. We're not seeing this decrease or the increase and so on. So A, source is stationary. So when is the source moving away from the observer? So when you're moving away from the observer, what happens? The wave increases. So I'll go for C. And then you must give a reason for 6.3.2. So the frequency, okay, saying the frequency decreases. Or you can tell us that the wavelength increases, because this point will be the source. So this distance is increasing. So the wavelength increases, the frequency is decreasing. Then 6.3, they're telling us that if an ambulance that is moving right from the observer at this speed, and the frequency of the siren that is heard is at this frequency. I feel the frequency of the observer with the speed of air is that an ambulance is moving away. So one thing we know about the Doppler formula is that the frequency of the listener is equal to V plus minus V of the listener over V plus minus velocity of the source times the frequency of the source. Now, since the ambulance is moving away and the listener is stationary, okay, moving away from one side at the speed. So that's 340 over 340 minus. It's going to be minus or a plus? Because an ambulance is moving away from one side at this speed. Also, this has to be a plus, so that we have a smaller object. Then multiply by the frequency of this source, which is 900. Okay, so 340 over 340 plus 25 times the 900, we get to 838.36. 838.36 hertz. Okay, then the hydrogen spectrum line from the sun has a wavelength of this. The spectrum line of the nearby star has a wavelength of 657. What can we consider about the relation of the star in relation to the sun? Okay, so we can see that the wavelength of the spectrum lines of the hydrogen atom from the star is long. Okay, the wavelength is longer because this is 656, this is 657. So the star has a longer wavelength than the radiation pattern of the sun. So which means this is going to be a red shift, and this simply means the star is moving away from the sun. Okay, question number 7. Question number 7. An investigation was carried out to show how electric field varies at this distance in positivity charge, positively charged field. To achieve this, positive charge Q was varied and so on. So the following table. So you have the charge in nanocoulomb and then the electric field. Okay, then define the term electric field at a point. So this is the force. Okay, the force that is experienced at a unit positive charge at that point. So when you check out the videos of the perspectives, you get that definition or the definitions. Then they want us to draw the electric pattern for positively charged. So when it is positively charged, we expect the field lines to be moving out. Okay. Remember, these field lines should never cross. So that is that. And then 7.3, they want us to plot a graph of P versus Q. With the graph we have the values. P versus Q. So I'll just try to put that sketch. There's a graph page. Let's say 1, 2, 3. I'm just gonna use 2, 4, 6, 8, 10, and so on. Then here I can use transit. It makes sense. 10, 20, 30, 40, 50, and so on. So we know that 1 is with a 4, which is somewhere there. And then 4 is going with 16, which is slightly below. And then 8, this is 8. It's gonna go with 42. It's slightly above. 14 or 11 is slightly above 40 there. And so on. So just plot the points, but you're gonna notice that these points are not forming like a normal straight line. So which means you need to draw a line of best fit, a line where all the points are close to that line. Okay, all the points may not pass through the line, but all the points must be close to the line. So that is the graph that will be needed for you to get performance. And then you need to use the graph only to answer the question. Identify the controlled variable. So in this case, the controlled variable, if you have to look at the graph, remember, it is the E versus the Q. Okay, E versus the Q. Now it's the other way. This is the Q, that's the E, okay, E versus the Q. So the only thing that is controlled here, because they said the distance is varied and the distance away from the positive charge, fixed distance. So that is the controlled variable. So the distance. Okay, and then the dependent is the E, the electric field. Remember, in any graph, whatever appears on the y-axis becomes the dependent. The x-axis, the horizontal, is always independent. And then determine the fixed distance between the charges. So in this case, we can find the gradient, which gradient will be the E over the Q. Remember, from our E, K, Q over R squared. So which means this gradient must be equal to K over R squared. That's what I'm seeing from this formula. If I can get B over Q, which is the gradient, then I have. So we need to find the gradient. So with the gradient, we can find, I don't know, we can use the gradient, so we can even just gradient with this graph of mine that's not accurate. It's going to be a bit weird. But no, it's fine. We can get any points. Let's say I'm using the first point and then the last point. Okay. First point and then the last point. Okay, so I'll try to use my first and last values, okay, to get the gradient. So that's going to be 55 minus 4 over 14 minus 1. This must be equal to K, which is 9 times 10 to the 9 over R squared. Okay, so 55, okay, which is going to be a 51 over 15. When I do my cross multiplication, that's going to be 51 R squared is equal to 9 times 10 to the 9 times 13. So R is going to be the square root of 9 times 10 to the 9 times 13 over 51. Let's see, 9 times 10 to the 9 times 13 over 51. And 13 higher becomes 1. Did you do the correct things? Because it's going to point us. It's going to point us. I'm getting 4, 7, 8, 9, 6, 4, 9, 4, 8. Let's go back to the graph and see. Because this was the nanocoulombs. Okay. And then this is a K, which is like a Q. Okay, we can now see. So nano and kilo. So the Q is times 10 to the negative 9. And then this is times 10 to the third 2. So when I simplify that, okay, I should change a whole lot of things to some that. It's gonna give me now the 51 times 10 cubed. But why am I doing that? Just say 10 cubed. And then this is times 10 to the negative 9. Let me just include it there. Times 10 to the negative 9. And then times 10. Yeah, perfect. So I'm getting 0.04789. I'll just make it 9 meters. Perfect. So guys, that's the answer. Then question 8, a battery in the circuit below has an EMF of 6 and internal resistance of that. With S1 and S2 open, can we give the reading on V2? Where is V2? This is V2. So V2 is connecting the EMF, which has to be 6 volts. Okay, it's connecting to the battery. Then with S1 closed, if this is closed, it means the current is now taking this route, passing through R and then this. Okay, telling us that the reading that was recorded is 0.75 for the ammeter. Explain the meaning of this. Okay, so when a charge of 0.751, I don't know, are they asking us to explain what current is? Okay. So you can set the charge of 0.75 coulomb traveling in 1 second. Because that's what current is. Then with S1 closed, we want us to calculate the internal resistance. Okay. So we can use the EMF formula. Okay, which EMF is I into R plus small r. We now know the current is 0.75. Our EMF was a 6, 0.75. Do we know the external resistance? No, that's what they want us to reach. The internal resistance, they give us a 0.4. Divide both sides by 0.75. 6 divided by 0.75, I'm getting 8. And then 8, I subtract 0.4, I'm getting 7.6. Okay, same divide. 8 minus 0.4 will get that. So 7.6 ohms. Then they want us to get the value of R. Now remember, with capital R, still S1 is closed on. With this capital R, it's more like a parallel combination. So what I'm going to do, I'm going to combine. Let me just write it in. So I'm combining this and that. So let me combine the 3 and the 1 to give me 4, so that I have R and then a 4 ohm. Okay. These combined together must give us the 7.6 ohms. Since it's parallel, I can use the product and sum. So product over the sum is giving me the 7.6 ohms. My product is going to be 4R over 4 plus R must give us 7.6 ohms. If I try to cross multiply 7.6 times 4, I'm getting 30.4 plus 7.6 R must give us 4R. It's the product over the sum. Why am I getting something different? Is it going to make sense? 7.6 minus 4 is 3.6. 30 divided by the answer, you get to 8 point something, which doesn't make sense. Let me see. Oh, sorry guys, sorry. We also have another 4 ohm. There's another 4 ohm there. We are such honestly. Was not making sense. So let's see. So we have we said product over the 4 plus R. Now plus this 4 ohms must give us the 7.6. Move the 4 that side. 4R over 4 plus R must give us the 3.6. Cross multiply 3.6 times 4, I'm getting 14.4 plus 3.65. When I move the 3.6 that side, I'm going to end up with 0.4 R is equal to 14.4. Divide by 0.4, divide by 0.4. So my R is going to be 36 ohms. So this R is 36. So what I did, I first combined these two since they're in series directly and got the 4 ohms. And then since these are two resistors in parallel, we say product over the sum, we give you the effective resistance of just the parallel combination. Okay. Alternatively, what someone can do, if you can have the 7.6, okay, we subtract this 4. then I'll be left with 3.6. So which means this pair of combination is equivalent to just 3.6. Oh, makes sense. Then 8.4 S1 is now open and S2 is closed. How will the power dissipated by the 4 ohm change? Okay. So if this is open and this is closed, which means the power will just take this switch. Remember, this whole thing is a 3.6 ohms combined. This is a 4 ohm. Now, if this is off, which means we only have 4 ohms within the circuit. So the total resistance will be 4 ohm, and then that internal resistance, which is always a must. So one thing we have to do, we have to say that the resistance is going to increase. That is for the fact. Okay, it will increase because the external resistance has decreased. Okay, so the power, we're saying the power increases because the external resistance has decreased. Then you can tell us, so you can use the formula of power being directly proportional to I squared R. Okay. Then 8. They're telling us that the 12 learners conducted an investigation to determine the internal resistance of the battery, the circuit below is that. Okay. And then a graph was plotted. From the graph, can we deduce the EMF? So EMF is basically where the graph normally starts. For as long as this potential difference against the current. So this graph is starting from 4.5. So the y-intercept, that is the EMF. Then calculate the internal resistance. So internal resistance will always be the gradient of this graph. The gradient, because if this is potential difference in the current from EMF is equal to 5R. If we get the EMF over the current, we end up with internal resistance. So the gradient, so we consider the change from there up to there is going to be 4.5 negative. Because I'm getting the negative of positive. So whichever you look at it, you can have 4.5 to 0 minus 4.5, which is negative 4.5. Then I'm dividing it by from 0 to 7.5, which is positive. So I'm going to get a negative answer. Why? Because when you consider this line is having a negative gradient. So it's negative 4.5 divided by 7.5, that's giving me negative 0.6. So which means our internal resistance is 0.600. Question number 9. Study diagram below and answer the questions that follow. So what type of generator is shown in the diagram? We must motivate to answer by referring to the specific names of the components. Okay, so this has to be, we have this and this, and then we are calling it a generator. So it's an AC generator. Okay, number one, it has two slip-rings. That's number one. And then number two, it has a handle, which handle will be turned for you. Okay. So if it was connected to, let's say, power supply or something, then it would definitely reduce it. Then indicate the direction in which the current will flow in section A. So since we've seen the field to be moving in this direction, we want us to get the current. So using the correct right-hand rule or the correct hand rule, we can see that it's moving that direction. So it's going to be beautiful. going to be bit A. And the 9.3, the following graph was obtained from the generator. How many rotations are we having? So it's seen that from here up to here. Does that make sense? No, from here up to here. That's one rotation. Okay, the trough, and then next one rotation, and then this is a half. So we can say that it is 1.5 rotations, or 1.5 times. And then they want us to define root mean square, RMS. Okay, so root mean square current is saying that is the alternating current, which produces the same amount of energy as the equivalent of the DC. This is saying is the AC current that produces AC current, which dissipates, or we can produces same amount of energy. And amount of energy as the DC. Then calculate the average power. So with average power, remember we need to know the maximum power. Okay, so if we have I RMS, we shall get our I max divided by the square root of 2. And we know that power can be given as I squared I. Okay, we have the resistance, or we need the current. In the question, they told us what is going on. And we can see from the graph that the current is 15. So what we're going to say, we're going to convert this maximum current, which is 15, over the square root of 2. I'm going to square this, and then I'm going to multiply it by the equation. So it's saying 15 over square root of 2 squared times the 30. That's giving me 3375 watts directly. So if you have decimals, because of being this separate and rounding it up, no problem, but the answer should be close to the same. The 9.4 is a hair dryer, not a chair dryer. A hair dryer that is rated at 2.2 watts. Okay. At 240 volts. Then assume that the hair dryer is secure resistor, that is the maximum current that flows through the hair. So what we can see then is that we have the power. Okay, so we know that we just choose a different color. Okay, the P average is I times P. Now, what is our power? It's 2.2. What is our current? What is our current? Our current, we don't know, but we have the voltage, which is 240. So I'm just going to say 240 I. Then when I divide 2.2 by 240, I'm getting 9.16. 9.1667 amps. Question wants the maximum current. So for us to get the maximum current, you must get the IRMS times the square root of 2, which means my answer of 9.167 times the square root of 2, I'm getting 12.196 amps. That is 9.10. Then question 10. Diagram below shows a photo tube that was used to demonstrate the photoelectric effect. Demonstration was carried out by shining a light from a red, green, ultraviolet into the surface. Okay, they gave us the demonstration number, the color of the light, and then the ammeter ring. Okay. Can we explain what is meant by photoelectric effect? So we know that this is just a process by which electrons, okay, so electrons are ejected. And so electrons are ejected from a metal surface. From a metal surface after a light of sufficient frequency, and a suitable frequency is incident on the surface. So in other words, you first shine the light on the surface, and then electrons will come off, but the light has to have sufficient energy. Then explain why there's no reading on the ammeter when the red light is shown on. So we know that for red light not to show, we know that the frequency is low. Okay, so the frequency of the red light is lower. The frequency of the red light is lower than the minimum, which minimum is normally known as the threshold, the minimum frequency needed. Then for the following statements, use increase, decrease, and so on. So the kinetic energy of the photoelectrons dash when an ultraviolet is shown on the surface. So in this case, we're just going to say increase. Okay, in ultraviolet, and the reading is a yes, so it increases. Then the reading on the ammeter dash when the green light. So green light is also a yes of higher intensity. Explain the observation. So since the ammeter reading is a yes, which means this increases also. Ammeter reading increases when the green light is of higher intensity is shown. We need to explain that. Okay. So what we need to know is that with intensity increases the number of electrons, or the number of photons, not electrons. So the number of photons will increase by unit time. Okay, so if the number of electrons are increased by unit time, which means the rate at which they will be striking the metal surface is going to increase. Hence, the number of electrons that are leaving the surface will also increase. Then 10.4, they're telling us that the cathode is made up of copper with a work function of this. Okay, so which means W naught is 3.52 times 10 to the negative 19 joules. If ultraviolet with a wavelength of 390 times 10 to the negative 9 meters was used during demonstration, calculate the speed. They want us to take the beat. Now we know that E, the energy, must be equal to W naught plus the E3 max. Okay. So this E can be given as H lambda over C is equal to our W naught. Plus we can still take the E3 max, and then we can do the substitution. So the value of H is always 6.63 times 10 to the negative 35 in this table. Times the wavelength, which is 390 for the seed 390 M. Why am I saying wavelength? I think I've messed up this formula. Messed up that thing. Let me just it's HC over lambda. Sorry guys, I thought it's HC over lambda. Let's see over lambda. So 3 times 10 to the positive 8 over now the 390 times 10 to the negative 9, since it was number. This must be equal to the work function that they gave us. Its work function was 3,52 times 10 to the negative 19 plus my EK max, which I don't know right now, but I'll sort it out. Let me first figure out what is this and that. So I'm going to move this to the side. Okay, so I have 6,63 times 10 to the negative 34, that's 7. Okay, I'm multiplying by 3 times 10 to the 8, that's the speed of light, over 390 times 10 to the negative 9. Okay, I'm subtracting 3,5 times 10 times 7 to the negative 19. So I'm getting 16 times 10 to the negative 10. Now I know that E mass is a half times the mass of the electron, which is 9,11 times 10. 9,11 times 10 to the what? What is electron mass? Negative 31. Okay, so negative 31 v squared. Now I'm going to divide both sides by that. So divide by 0.5 times 9.11 times 10 to the negative 31. Well, getting a big answer. It's really big. It's really big. Okay, but I need to find the square root of the answer. Square root of the answer, which is the velocity, is giving me still a big answer. Okay, so if I find, I'm getting 5, 9, 2, 6, 7, 3, 9, 7, 1, 2, 3, 4, 5. So it's 5.9 times 10 to the 5. That's what I'm getting without the rounding offs and stuff. This is what I'm getting. Okay, so paper was out of 153 hours, okay, just as we discussed in the prediction. Okay, so let's look at the multiple choice. So they're telling us we have various options that have been provided. We just need to choose one. 1.1. Two forces, F1 and F2, are applied on a box that is lying on a frictionless surface as shown below. The magnitude of F1 is greater than the magnitude of F2. Okay, so what will happen to the box? The box will accelerate to the left? No. The box will accelerate towards the right. That is going to be correct. Will it move at a constant speed towards the right, move at a constant speed towards the left? So I'll go with the option of accelerating towards the right. Then 1.2, they're telling us that a 5 kilogram iron shot put and a 10 kilogram aluminium shot put with the same diameter both fall freely from a shelf that is 12 meters above the ground. So if we are to ignore the effects of friction, when the shot puts are 3 meters above the ground, The short boost will have the same momentum. No, we can't go for momentum because momentum will be dependent on the masses, and since the masses are different, we cannot have the same momentum. Will they have the same kinetic energy? Kinetic energy depends on mass also, because it's mv squared. Potential energy depends on the mass, so it cannot be the same. So in other words, only option that is reasonable is option B. Acceleration needs to be the same, regardless of the mass or the height. Okay, 1.3. Two asteroids S and T are having masses m and 2m respectively. They are on the course for a collision. Okay? So if the magnitude of the acceleration on S is a, then the magnitude of the acceleration on T is. Now, for as long as the collision is going to take place, the Newton's third law will have to apply. So the F net on this case is going to be MA. And then the F net in this case must be 2m multiplied by A. Let me just call that AS and AT. But it's just the same acceleration, so let me just keep it the same. Just A and A. So for me to get this acceleration of T, the force that will be acting will be equal, but just in the opposite direction. So MA is equal to 2m80. Then I make 80 the subject. So the m will cancel the m. And then 8 is going to be a over 2, which is a half of a. And option B is going to be my option to go with. And then 1.4. A sound source approaches a stationary observer at a constant velocity. Which of the following describes the observed wavelength and the frequency from the sound source as it approaches? So the observed frequency, number one, for as long as the source is approaching, it must be greater. Okay, so we're going with option A and option D. Now, from V is equal to F lambda, or C is equal to F lambda, we can see that frequency and wavelength are going to be inversely proportional. So if one is greater, then the other one has to be less. So option D would be the best for that. And then 1.5, they're telling us two objects, M1 and M2, with a distance r apart, experience a force F. The mass M1 is now doubled and the distance is halved. The gravitational force between M1 and M2 now is. So from Newton's law of universal gravitation, we know M1, M2 divided by r squared. This is the original. Now, if we apply the conditions, it's going to be G 2M1, and then it's going to be M2, then divided by, say, the half r squared. So that's going to be 2gm1 m2 multiplied by 1 over 4r squared. When we simplify, 2 divided by a quarter, that must give us 8. So which means it's going to be 8 times the force, which is option D. Then 1.6. If we have an object that is thrown vertically downwards towards the ground from a height h with a velocity v, the object strikes the ground and bounces upwards. Then it's caught when it reaches the maximum height. So at maximum height, the velocity has to be 0. So this one, I'll consider it to be an option. This one, I'll consider it to be an option. These two are out because we are seeing that after bouncing, I'm assuming this is the maximum height. Okay, or this is the maximum height, but then it just continues. Maximum height, but then it continues. So B and D, they are out. Now, when I look at the direction of the velocities, If a ball or an object is thrown downwards, we expect the velocity to increase and not decrease. So option A is going to be the best because velocity is increasing. And then the bouncing, and then it gets to 0. So I'm going with option A as my best option. And then 1.7, the crate is pulled up a slope. Which of the following forces will do 0 work on the object? The pulling force, this one is going to do work. The normal force, since it's acting perpendicular, it might not do work. Frictional force is going to do work. Gravitational force is going to do work, since there's a component of the gravitational force. So I'm going with option B, which is the normal force. Then 1.8. Okay, 3 identical spheres X, Y, Z are placed together in a triangular arrangement, each touching each other. The spheres are then moved back to their original positions. So for us to get the net or the charge on each one, remember they must all have the same charge after the separation. So I'll get the total -5. Okay, so that's a -5. What's happening to my pen? Okay, so -5 plus 0 plus 2. This gives us a 3 negative. Then divided by 3, we get a -1. So A is the best answer for that. Then 1.9. A positively charged object has fewer electrons, yes, but compared to what, neutrons? No. It has fewer protons. This is wrong. It has fewer electrons, yes, than the protons. This one makes more sense. Okay, if the electrons are more, then the object will be negatively charged. Okay, so I'm going with option C because it's the only one that makes sense, because this one, more protons than neutrons, no, can only have more protons than electrons. All right, then 1.10, the minimum resistance that can be acquired from a connection of two 4-ohm resistors. So when we have two 4-ohm resistors, remember the connection can either be in series or in combination, or in parallel. Okay, so if I look at the series combination, I'll have a 4-ohm and then a 4-ohm. So a 4 plus a 4, that will give me 8 ohms. That is maximum. Okay, and then if I look at the parallel combination, I'll have my product, which is 16 over the sum, which is 8, and then I'll have a 2. So I'm going to go with option B. Okay, because we say the product over the sum. So it's 4 times 4 over 4 plus 4. 16 over 8, it's 2. This is the smallest resistance that we can have. Okay, so that is how my number 1 would have gone according to the way I understood the questions. Okay. Then question number 2. Block M, that is 10 kilogram, is connected to block small m with a 2 kilogram with a rope T of negligible mass. Okay, there is a pulley here. Okay. Both blocks are at rest, and then the slope is 30 degrees with the horizontal. The frictional force cannot be ignored. And then they want us to define the term normal force. So it's a force with which you can say a surface, a force which a surface exerts on an object, okay, with which we can say it is in contact. It is in contact and perpendicular to the surface. So something like that. That could be the definition of a normal force. And then they want us to draw a labeled free body diagram of all the forces acting on the 2 kg. So when you look at the 2 kg, it's just the tension and then probably the weight. So we're not going to waste time there. We're going to say this is tension and then that's the weight. Then they want us to calculate the frictional force needed to keep the blocks at rest. The frictional force needed to keep the blocks at rest. Okay, so what I'm going to see, I can look at it block by block. Okay, if I look at T, I know that I'm going to have the frictional force. I don't know which direction should I assume the object is moving. So since the 10 kg is bigger, I'll assume the direction of motion is this side. So I'll have Fg parallel, then I'll have my frictional force there. Okay, let me try to make sense out of this. So when I look at the first body of the 2 kg, okay, so we're gonna say that with the 2 kg body, with tension, let me start with net force is equal to MA. Okay, so tension minus the weight must give me the mass and the acceleration. But the objects are at the rest, which means they're not going to move. So our acceleration has to be 0. So which means the tension is equal to the weight, which weight is going to be 2 multiplied by 9.8. Okay, so when I punch that into my calculator, I'm getting 19.6 newtons. Then let me also consider the 10 kg body. So what we are saying is that we are assuming that the object is moving downwards. So which means the F net is going to be the Fg parallel minus the frictional force minus the tension must give us the MA. I don't know if that is going to make sense. So we're saying the Fg parallel minus the tension minus the frictional force must give us MA. But our MA will be 0. Then, since we're looking for the frictional force, we can just transpose it that side. Fg parallel is the same as mg, the sine of theta minus the tension is equal to the frictional force. The mass is 10 times 9.8. The sine of 30, I'm subtracting the 19.6. Why am I saying 19.n? Okay, I'll punch this into the calculator. 10 times 9.8 sine of 30 minus 19.6. This gives me 29.4 newtons. So this is what I'm ending up with as my frictional force. Okay, just to keep the object without moving. Okay, then 2.4. They're telling us that the rope snaps. Okay, and then M decides to slide down. The kinetic frictional force is 25 Newton. Okay, since there is no tension, the frictional force is going to be that much. Now they want us to draw a free body diagram on this 10 kg. So we can see that there is no tension. The friction is going to act upwards, and then we're only going to have the Fg parallel. We're going to have the weight, and then the normal force there. So how many marks is it? It's 4 marks. So we can have approximately 4 forces. Okay, so I'll just, let me put it this side. This is 2.4.2. It's 0.1. Okay, so we said frictional force there. We said Fg parallel. It's saying the weight there. and then that's going to be our normal force. So that should be our free body. Then for 2.4.2, they are asking us to calculate the magnitude of the acceleration. Okay, so we need to get the acceleration with which the object will be moving downwards. So what I'm going to do is I'll still consider more or less the same thing and look at my free body and say that my F net is equal to, so I'll have my FG parallel minus my frictional force must give me the mass multiplied by the acceleration. So mg sine of theta, my frictional force, we already have it, must give us the ma. I'll substitute, so 10 times 9,8 sine of 30 minus the 25 must give us the mass, which is 10, and then the acceleration a, which I don't know. When I substitute, when I punch these numbers, 10 times 9,8 sine of 30, then I'm subtracting 25, I'm getting 24 on the left. Okay, is equal to 10a. Divide both sides by 10, which means our a is 2,4 meters per second squared. Okay, so that is what I'm getting for 2.4.2. Then we move on to 2.5. They're telling us that block M, the small block, just takes a half of a second to reach the ground. They want us to get the final velocity. Okay, so what are we going to do? So they are telling us that the time, this is 2,5.1, is 0.5 seconds. What do they want? They want us to get the final velocity, Vf. So V initial, I'm going to be 0 initially when it was just hanging and dangling. Okay, so I will use the V final is equal to V initial plus acceleration times delta t. So my V final is going to be 0 plus my acceleration now is going to be under free fall, which is going to be 9,8 multiplied by 0,5. And that's going to give me 4,9 meters per second. That's what I'm getting in that case. Since it's after the snapping, the object will just fall under the gravity. So that is 2.5.1, and then 2.5.2. How would the final velocity of M be affected if the mass was doubled? Okay, and dropped from the same height? Increase, decrease, or remain the same? So in this case, I'm going to go for remain the same. Okay, why? Because it's just more or less the same as the first question we answered under the multiple choice. Okay, so I'm gonna say it's just gonna remain the same, and the reason for this is that our velocity is independent of the mass. The velocity is independent of the mass, and the motion of the object will entirely be affected, I'll say, by only the gravitational force. Gravitational force. So in other words, it will be some sort of a free fall. Okay, so that is question number 2. Question number 3, they are telling us that the Curiosity rover was dropped from 125 kilometers above the surface of Mars. The mass of the Curiosity rover is this much, and then the mass of Mars is this. The radius of Mars is 53.25% that of the Earth. Then they want us to state Newton's law of universal gravitation. So we know that objects in the universe, they exert a force between them that is directly proportional. Let me just write it this side. So it's saying 3.1. So the force between two objects in the universe is directly proportional to the product of the magnitude of their masses, and then inversely proportional to the square of the distance between their centers. Okay, something like that. That would be universal law of gravitation. And then 3.2, they want us to calculate the weight of the curiosity on Earth. So we know that weight is given as mass times gravitational force. We know that the mass is 899. We're multiplying by 9,8 because the gravity on Earth is 9,8. So 899 times 9,8, that gives me 8810,2 newtons. Okay, so saying this, 2 newtons. That is 3.2. Then 3.3, they want us to get the gravitational acceleration on Mars. Let me just write it. So we know that G is equal to capital Gm over r squared. Okay. So what is the value of G? G is given as 6,67 times 10 to the negative 11. What is the capital M? That is the mass of Mars, which is 6,42 times 10 to the 23. And now when it comes to the radius, we need to determine the radius of Mars. He told us it's 53,25, that of Earth. So for R, I'll say 53,25% multiplied by the radius of Earth, of the Earth. So I have to check the formula page. From the formula page, we can see that the radius of Earth is 6,38 times 10 to the 6. 6,38. Okay, so 6,38 times 10 to the 6. Okay, so what does this give us? 53,25% of 6,38 times 10 to the 6. So I end up with 3397350. Let me just use it the way it is. Okay, I'll substitute 6,67 times 10 to the negative 11 multiplied by 6,42 times 10 to the 23 over 3397350, but then I have to square this. Okay, so when I punch this into my calculator, times 10 to the negative 11 multiplied by 6,42 times 10 to the 23, dividing it by 3,350 squared, it's giving me 3,71. That's going to be meters per second squared. So this is the gravitational pull, or the force acceleration. Okay, then 3.4. Would the mass of the curiosity be different on Mars than on Earth? Yes or no? The answer is a no. Work done is equal to the change in kinetic energy. Okay. Then 6.5, use the work energy theorem to calculate the speed at the height of this 5 marks. Now, when I look at this question, remember this object is moving upwards. I can look at it as a projectile. Okay. So if I use that scenario, I might end up losing the marks, but I will get the same answer. Okay. So what do they want? They want the speed when the object is at a height of 11. Now let me use the work energy so that I don't deviate from what we have. Okay, so this is 6.5. So what I'm going to do is, since I had a free body diagram, I can start by probably getting the tension force. I mean, I was given the acceleration of the system. I can look for the tension and then look at the work done by almost everything there. So what I'm going to do, I'll say W net is equal to the change in EP plus the change in EK. Okay. But why do I need, no, there's no need of using this. I'll just use the change in EK. But for me to get the work net, I'll get the work that is done by the tension minus the work done by the FG. Should be equal to the change in the kinetic energy, which is going to be a half m v final squared. You can subtract the v initial squared, it's fine, but we already know that the v initial is a 0. Okay, so we need to get the tension first of all. So we're gonna say that F net is equal to MA if I just focus on the body or the free body that I drew. So it's gonna be tension minus the weight should give us the mass and the acceleration. So which means my tension should be the mass acceleration plus the weight. So the mass is 85. The acceleration is 0.7. They said 5. Perfect. And then plus our weight, which is 85 times 9.8. Okay. So 85 times 0.75 plus 85 multiplied by 9.8. I'm getting 896.75 newtons. Okay, so initially, now I need to get the work done by this. Okay, so it's 896.75 multiplied by the distance, which is 11, and then the cos of 0, since it's moving the same direction. Okay, that's gonna be 9864.25 joules. Okay, so 9864.25 minus the gravitational, we got 9163 is equal to a half times 85 v final squared. Okay, so when I subtract that 9163, I'm getting 71701.25 is equal to 40. Is it 47.5? No, 42.5 v final squared. Then I'll divide both sides by 42.5 over 42.5. This cancels that, and then I need to find the square root on either side. So my V final is gonna be 4.06 meters per second. So even if I were to use the equations of motion, I was gonna get the 4.06. How? If I use the Vf squared is equal to Vi squared plus 2a delta y. We're looking for Vf. So it's gonna be square root, V initial is a 0, plus 2 multiplied by our acceleration, which is 0.7. Now I can't use that. No, I can actually. So it's 2 multiplied by 0.75 multiplied by 11 to give me that. But this does not apply to the work energy theorem. Okay, then 6.6. They're telling us that a 30 kilowatt motor is used to lift the mass of 85 kilograms to a height of this. Calculate the percentage efficiency of that. Okay, so what we're going to do first of all, we know that our network was 9864.25, the network done by the tension, because we're focusing on the motor, and then the motor is having the cable within it. So we can say that power is given as the work done divided by the time. Is it possible for me to get the time, which will be work multiplied by the power? So the work done was the 9864.25 that we just calculated over the power, which is 30,000 watts. Okay. Then I'm gonna get, I divide that, I'm getting 0.329 seconds. Then I need to look for also the energy input, which is still gonna give me power multiplied by the time. So I'm moving in circles. So still the 30,000 for the motor, multiply the time it takes, which is 0.329. I mean, I'm just gonna get the same answer of this. And then when I look for efficiency, it's gonna be the input over the output times 100%. So our input is 9864.25. The output is just the same thing. We're multiplying by 100%. So the motor is 100% efficient, which is very rare. According to the question, this is what I'm getting, but in real life, it's hardly possible for something to be 100% efficient. Okay, question number 7. The siren of a rescue vehicle emits waves at a frequency of 360 Hz, and then the frequency of the sound as heard by the listener that is standing by the roadside is 405. Define Doppler effect. So Doppler effect, we know that it is just the change, okay, in the frequency of sound detected, frequency of the sound detected by the listener. Okay, and why is this? It's due to the change in the velocities of the listener and the source, but relative to the medium of sound propagation. Okay, there you have your 2 marks. Then 7.1.2. Was the rescue vehicle moving towards or away from the listener? Explain the answer, making specific reference to the frequency, wavefronts, as well as the wavelength. So the fact that the frequency is higher, okay, is going to be moving towards. Okay, so what's going to be our explanation? I'm going to say that the observed frequency observed frequency is higher than the emitted. Okay, so as the vehicle approaches, okay, the wavelength decreases. The wavelength will decrease, and since wavelength is inversely proportional to frequency, then the frequency will be high. Okay, then 7.1.3, take the speed of sound in air to be 340, calculate the speed with which the vehicle is moving. So I'll do it this side. So we know that frequency of the listener is equal to V plus minus velocity of the listener plus minus velocity of the source times the frequency of the source. So they told us this was a 405. They told us that's a 340, I'm going to say plus on top. Velocity of the listener is a 0 over 340 minus velocity of the source, which we want, times 360. Okay, so what I'm going to do, I can have 405 over 360 is equal to 340 over 340 minus Vs. When I do my cross multiplication straight away, I can have 340 minus Vs is equal to 340 times 360 over 405. Okay, so when I simplify what is on the left, so on the right, I'm having 302,22. Then I just have to move this aside. Vs must be 37,78, which means it's 37,78 meters per second. Okay. Then 7.2, the driver of the vehicle continues at this speed past the stationary listener. What change or changes, if any, would occur in the following? Write down the values. So the frequency of the siren as heard by the driver. So this must still be the same. Okay, 360 hertz. The frequency that is observed by the listener. So now that frequency is going to be 340. It's going to be minus 0 over 340 plus the 37,78 multiplied by the 360. Okay, when I do that, you know that it should be smaller. I'm going to have 320,47 hertz. And then the speed of sound is still going to stay the same. Okay, 340 meters per second. So that is question number 7. Question 8. Point A and point B are 0,04 meters apart as shown. The sketch not drawn to scale. X lies this much, and then sphere X has 1238 electrons that were removed from the surface. So what is the nature of the charge on X? Choose positive or negative. I'm going to go for positive. Why? Because electrons were removed. As long as electrons are removed, then the sphere will stay more positive. Then calculate the magnitude of the charge on sphere X. So I could use the formula or the equation. This is 8.2 of Q is equal to NE. They need the charge. So the number of electrons were 1238. Multiplied by electron charge is 1,6 times 10 to the negative. What is this? Yeah. To the negative 19. That's gonna make sense. Determine the charge. Oh, that's fine. So if that is removed, so if I multiply that, I'm gonna get 1,98 times 10 to the negative 16 coulombs. Okay. Let me just check this paper. Okay. Okay, mass of electron. Is this? Okay, that's fine. I'm gonna take that to be my answer. And then define the term electric field. So electric field is just the region of space, okay, in which a charged particle or a charged object experiences what we call an electric force. And then 8.4, draw a net electric field pattern of two identical with opposite charges. Okay, so we know that opposite charges usually do attract. Okay, so we're gonna have 8.4, that's a positive, it's a negative. Just have field lines that are moving. As long as the field lines do not cross or do not touch each other. So the arrows should also be indicated correctly. Okay, so that is 8.4. And then 8.5. At point A or B, or at what point between A or B is the magnitude of the electric field due to the charged sphere X greater? We must explain our answers. So we know that electric field is given as a force over Q, which is the same as AQ over R squared. Let me use this. So you can see that the electric field is inversely proportional to the radius squared, which means if the radius is increased, the electric field is going to become smaller or weaker. And if the radius is smaller, the electric field is going to be stronger. So I'm going to go between point A or B. So I'm going to go with A. Okay. And the reason for that, I can say that E is inversely proportional to 1 over R squared. That would be my answer. But I can put it in words and say electric field is inversely proportional to the distance of separation, or to the square of the distance of separation. Then 8.6, calculate the electric field of sphere X at B if sphere X is replaced with that. So let's do that. KQ over R squared. So 9 times 10 to the 9 multiplied by now our Q, which is going to be 2 times 10 negative. Okay, then I'll just do the substitution. 9 times that and that, I'm getting 20,000 Newton per Coulomb. Then 8.7, a negative point charge Y with this is replaced at B. Okay, this is B. Let me just put it this way. Okay. So B is somewhere there. We have X, and then we have A. Okay, so we have 3.2, and then we have negative 2,8. Initially, remember it was a 2, it's just a 2 times 10 to the negative 9 at point X. They want us to draw a vector diagram to show the direction of the forces on the charge X as a result. So why can't I just put it down here? We can see that B is positively charged. No, Y with this is now placed, so it's a negatively charged, 2,8. And then at A, we have a 3,2, which is positively charged, and then X was negatively charged. Okay, so between A and X, since the signs are opposite, there's going to be attraction. So which means at X, the force of AX is going to act to the right, And then since these two are of the same signs, it's going to be repulsion, which means the force of B due to X is going to be on the opposite direction. So this should be your vector diagram. The force on X as a result of A, force of X as a result of B. That should be the vector diagram. And then 8.7.2, they want us to calculate the net electrostatic force between the two. So we need to calculate the FBX and then the FAX separately. Okay, so I'll come down and say this is 8.7.2. FA of X, KQ of A, Q of X divided by the distance of separation, 9 times 10 to the 9, multiplied by my A, we said is 3,2 nanocoulomb. So that's going to be 3,2 times 10 to the negative 9. Our X is negative 2, so just use the 2 times 10 to the negative 9 over 0,01, but everything is squared. Okay, so when I punch that into my calculator, I'm getting 3,2, and that I'm getting 5,76 times 10, 1, 2, 3, 4 to the negative 4. This is newtons. And then F B of X, still the same formula, substitution, negative is positive 9, multiplied by 2 times to the negative 9, multiplied by, we say it's going to be 2,8 times 10 to the negative 9. Dividing this by 0,03 squared. This is going to give me 5,6 times 10 to the negative 5 newtons. Then my F net is going to be 5,76 times 10 to the negative 4 minus 5,6 times 10 to the negative 5. Okay, so that gives me 5,2 times 10 to the negative 4 newtons. So that is the net electrostatic force. Okay, then question number 9, telling us that a circuit diagram is set up as in the diagram below. Resistors R1, 2, and 3 are identical, which means they have the same value. Switches S1 and S2 are closed. Ignore the internal resistance because it's for third term. Good. Then they want us to state Ohm's law in watts. So we know that Ohm's law will tell us that the potential difference across an electric conductor is directly proportional. It's directly proportional to the current through the conductor, directly proportional to the current through the conductor at a constant temperature. So the temperature has to be the same or constant for that to happen. 9.2, they want us to name the component of a non-ohmic conductor in the diagram above. So I'm going to go for the bulb, or some people call it the lamp. Okay, because resistors are all ohmic. The ammeters, these ones just measure, so they cannot be used as non-ohmic conductors. So I'm going for the bulb because name the component of a non-ohmic conductor in the above. So we know that the bulb, what does a bulb have? What do we call those springs inside that give the light? That could be also an option to tell us that those springs. Okay, then 9.3, write down the reading of the voltmeter with both switches closed. So if both switches are closed, these systems are going to be in parallel. And if that is true, which means the voltage is maintained, it has to be the same. So it's going to be a 12V. Then S2 is open, and it's just these two that will be in series. But we know that the total voltage across the VR2 and the VR3 must be equal to the Makul V. So still 12 volts, since the voltmeter is connected across the terminal. Then 9.5, switch S2 is closed and S1 is open. Now the moment you open S1, there is no current that is flowing. Nothing is happening there. They want us to get the voltmeter ready. So it's going to be 0V. Then S2 is opened. How would this affect the ammeter reading? So if this resistor is out and we have just this two, is the ammeter reading gonna stay the same, increase or decrease? Now let's take this to be 2 ohms, 2 ohms, and then 2 ohms. These two are in series. For them to be combined, we shall have just a 4 ohm resistor, one block that is a 4 ohm. Now the moment we have a 2 ohm and a 4 ohm combined, if both switches are closed, we shall have a product over the sum, which is like 8/6. That's 4/3, which is 1,3 ohms. That's going to be our effective resistance. Now, if this resistor is out, we're going to have an effective resistance of 4 ohms, which is bigger. So if the resistance is bigger, the current is going to be. Let's see. If that is going to make sense, let's see. But telling us if S2 is opened, okay, so there's no more flow of current this side. It's just the same current that is flowing through the circuit. Originally, the ammeter reading was constant. So if switch S2 is opened, how would this affect the ammeter reading? But the ammeter reading is connected, not even close to any of these. So the ammeter reading is going to stay the same, guys. It stays the same. Okay, then 9.4, both switches are opened. Resistor R1 is removed. How would this affect the voltmeter reading? So both switches are closed, but then R1 is removed. So there's no resistor here. It's just that. Is there any voltage across? Is there any voltage across? Yes. So how will it affect the voltmeter reading? Voltmeter reading is gonna stay the same. It's gonna stay the same. So guys, that's all that we have to do. But remember, this is a proposed memorandum. Yes, there could be hiccups here and there. We're human, okay? If there are any issues, please just load them under the comment section. Shall rectify them. Welcome to this episode where I shall be looking at the revision of the Physical Sciences Paper 1, okay, for September for the preparatory examinations, okay? So in Paper 1, there are a few topics, or the structure of the paper that we can look at is number 1. We always expect to have some 10 MCQs, okay, multiple choice questions, and they normally account for 2 times 10, which is like 20 marks. And these MCQs will cover all the topics of paper 1. Then number 2, we have the motion, okay, or laws of motion. That's another topic. And then number 3, besides this motion, or we can just break down the motion and say it's normally the vertical projectile motion, okay, where the laws of motion need to be used. And one thing that we need to put into consideration is basically the directions that we normally use. Okay, so the laws of motion normally take between, I think, 2 questions. And then from there, we can have our momentum, as much as momentum is also still motion, but it's fine. So that's momentum together with the cousin called impulse. Okay. And then after that, we can have our work energy and power. And then from the work energy and power, we need to know at least that theorem. Okay. What is it equal to, and how do we transform it from words into its application? And then next, we have what we call the Doppler effect. Okay, usually this is 1 question, just like the work energy and power. And then from Doppler effect, we have what we call the electrostatistics. Okay, electrostatistics. We need to remember the Coulomb's law and the formula, okay, of calculating the force and all of that. So it's also 1 question. Then besides electrostatics, we have what we call electricity, which is basically electrical circuits. And then from electricity, we have the motors and generators, electrodynamics. Normally call them motors and generators. And then lastly, we can have our photoelectric effect. Okay, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so we have basically 9 aspects, so areas that we shall be focusing on. Okay, so I'll try to follow the order of the question paper. Okay, but in most cases, when I'm advising learners, if you're writing any paper, start with any question that you are comfortable with so that you can maximize the amount of time at your disposal. Okay, question number 1, which is the multiple choice questions. They're telling us that various options are provided as possible answers. The following questions must choose the answer and write only the letter A to D next to the question number. Okay, so question 1.1. They are telling us that the impulse delivered by a net force, okay, impulse delivered by a net force that is acting on an object is equal to impulse delivered. So we know that impulse is also the change in momentum. Okay, change in momentum is also the same as impulse. The change in P is the same as the impulse. But now we're talking about the net force. So impulse delivered by a net force is equal to the change in momentum. So I'm going to go with option C, because option A talks about the initial momentum. Nope. Final momentum, rate of change of momentum. Rate of change of momentum is the force itself. But now they're talking about the impulse. So change in momentum would be the best option for that question. Then 1.2, the graph below represents the relationship between the net force as well as the displacement it undergoes. And then the force and displacement are in the same direction. So if we have F net is equal to delta X and something that we don't know, what are they looking for here? Because that's not mass and acceleration. Okay, which one of the following statements can be deduced from the graph? They're telling us that the area between the graph and the displacement axis represent the net work done. I think that makes sense. But does it make sense? Net work done, if you look at the area that is under here, because we know that for us to get the area here, it's going to be force multiplied by the displacement, which is correct. Okay, which is correct. Work done. Let's see. The area between the graph and displacement represents the power. No, with power, there has to be time. We don't have any delta t, so we can't use this. And then the gradient of the graph represents the change in kinetic energy. Change in EK is equal to W net, the net work. And here we're just looking at the net force. Okay, so this is out also. Then the gradient represents the work done. When you talk about the gradient, so it's like F net over the displacement, which is like the work done by the force. Is that true? Nope, 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 nope. That is not true. Because we know that work done. Okay, remember we said work done is this force times the displacement. Now, if you have the force over the displacement, then that is like the reciprocal of work. So the best option for me would be option A. Then 1.3, a ball is dropped from a certain height above the ground and bounces a few times as it hits the ground. The VT graph describes the motion of the ball from the time dropped. Ignore the effects. Okay, so from here, velocity 0, which means it was just dropped. It attains the velocity by the ground. Okay, then bounces off and reaches its maximum at D. And then goes back again for the bounce. And then reaches also a 0 or the maximum at that point. So in the relation to the velocity time graph for the bouncing ball, which statement is correct? Okay, we need a statement that is correct. They're telling us that down is taken as a positive direction and the ball is at its highest position at point C. Nope. So this C just cancels the whole scenario. This is out. Remember, maximum position is basically D and that other point, okay? Or even point B. I wouldn't really call that. Okay, let's see. But I'll go for this one to be the maximum position. Okay, then option B, down is taken to be positive. This is also wrong, okay? And the ball is at the highest point at D. So the last part is correct, but then the first part is wrong. Then C, down is taken as negative, okay, which is correct. And the ball is at its highest at C, which is wrong. This last part is wrong. And then down is negative, the highest point is D. So D is the best option. And then 1.4, they're telling us that an ambulance approaches this person as he is standing beside the road. As the ambulance drives away from him, the pitch and the wavelength of the siren that he hears will undergo the following changes. Okay, so we know that the pitch refers to how loud or how low the sound note is. And if the ambulance is moving away, the pitch forms because of atoms in the element that are or that will absorb, because this is an absorption spectrum. So there is no an absorption spectrum emits. No. So A is out, B is out. Let's look at C and D. So absorbs light, photons, and atoms, electrons, making a transition from high to a low. Absorbs light, photons, and atoms, electrons, making a transition from low to a high. So when it absorbs the light, it gains energy. And there's no way you can start from being a hero to a zero when it comes to this sort of absorption spectra. You always have to start from a zero and then become a hero. So option D becomes the best. Okay, start from zero, you go up. All right, then 1.6, two objects with the same mass, with a certain distance d between them, exert a force on each other. Okay, if the mass of one object is doubled and the distance stays the same, the force between the two will also be doubled, because we know from Newton's law of universal gravitation, Gm1 m2 over r squared. If you change this by 2, which means the entire force is going to increase by 2 also. So option C would be the best. If ever it was the distance that was doubled, then the force would be now a quarter. Okay, if both masses were increased by 2, they were doubled, then the force will be 4F. All right, then 1.7 diagram below shows a point P at a distance r from a charged sphere Q. And then they are telling us that the electric field strength at P is directly proportional to R and to the right. So let's start by finding out what's the formula for electric field strength. So we know that it is K. Is that really correct? Because it's a KQ over R squared, yeah? Something like that. But now when you look at the electric field strength and the distance, they are inversely proportional. Let me just confirm with the formula. I don't want to mislead people. Let's confirm it. We said electrostatistics. Okay, so it's KQ over R squared. Thank you. All right, so if that is the case, so option A is out. It's not directly proportional. Option B is out. It's not directly proportional to the square of the distance. So these two are out. Okay. Then C and D inversely proportional to the square of R. That's okay. Inversely proportional to the square of R. And then they're telling us it's to the right. And then this one is giving us to the left. So we know that if P, we normally take P to be a positive charge, okay? And if it's a positive charge, what's going to happen here? It's going to be attraction, okay? So the electric field is saying it's going to be attraction, this one, this side, this one, that side, okay? At P. So when you're focusing on P, the force, this force will work on P in that sort of direction. Does it make sense? And then this one will work in that sort of direction. So I want to believe that P is going to have inversely proportional to the square of R, and it's going to be on the left of P. Okay, so that is 1.7. Then 1.8, which of the following statements about an AC generator is true? They're telling us that the minimum potential difference is not 0 volts. This is wrong. The EMF produced decreases at the number of windings. This is wrong. The EMF must increase. The maximum value of the AC can be increased by increasing the period of rotation. Nope, you can't. Then the maximum value of the AC produced can be increased by increasing the speed. That's correct. So option D is the only correct option there. Then 1.9. A battery with internal resistance connected to a fixed resistor R. The voltmeter is connected across the battery. As we can see in diagram A, the battery is replaced with one with the same EMF, but with a larger internal resistance. Okay, as in B. So this is 0,4, this is 0,2, okay, as we can see. Then they're asking us that how would the voltmeter reading and the current through the fixed resistor change compared to A when the switch is closed. So when you look at this in diagram B, so our focus is mainly on diagram. Is it B or A? Because they're telling us that the battery, because our focus was A, the battery is replaced by 1 with the same EMF, but with a larger internal resistance as shown in B. 1, 2, so the same EMF, but it's just the internal resistance that is greater. How is this going to affect the reading of that? Now, one thing we need to know is that the current we have change in Y, delta Y is equal to VI times delta T plus a half A delta T squared. But what we are saying is that the A is going to be replaced with a G. In most cases, A is going to be replaced with a G. Now, depending on the direction of motion, okay, because we need to take also consideration when doing that. So I usually prefer to take upward motion to be negative, okay, if it is upward, and then downward motion to be positive. So if we're focusing on downward, then this will be a plus, plus, and plus. Then if it's an upward motion, this can be minus, minus, and minus. That is my approach. It's also believed, we know it can also work, whereby someone can take the downward motion to be negative, okay, and then the upward to be positive. You just need to state your case. You'll always get the same answers in whatever calculations you're gonna do, for as long as you maintain the signs that you deciding to go with. Okay, so having looked at that, I believe we're good to start with the questions. Okay, I'm just gonna go through some questions. If time allows, I'll cover as much as I can. Okay, question number 1. We're being told that a cricket ball of mass 156 grams is dropped from point A on a tall building that is 15 meters high, and then it strikes the concrete pavement, and then it bounces off. And then it bounces off. So this object is dropped, it falls, hits the floor, and then it bounces off to a height of 4, maximum height of 4. Then they're asking us to calculate the velocity with which the cricket ball strikes the pavement. So for as long as an object is dropped, then the initial velocity is going to be 0. And this question is asking for the final velocity. So we're gonna say our initial velocity is 0, our final velocity is what we don't know or what we're looking for. The only thing we've been given is the displacement. Change in Y is being dropped from a height of 15 meters. Then we need to select which equation are we going to use. Since our focus is V final, we have the V initial and we have the displacement. So the equation to use would be the VF squared is equal to VI squared. Since the object is being dropped, we said I'm going to take positive to be the downward motion. This is 2G delta Y. Then I'll do my substitution. So that's going to be our VI, which is 0 squared plus 2 times 9,8 times the displacement, which is 15. Okay, when I put that into my calculator, I'm just getting something like this is 2 times 9,8, is that true? And then times 15. So that gives me 294. So VF squared is 294, and then I need to find the square root. Okay, then the square root of my answer gives me 17,15 meters per second. Okay, that is question number 1. Then question number 2, 1.2. If the effects of air friction are not ignored, in other words, if they are put into consideration during the fall of the cricket, how would the value that you calculated here change? Will it be higher? Will it be lower? Or will it stay the same? So guys, what do you think? If there is resistance involved, if there is friction involved, what effects does friction have in the final velocity? So in this case, I'm gonna go for lower. Why? Because friction, we said, is a force that opposes motion. So for as long as it's trying to oppose motion, because the ball is falling downwards, friction will be acting upwards. So which means this ball is gonna fall with a lower velocity. Okay, and then 1.3, they're telling us that the cricket ball is in contact with the concrete for about 0.8 seconds. So that 0.8 is more of a reaction time. Okay, so if we ignore the effects of air friction and we are taking downward motion as positive, okay, calculate the impulse. What do we do when we are getting impulse? We know that from your momentum, impulse and stuff, you might have said that our F net is the same as change in momentum, the rate of change in momentum, something like that, delta P over delta T. Does that make some sense? F net is this. So when we talk of impulse, it's the change in momentum that we're focusing on, which means our change in momentum will be the F net times the delta T. But what is our F net? We know that F net can also be written as ma, m times the acceleration. And acceleration can also be expressed, since in this case we don't have the acceleration of the object, we can use the velocities, okay, and say the mass, which is v final minus v initial divided by the time. Mass times acceleration, which is v final minus v initial over t. We can use that as well before we can get to the actual answering of the question. Okay, so I'm just gonna erase this and just start over. Okay, so what I need to first of all find, what is the initial velocity or the final velocity that we're focusing on. So for as long as the cricket ball is in contact with the pavement for this much, and we're taking downward, calculate the impulse of the cricket ball on the pavement. So our final velocity is going to be assumed to be a 0. Okay, as soon as this ball strikes the ground, and then takes some time. Okay, initial velocity, I don't know that. My G is gonna be 9,8, and then I'm going to look at, what's this? I'm gonna look at my displacement to be, is it 4? Yes, I'll look at my displacement to before. It makes sense though. Yeah, displacement is gonna be 4. And then from Vf is equal to Vf squared is equal to Vi squared plus 2g delta y. When I try to do the substitution with the 0, this is Vi squared plus 2 times 9,8 times 4. So now as I'm finding the velocity with which the ball started to rise up. Okay, so we are saying the ball strikes. It takes some time just on the pavement, and then it goes up to a height of 4. Okay, so the velocity with which the ball left the ground or the pavement is what I'm looking for. So when I do the maths here, this is gonna be, why am I taking 4? Why am I taking 4? Because it's moving upwards now. So it's gonna be negative 4. Okay, so that is 2 times 9,8 times 4, which is 78,4. So 78,4 is equal to the Vi squared, and then I find the square root of that, which is 8,85 meters per second. So this is just the initial velocity with which the ball is gonna leave the pavement. Then I will apply my F net and delta P. Okay, so we know that our F net times delta P is equal to the change in momentum, and we said this change in momentum is the same as AM V final minus V initial. When we do the substitution, what was the mass of the ball? They mentioned something like 156 grams. Change that to kilograms, it will be 0,156. What is our final velocity? It's negative 8,85. Since it's moving upwards, we are subtracting the initial, which was our final when the ball was striking the ground, which is 17,15. 17,15, since it was taking the positive sort of direction. Okay, when I work this out, I'm just gonna get something like negative 4,056. This is mass, which is kilograms per meter squared. So since we're focusing on impulse, it's gonna be 4,056, but in which direction? It's gonna be upwards. Okay, then 1.3.2, they want us to get the net average force that is exerted. Okay, so since we know that our F net is delta P over delta T, our change in momentum is the negative 4,056, and we're dividing it by the time. The reaction time was 0,8 seconds from the information that we were given. So we divide it by 0,8. If that happens, then we're going to get negative 5,07 newtons. So this can also be written as 5,07, but upwards. Okay, so the force is going to act upwards. And then 1.4, they want us to sketch a position time graph. Now guys, we have different types of graphs when it comes to projectile motion. We have what we call the position time graph, we have the velocity time graph, and we also have what we call the acceleration versus time. Now we need to know how all of these look like. Okay, so if it's a position, in most cases it will take form of a curve, and then if it's a velocity time graph, we normally use straight lines to draw that. Okay, no, it's fine, we shall probably look at the different scenarios. So sketch the position versus time of motion of cricket ball from the moment it is dropped up until it reaches the maximum height after the bouncing. So what we need to remember, they said position time graph. So on our y-axis, we're gonna have our positions, and then on the x, we're gonna have our time. So this is position, which position can also be represented as the y. Okay, and the question is, at what height did the object start falling? Okay, this position is in meters, this time is in seconds. So the object started falling from a height of 15. Okay, and then the object dropped. We don't know the time it took, we don't even need it at the moment. Then this object took some time on the ground, on the pavement, and then it rose again for a certain height, which height we said was 4. So for as long as we have this, then we're good to go. So position time graph will always be a curve or made of curves. So this is the reaction time. Okay, then 1.5. The cricket ball is now replaced with a softer ball, okay, of similar mass. They want us to state how the net average force exerted by the concrete pavement on the softer ball, with your answer it's meant to be 1.3.2. We need to write only greater, smaller, or stays the same. So one thing we need to know is that from F net being delta P over delta T, change in momentum, we know that this net force is inversely proportional to the time. So if we are dealing with a soft ball is going to take more time on the pavement floor. In other words, the reaction time is going to increase. Okay, so when the reaction time increases, the net force decreases. Okay, so we're going to say delta T increases, which decreases the F net. So in other words, state how the exerted force is going to say smaller than. Okay, so the answer will be smaller than, because delta T increases, which decreases F net, because we know that delta T is inversely proportional to 1 over delta T. Okay, guys, that is question number 1. Then question number 2, it's more or less the same thing. We've been given a position time graph of a tennis ball. Okay, how do we approach a question when a graph is being provided for us? So they're telling us that the position time graph of a tennis ball that was thrown vertically upwards from a second floor of a school building shown below. Ignore the effects of friction. Okay, the height of the second floor is 6.5 meters. The ball rises 0.9 meters from the height of projection. Okay, so from here up to this point, that is 0.9 meters extra. Okay, before it starts to fall to the ground, so which means maximum height, an extra 0.9 meters. Okay, write down the magnitude and direction of acceleration of the ball while it's moving upwards. So the acceleration of the ball will always be 9.8 for as long as it's under a projection or projectile motion. Okay, and this acceleration acts downwards. regardless of whether it's projected up or down, it must always act downwards, since that is the initial direction of gravity. Okay, and then they want us to calculate T1, the time it takes the ball to reach the maximum height. Okay, one thing we know about maximum height is that the final velocity has to be a zero. That's one thing we need to know. Final velocity has to be a zero. So now, since we've been given displacements, we've been given the g's known to us, but we're focusing on the displacements. Let's say the distance traveled, Vy, is 0.9 meters. What else do we know? We know that our V initial, is it going to be a zero? It was projected vertically upwards from the second floor. Okay, so I'm not going to assume that. So I'm going to use this equation, Vf squared is equal to Vi squared plus 2g delta y, something like this. So we are saying at the maximum height, final velocity is zero. Is that true? Yes. But the question is asking for the time it takes. Let me see if I can get an equation that has time straight away, so that I don't have to waste a lot of time. This is Vi delta t plus a half delta t squared. And then F is Vi plus a delta t. I have that. Do I have the initial velocity? No, I have the initial position. It's not gonna make sense. So which means I need to first of all get the initial velocity. Okay, so my Vf is 0, my V squared I plus 2. Now the g is going to be negative 9.8 because the object is being projected upwards. And upward projection, I normally take g to be my negative. Okay, and then times the distance that the object traveled, which is the 0.9. Okay, when I sort that out, when I multiply that, I'm just going to use this to be positive since I've already considered the g to be negative. Okay, that is 2 times 9.8 times 0.9. That gives me 17.64. When I transpose that, Vi squared is equal to 17.64. Find the square root. The square root of the answer is 4.2 meters per second. So this is the initial velocity. So having obtained the initial velocity, then I can use this equation here, the first equation of motion, and say my final velocity is 0, my initial is 4.2 plus it's gonna be negative 9.8 t. I hope that makes sense. When I move, if I transpose, I have 9.8 t is 4.2. Divide by 9.8 over 9.8. Okay, so 4.2 divided by 9.8, I'm getting 0.428 seconds, which will be more or less like 0.43 seconds. Okay. That is 0.43 seconds. So that is that. That is being it in 2 steps. But someone can even use this second equation, this, since you're looking for t, and then you get that straight away. Okay, and then 2.3, they want us to calculate the initial velocity of the tennis ball at the instant that it's released. At the instant that it's, so we've already calculated that, okay, which means we've used a very long approach, which has already even answered the next question, but it's fine. So we say this is a 0, vi squared plus 2 times the 9,8 negative times the 0,9. Okay, and what did we say? We just transposed that. So vi squared is 17,64. Then when we took square roots, our vi became 4,2 meters per second. There's no harm doing that again, as long as it's going to give us the max that we desire. Remember, all questions normally have different approaches, quite a number of approaches. Then 2.4. Now they want us to sketch a velocity time graph. Okay, they gave us a position time graph, they want us to sketch a velocity. So we said velocity is always made up of straight lines, no curves. Okay, then I can put my time somewhere here, which is in seconds. So if this is the origin, what was the initial velocity? The initial velocity was 4,2, the one we've just calculated in the previous question. And then it took some time, which was 0,42 seconds, so 43 seconds to get there, which we can label as our T1. And then the graph continues. So it's just a straight line from here into that sort of direction. We don't need to mark this off as 0,43. You can if you have time, no problem. So it's calling this point A, where the ball started from, and then point B, which is more like the maximum height. At the maximum height, that can be point B, and so on and so forth. So after the maximum point, this section just tells us the direction or the velocity of the ball when it's falling down. So that is what one would do. Someone say, all of this for 4 marks? Yes. For as long as you have a straight line, not a curve, you get a mark. Then for as long as this part is shorter than the other part, because remember, this A to B is just the section from point of release up to the maximum point, which was quite a small distance. Okay, and then the 4,2, for as long as you've indicated it, you'll also get a mark. And then the time T1, which is the 4,3, you get the last mark. Okay, then let's look at question number. We need to do this because I feel like it looks more or less the same as what we've done, but it's fine, not a problem. We can look at it. Then question number 3, they're telling us that the sketch below shows the motion of a ball that is thrown vertically upwards from a balcony, and it takes 0,4 seconds, okay, to reach the highest point, after which it falls down past the balcony, boom, up to that. Then from the graph, how high is the balcony from the ground? So the ball is projected from the balcony, which means the distance from here up to there. That's how high the balcony is. So it's just 8 meters. And then 3.2, without any calculation, what is the numerical value of T1?
T1, somebody? Remember, this is more like a parabola. And this 0,4, where the time is at the maximum, or the velocity is 0. That is the maximum height. This is acting as our axis of symmetry. So if this is 0,4, even this must be 0,4. So which means that is 0,8 seconds without any calculations. So that is just the logic. And then 3.3, they want the initial velocity. So we shall use more or less this, can use the first equation and say V final is equal to Vi plus A delta T, the initial velocity. So we can use the final velocity at this point of the maximum. Okay, so I'm gonna take the V final to be 0. Vi is what I need. I'm gonna say plus, I'm gonna use negative 9,8 times my delta T 0,4. Okay, so 9,8 times 0,4, I'm getting 3,92. Okay, then Vi minus 3,92 is equal to 0. Then move it that side, which means the initial velocity is 3,92 meters per second. Which direction? It is basically upwards. It's upwards. Okay, and then 3.4, they want the maximum height above the ground that is reached by the ball. Now, since they're asking for maximum height, that is like displacement. Which displacement formula can we use? We can use. I don't know. Let's use the second equation, which is delta y is equal to Vi times delta T plus a half A and then delta T squared. I think this can work. So they want the maximum height above the ground, so we're looking for delta y. So what is our initial velocity? We got it as 3,9. So guys, regardless of what value you get, for as long as that value is gonna be used in the next question, please use it, even if it's wrong. Okay, it will do you some good for consistency's sake. So the time was 0,4 seconds plus a half, since the direction of projection was upwards, gonna be negative 9,8, and then we're multiplying that by 0,4 squared. And I use my machine. 3,92 times 0,4 plus a half times negative 9,8 times 0,4 squared. I'm getting 0,78 meters. So this is just from the point of projection. So 0,78. So just from here up to there, that is 0,784. Now, since they're talking about from the ground, the distance from the ground, or the height from the ground, it's gonna be the 8 plus the 0,784, which becomes 8,784 meters. And then lastly, no, it's not lastly, 0.5, calculate the magnitude of the final velocity of the ball when it reaches the ground. Okay, so in this case, we can look at number 1, either break down the journey into 2. Someone may choose to focus on the second part of the journey of the ball, which is like from the maximum point up here. Since we know that at this point, the velocity is 0, so which means this will be our initial velocity, and we're looking for the final velocity, which will be 0. This one, the initial velocity. The time it took, we don't know, but we can get an appropriate formula. Or alternatively, someone can take the entire journey of this ball and then still get to the same result. So in this case, I'm just gonna look at just from the maximum height, the first scenario. So if I use Vf squared is equal to Vi squared plus 2a delta y. Since I know my maximum height, I can use that. So they want the final velocity. So this is Vf squared. Initially, at the maximum height, the velocity was 0. So that's going to be 0. Plus 2. Our acceleration is negative 9,8. And then our height is 8,784. You could round that off to 2 decimals. There's no problem. So that is 2 times negative 9.8 times the 8.784. I'm getting, does that even make sense? Yes. I'm getting negative. No. If I use negative, then that means I'm using the initial root. But if I'm focusing on just the section from the maximum to, then it's meant to be positive. So that is 172,1664. That is Vf squared. And then I can find the square root of that. Square root, my answer, I'm getting 13,12. Okay, that's 13,12 meters. So that is going to be our maximum velocity or terminal velocity. So we said alternatively, someone can use that other route of the entire journey. Okay. So if you're using the route of the entire journey, then your displacement is just gonna be 8, because from the point of projection up to the same point of projection, the displacement is gonna be 0, and then we focus on just the 8. Okay, if we try that out, we said our initial velocity. Now let's try it out and see. Maybe let me just jot it down here. Just for the sake of space, I'll erase it. Okay, I'm using just the same thing. Vi squared plus 2a delta y. So we got our initial velocity as 3,92. That's what I want to use. So 3,92 squared plus 2 times now negative 9,8 times 8. 3,92 squared. Is this gonna make sense though? Something's fishy, something's fishy, something's fishy here. Guys, no, it's okay. Let's just ignore that and just use that formula. There's no need for second option. How does it test that? It's okay. Then 3.6, they want us to draw velocity time graph. Okay. So if this is the velocity, and then that is the time in seconds, velocity in meters per second of the motion of the ball, indicate the following: initial velocity, final, and the time taken to reach the maximum. So our initial velocity, we said, was 3,92. Okay. And then the final velocity, we said it's 13. We said at maximum, what is the time? We said that was 0,4. So we're just gonna draw a line. It must be longer. And then we can put the 13 down. Then we can call this 13,12, but in the negative. Okay, it's not a big deal for as long as you have the initial or you have these 3. It's a mark for each. Okay, then we move on to the next question. Question number 4. Question number 4. What do they want us to do? They are telling us that a boy kicks a ball, okay, vertically upwards from a height of 0.6 meters above the ground. Then the ball moves past the top of the building 21 meters higher than the original point from where it was kicked. And then the ball hits the roof in 3.1 seconds after it was kicked. Then the ball bounces off the roof and then it comes to rest. So the ball is kicked, it goes up past, reaches maximum, hits the roof, bounces off, and then it gets to rest. Okay, then they're asking us to write down the magnitude and the direction of the acceleration of the ball at point X. Where is point X? So point X is not indicated on the question, but regardless of where that point is, even if it's there, even if wherever it is, I don't know whether it's that. So that's gonna be just 9.8, and the direction must always be, we say, downwards, for as long as it's gravity, as long as it's free fall. So it's 9.8. I'm sorry guys, it's 9.8 meters per second squared. So now what about the units? Then 4.2, calculate the magnitude of velocity with which the ball was kicked. So we're looking for the initial velocity. What do we have in question? We know that this is 0.6 above, so which means the ball is going to travel 21 meters from where it was kicked. Okay, and it takes 3, where the ball hits the roof of the building 3.1 seconds after it was. Okay, so I'm gonna look at the 21 from there up to there and then see. So if I look at my downward motion as positive, I can use delta y is equal to vi times delta t. Can use a half a delta t squared. Why? Because the question is asking for initial velocity, which is the vi. Only thing we have is the time and the displacement. Okay, so my displacement is gonna be the 21, which is negative. Initial velocity, I don't know. My time was 3.1, and then a half. My A is gonna be 9.8. Oh, why am I doing that? It's okay. And then the T is 3.1 squared. I'm using negative 21 because I'm taking the downward motion to be positive, which means my displacement when it moves up will be negative. I am not necessarily focusing on the G. Okay, when I do the substitution of all of this, I have a half times 9.8 times 3.1 squared. That's gonna give me 470. Okay, no, not 470, sorry. It's 9.8, it's 47. So the whole of this is giving me 47,089. And then I must move it that side. So say plus 21, which is like a 68,089. And then when I divide this by 3.1, I'm getting 21. So initial velocity is 21,96. meters per second, or any other acceptable option or equation can be used. And then calculate the maximum height that the ball reaches above the ground. Now, since the initial velocity that we're focusing on is 21.96 meters per second, they want us to get the maximum height, and we said at the maximum height the final velocity must be 0. We're looking for delta y. Okay, so we can use v squared, v final squared is equal to vi squared plus 2a delta y. Our v final, that is a 0, is equal to, I'm going to say 21.96 squared plus 2 times our a, which is 9.8. I'm going to call it negative because I'm taking gravity to be downwards. Okay, now I move it that side, it's going to be 19.6y. What is 21.96 squared? Getting 482.2416, then divide by 19.6, divide by 19.6. That cancels out, and then my y becomes 24.60 meters. So this is the maximum height that the ball is gonna reach. And then 4.4, being asked is referring to the sketch. Refer to the sketch and state whether the collision of the ball on the roof is elastic or inelastic. So since the ball reached the maximum height, it bounced off. Okay, so wait a moment. Is that question done? Calculate the maximum height that the ball reaches above the ground. Above the ground. We're not done. This 24 is, so remember, the ball was kicked from a height of 0.6. So which means we have to add the 0.6 also. Sorry. Plus the 0.6. Then that becomes 25.2 meters. Thank you. Then 4.4, we were saying the ball is gonna reach the maximum height and then it drops to the roof, just one bounce, and then it comes to rest. So is it elastic or inelastic? So I'm gonna say it's inelastic. The reason being, from the maximum height, the ball bounces, but the bounce just reaches a height that is lower than the maximum and then gets to rest. So we can say that the ball just does the bouncing. Ball bounces lower than the maximum height before. Lower than the maximum height that was reached. So I did mean that the ball decided to bounce higher, then it was gonna be elastic. Okay, and then 4.5, they want us to sketch position. Remember I said position is a curve. Okay, position is measured in meters, and then time is measured in seconds. Okay, position time graph for the complete motion of the ball from the moment it was kicked until it comes to rest. Okay, so if I'm to look at it, remember the ball is gonna reach the maximum, we say 21. So if it says 21, okay, we have 21, and then which other height do we have? Okay, 4,2 minus 24,6 minus 21, which is 3,6, which means the height of the bounce is 3,6. So in other words, it went up. This is gonna be like 21, and then there's an extra 3,6 for it to reach the maximum where the velocity is 0. So I'm gonna take this to be my 21 negative. Okay, and then to just move, it reaches a maximum height of how many meters? 3,6, because we say 24,6 minus the 21, which is 3,6. Okay, and then it bounces off. They told us the bounce takes place at a time of 3,1 seconds. Okay, and then it takes also another bounce. Do we know that time for the next bounce? We don't know it, but it does before it comes to rest. So what we need is the initial starting point, the maximum point it reached, and then that other point. Okay guys, so that is question number 4. Question number 5. Question number 5, I think I'll have to stop at a question below what I'd prepared. So this is more or less still the same, but it's okay, we can look at it. They're telling us that Sandile, who is standing on a platform, throws a small metal ball vertically downwards, vertically up from the height of 1,73 above the ground. So this is 1,73 up. Okay. At this velocity, the ball travels past the top of the building and returns to the hand, who is still at that same height. Ignore the effects of friction, sandy delay somewhere here. So with what speed does the ball strike Sandile's hand? So the ball was projected at 8. So since Sandile is still just at the same point, we're gonna say it's 8 meters per second. Nothing changes. Since we are ignoring friction, it's just gravity that is doing the work. Okay, using the equation of motion and not energy principles, calculate the maximum height that the ball reaches above the ground. So Vf is gonna be 0. V initial, we have it as 8. A, which is G, is 9,8, and then the height is what we're looking for. So I'm gonna say Vf squared is equal to Vi squared plus 2 times acceleration delta y. Then we say that maximum height velocity must be a 0. 0 squared, initially it's 8, and then since I'm projecting it upwards, it's gonna be negative 9,8 times the y. So 2 times 9,8, that's 19.6. So I'm gonna transpose it that side. So 19,6y is equal to 8 squared, which is a 64. Then I divide by 19,6. Okay, 64 divided by 19,6, I'm getting 3,27. 3,27 meters. That is from the point of projection. Okay, from here or from wherever Sunday is up to there. But now from the ground, since the question is talking about the ground, which means I'll have to add the 1,73 meters, which will make it, I don't know guys, help me, 1.73, which is 4,9995, which is, around it off, is just gonna be 5 meters above the ground. 5 meters above the ground, 5 meters above the ground. Okay. And then 5.3. So if a window on top of the building, on the top floor of the building is at 2,5 meters, calculate the time it's gonna take for the ball from the moment it was thrown to pass the top of the window on its return. So this is a quadratic, guys, a quadratic time it takes to pass the window. Okay, let's see. So we must be able to get at least two values if possible. So we can start by doing what? We need to get the final velocity first of all, because in this case we're not focusing on the maximum height. We just want the velocity after the 2,5 meters of distance traveled by the ball. So that's going to be 8 squared plus 2 times 9,8 negative times the 2,5, because that is the distance from Sandley's hand to the window. Okay, when you sort this out, 8 squared plus 2 times negative 9,8 times 2,5 followed. What's going on? I'm getting 15 and square root of 15, so this is 15, and then square root of 15 is 3,873 meters per second. Okay, this is like our final velocity. And then if I use Vf is equal to Vi plus 80 or a delta t. Our V final, we have it 3,873. It's going to be negative. And then our initial velocity was 8. Our acceleration is negative 9,8 times a certain time. Okay, so when I move the 8 that side, it's gonna be minus 8, which is, I messed it, 3,873 plus 8, that's 11,873. Negative is equal to negative 9,8. We now divide by 9,8 over 9,8. That cancels. What do we have? Getting 1,21 seconds. So they say every the time taken for the ball from the moment it was thrown to pass the top of the window on its return to Sandley's hands. So I'm getting 1,21 seconds. Okay, the reason as to why I'm using the 2,5 is because that top part is gonna cancel out to be 0 in terms of the displacement. Okay, since this part is gonna be the positive displacement and then this negative displacement is gonna cancel it out. That's why we're gonna just stay with the 2,5 meters. Then 5.4, taking upward direction as positive. Draw sketch of position, time again. Guys, we said position is a curve taking upward as positive. Time is in seconds. Okay, so if we take our position in that sort of format, what do they want exactly? They want us to draw the ball's motion from the moment it left Sandy's hand until it lands back into his hands. Oops, okay. That is 0. That's pretty easy. Something like that. So what is the maximum height that, or the maximum position that we got? Somebody help us. It was 3,27. 3,27. So just indicate this. 3,27. Is there time that is needed? How long did it take? Do we know that? Is the window calculator time taken? And that is for the window. Nothing. So we can just leave it like that. So for as long as we have the correct 3,27, as long as the shape graph starts from 0, because that's our displacement, the ball was not moving at that point. As long as the shape is correct, and then we label this correctly with the correct units, then we're good to go. Question number 6. I don't know. I feel like we should skip this, or I don't know. Skip it, do it, skip it, do it. It's fine. Let's attempt it and see. So the ball is thrown vertically upwards at the velocity of 4 meters per second. 4 meters per second from the roof of a building with a height of 10 meters. And then the ball strikes the ground and rebounces to a height of 3 meters. Okay. Okay guys, let me work this out, but if the next question is more like the same, I'm gonna skip it, so that we look at just a different sort of scenario. Okay, so they want us to get the time taken for the ball to reach the maximum height. So we said maximum height, final velocity is 0. So our initial velocity is 4 meters per second. Okay, the ball strikes and rebounds to a height of 3 meters. So this is pretty quick. We can say Vf is Vi plus A delta T. Our V final is a 0. Our initial is 4. Since we're throwing the ball upwards, it's going to be negative 9,8 times T. Move the further side, which is 9,84. So 9,8 T is equal to 4. And then divide both sides by 9,8. 4 divided by 9,8. I'm going to get 0,41 seconds. Let's round that off. And then they want us to get the maximum height that the ball reaches. So the maximum height, we need to get an equation that involves displacement. So I can use what just happened? Okay. So I'm saying I can use my delta y is equal to Vi delta T plus a half A delta T squared. I want the height. Do I have the time? Yes, the 0,4. Acceleration, I have it. So it's going to be 4 times 0,41 plus a half times negative 9,8 times 0,41 squared. I hope that makes sense. 0,4 plus 0,5 times negative 9,8 times 0,41 squared. I'm getting 0, is that true? Let me just redo it again. 4 times 0,41 plus a half times negative 9,8 times 0,41 squared. Okay, I'm getting 0.82 meters. Okay, so that is our maximum height. And then they are telling us that the ball strikes the ground 1.09 seconds after it was thrown and remains in contact for 0.2 before bouncing off. We need position versus time. Use the ground as a reference and indicate the following. So when they say indicate the following, this is what they're going to mark. Okay. So this is position in M. I'll say this is my time in seconds. So if that is a 0, that is a 0. At what point did the projection start? This ball was projected from 10 meters. So which means our story must start from a height of 10. Okay. So we're saying, I don't know, let me just throw something small. That's a 10. And then this ball is gonna move up to the maximum. What do we get as our maximum height, guys? It was 0.82. So 10 plus 0.82, that's gonna be 10.82. And then this moves. Okay. It hits rock bottom. They are telling us it spends some time. So at what time does it hit the ground? Strikes the ground at this. So this is 1.09. Okay. It stays on ground for 0.2. So 1.09 plus 0.2 is gonna be 1.29. Okay. And then it just bounces off. To a height, did they give us that height within the question? Yes, to a height of 3, which means this graph must stop at 3. So this must be at 3. It's just that. As long as you represent the height from which it was thrown, it's a mark. Maximum height reached is a mark. The height reached by the ball after bouncing the 3 meters, so it's a mark. And then the time it takes to strike the ground, it's a mark. Contact time, it's a mark, because the difference between that would be your 0.2 seconds. Okay guys, that is question number 6. Question 7. Okay, this is interesting. This is interesting. Telling us that ball A thrown vertically upwards from the top of the building, that is 8 meters high, at the velocity of this at the same instant, that is another identical ball that is thrown upwards. So this goes down and then this one goes up. Okay, it's thrown at the same kind of thing. So I'm gonna just summarize this and say ball A and then ball B. The height, initial velocity, say VI for both balls, telling us A is at 12. At the same instant, B is thrown upwards with a velocity of 30. A and B pass each other after time. So they will be equal to, or the distance traveled will be equal after this amount of time. Then give the direction and the acceleration of B while moving upwards. So one thing we say is they want the direction. We said direction of the acceleration. Acceleration will always act downwards. Okay. Then they want us to calculate the velocity of B, ball B, the moment it passes ball A. The velocity that A or B passes A. Okay, so I need to get the final velocity first of all. final velocity that P is gonna be traveling with. So I'm gonna say V initial plus A times the delta T. Okay, so my initial was 12. Said calculate the velocity of P. Guys, I'm sorry now. We're looking at ball B, which is 30 not 12, plus the 9,8, which is gonna be negative. And then what distance is traveled? We said ball A and B pass each other after 2,13. So I'm gonna multiply that by 2,13 because I know they're gonna meet or they're gonna pass each other after 2,13 seconds. Then I'll do my substitution into the calculator. 3 plus negative 9,8 times 2,135, which is 9,077, which can be rounded off to 9,08 meters per second. Which direction? It's moving upwards. Okay. Then I'll calculate the distance between A and B. 2,5 seconds after it was projected. Okay. So I'm gonna use delta y is equal to VI delta t plus a half A delta t squared. Since they're asking us for distance, we know the VI, we know the t's. Okay, they gave us the t as 2,5. Acceleration, we know it. Okay, so I'm gonna look at probably both balls and see what's going on. There's ball A and then there's ball B. So if I focus on A, my displacement is gonna be our initial velocity was at 12, and the time that we're looking at is 2,5 seconds. And then plus, remember ball A was being thrown downwards, so the 9,8 is gonna be looked at as positive, and then times 2,5 squared. Okay, 12 times 2,5 plus 0,5 times 9,8 times 2,5 squared. That is giving me 60,625 meters. So that is how far ball A would have traveled. And then when I look at ball B, okay, if I look at ball B, let me say what is 80 minus 60,65, which is 19, something. Oh, that makes sense. Calculate the distance between A and B. After this kind of time, let me just dissect this. So this would have traveled that much, which is 60,6 something. So what is left is 19,375. Okay, now I'll visit that again. Let me look at B. When I look at B and use the same kind of approach, it's gonna be my 30 times 2,5 plus a half times negative 9,8 times 2,5 squared. Okay, same 30 times 2,5 plus a half times Negative 9,8 times 2,5 squared. That gives me 44,375 meters. So this is above the ground. That is above the ground. Okay. Let me just do this. Okay, so I'm gonna look at B. So if B has traveled 44,375 from the ground, and we are saying A traveled as far as the 60, something and reached here, and what is left below the ground, we said it's 19,375. If I get my 80 minus the 60,625 to get what is left at the ground, so that for me to get what is shorting, I'll focus on the 19, something and this 44. I subtract the two to get the distance between. So 44,375 minus the 19,375, and then I get 25 meters. So it's just 25 meters between the two balls. Okay, then they want position time. Oh Lord, these people have position time. So this is position in meters, and then we're saying this is the time in seconds. Okay, so we have two balls, remember. One ball is starting from 0, another ball is starting from a certain height, which is 80. So this ball is gonna move in this sort of direction. Okay, I'm gonna use a different color for other balls. So which ball started from 0? It's ball B. I'll label this as a B. And then A started from somewhere there, and then it's gonna hit the ground. So we're saying at this point, when they pass each other, we were told that time is 2,135. 2,135 seconds. Okay. So for as long as we have this position in meters or displacement delta y in meters, time in seconds, and all of that, then we're good to go. Then question number 8. We've seen this, guys. We have seen this. I don't know. I'll beg to skip it. Should I, guys? Yes, I think I'm gonna skip it because it just looks the same. When you look at our first question, when you look at the second question also, it's just the same sort of approach. So I'm not gonna do that. Let me just go to question 9 and wind up. Okay, so we're saying question number 9. Ask is question 8. Next time. Okay, question 9. They're telling us there is a girl that stands on a platform in a classroom. She throws a ball vertically upwards to the floor, hoping that the ball, after it bounced on the ceiling, will hit the ceiling. What's going on? A girl stands on a platform in a classroom. She throws a ball vertically upwards to the floor. Okay, so this girl is standing somewhere here. Around Soskis, I don't know how to draw girls. Okay, she throws the ball to the ground, hoping that the ball, after it had bounced from the floor, it would hit the ceiling. Okay, then it's making sense. So she throws the ball with the speed of this. So our initial velocity is 8 meters per second, the height from above the floor. Okay, so that is the platform. Okay, we need to ignore the air friction, air resistance. Then they want us to write down the magnitude and direction of acceleration of the ball immediately after it left the hand. So acceleration, guys, it's a giveaway, this one. Direction, downwards. Acceleration, downwards, it's a must. The 9.2 is the motion of the ball while it's moving downwards towards the floor. Is it free fall? Yes or no? The answer is a yes. Since we are ignoring the effects of air friction and this ball is just falling under the influence of gravity. So we are saying only gravity. It's only gravity that is acting on the ball. Only gravity acts on the ball. Or we can look at the influence of gravity on the ball, or the ball is moving under the influence of G. The 9.3, they want us to get the magnitude of the velocity with which the ball hits the ground. So magnitude with which the ball hits the ground, they want us to get the VF, final velocity. We said our initial was 8. Initial velocity was 8. G is 9,8. Do we have the time it takes? Anything? They only gave us the height, which means the displacement is, excuse guys, displacement is 1,8 meters. So we can use the VF squared. Yeah, VF squared is equal to VI squared plus 2A delta Y. We're looking for VF. Okay, so our VI is 8 squared plus 2. Since the ball is dropped down, so it's gonna be positive 9,8, and then the height is 1,8. So 8 squared plus 2 times 9,8 times 1,8. That gives me 9 to 9. So VF squared is 99,28. Then I must find the square root. So square root of my answer is 9,96. Okay, 96 meters per second. So that is the final velocity when the ball strikes the ground. Okay, then 9.4, how long does it take the ball to hit the floor? So we're looking for the delta t. Since we have our VF, we can even use that first equation. The VF is equal to VI plus the A delta t. I feel that is way quicker. It's VI plus A times delta t. So our VF, we said it's 9,96, is equal to the initial velocity, which we said was 8, plus our acceleration, which is 9,8 t. Positive since the ball is being dropped. Move the 8 that side. 9.96 minus 8 is going to be 1,96. 1,96 then divided by 9,8. So which means t is 2 seconds. Is it 2? Wait, 1,96 divided by 9,8 is 0,2. 0,2 seconds. Okay, and then the ball bounces inelastically on the floor. This simply means it's just gonna bounce off below the height of projection. So it bounces off inelastically on the floor where the speed of the ball decreases by 20%. And then the ball is in contact with the floor for 0,01 seconds. And they want us to determine by means of calculation whether the ball will reach the ceiling after it bounced off. So inelastically simply means the height kind of decreased compared to what was expected. Now, since they gave us 20%, they are telling us that it decreases by 20%. So someone can find 20 of the final velocity, which we got as 9,96, and then you subtract 9,96 minus this 20 over that. So it's 9,96 minus 0,2 times 9,96. I'm getting 7,97. Okay, that is 7,97. So this is gonna be the new velocity. Okay, they want us to determine whether it will reach the ceiling. Remember, our ceiling is at which height? 3,5 meters. So we need to find the displacement and see if our displacement is going to be 3,5. Okay, so if we get Vf squared is equal to Vi squared plus 2 times A. Oh God, so I think I'm tired now. I said A delta Y. Okay, we're looking for the displacement. We have the acceleration, we have the initial, we have the final. Yes. So we're looking for the maximum height that the ball is going to reach. And the maximum height, we said velocity will be 0. So 0 is the same as 7,97 squared. Now someone will ask, why are we using this? Remember, as the ball hits the ground, it spends some time there, the velocity decreases, and then the velocity with which it leaves, the velocity with which it bounces off. So let's say there was no 0,01 seconds. Then the velocity with which it hits the ground would be more or less literally the velocity with which it leaves. So in as much as it was the final velocity for the first journey, it's going to be the initial velocity for the next journey of the bounce. Okay, 2 times 9,8 delta y, it's negative since it's moving up. Okay, when I simplify that, 7,97 squared, I'm getting 63,521 minus 19,6 y is equal to 0. Move it that side, 19,6 y, then divide both sides by 19,6. Okay, and then our y is going to be divided by 19,6. I'm getting 3,24 meters here. Okay, so since the maximum height I'm getting is 3,24, and they told us that the maximum height out to the ceiling is 3,5, which means this ball is not going to reach the ceiling. Okay, so determine by means of question whether the ball will reach the ceiling. So the answer is nope, the ball ain't going to reach the ceiling. The ball won't reach the ceiling. Will not reach the ceiling with the target point. Alright, that is 9.5. And then 9.6, lastly, they want us to sketch a velocity time graph. Your first colleagues, this is velocity in meters per second. And then we're saying this is time measured in seconds. So if we look at velocity, remember we said velocity time graphs are basically straight lines. Now at what velocity did the journey start? So it started with 8 because that was the initial velocity. We worked out our final and we got 9.96. Yes, 9697. It's 96. Use a different color. Okay, so this is 9.96. Sorry if my rounding off was poor. And then at what time was that? After how many seconds? It was 0.2 seconds. It was 0.2 seconds. We found it. Let's see. Okay. And then from this point, what happens next? There is a 9.97 when it is doing the bouncing off. So I'm gonna put it 9.97. So which means this is also 7. Okay, when it is bouncing off. So I'm just gonna have this line to that point. And then I'm gonna have, they said it takes 0.01. So this is gonna be 0.21 seconds. So which means my line must pass the middle point, and this must correspond to this 9, something, and then it reaches 0, since it's gonna reach the maximum point of the 3.24. So straight line, then straight line. Okay, and then lastly, question number 10. Telling us a boy throws a ball vertically into air from the top of a building, and then the ball strikes the ground after 4.08. The velocity time graph has been drawn for the entire motion. Ignore the effects of friction. Okay, there is our definition question. What is a projectile? You said projectile was any body that was under the influence of acceleration with gravity. So a body, or we can say an object. An object that is acted upon by only acceleration due to gravity. Acceleration due to gravity. That's the only force. I'm sorry guys, my English, my repetition things. So an object that is acted upon by acceleration due to gravity, strictly acceleration due to gravity, is a projectile. Then what is the acceleration of the ball at 1.02 seconds? Remember, this is a velocity time graph. Okay, and for us to get acceleration is change in velocity over the change in time. You can use those formulas, equations of motion, but there is no need for that. Okay, so if you look at the change in velocity over the change in times, is 9.8 divided by 1.02, getting 9.61 downwards. Okay, that is if I'm to use the graph. Okay, acceleration of the ball at this time. So it's a two-way thing. Since we said an object acted upon by only acceleration due to gravity is a projectile, and this thing is just showing us the velocity time graph, and then they ask us for the acceleration, which means someone can say it's 9.8 meters per second squared downwards. But if we are to use the figures on the graph, change in velocity is going to be 9.8 over the 1.02. How are we getting the 9.8? Remember, we're getting the change, the gradient, change in v over the change in t. So that is what is giving me the 9.6. So it's fine, whichever option you go for, it's correct. So this 9.6 is taking into impact or into effect the values or the effects of frictional force. That's why it is even smaller. And then 10.3, they want us to get the displacement of the ball. So with the displacement, they want the delta y. Okay, we know that delta t is 4.08. Okay, so I'll say delta y is the same as vi delta t plus a half a delta t squared. Our initial velocity was it 0? No, it was 9.8. The starting velocity was 9.8. So that's 9.8, and then the time that we're focusing on is 4.08 plus a half. What is happening to the object is thrown into from the top. So I'm gonna take it to be negative. And then the time is still 4.08 squared. So when I punch that into the calculator, 9.8 on that, I'm getting 41.58 negative. So which means the displacement is downwards, 41.58 meters downwards. Then they want you to sketch the position time, and those are the things to look out for. So I'll say y in meters, and then this is the time in seconds. So number one, where did the graph start from, or where did the object? So that is the 0. And what time did it reach 0? At what time was the velocity 0? It's after 1.02. So 1.02, the displacement was 0, or the velocity was 0, so that's the maximum displacement. And since it's more like a parabola, twice that is going to be 2.04. Means the graph must also pass through that point. Then we need the time of 4.08, which is twice that. So it's gonna be, so this is the maximum height. And displacement is 0 at that time. Then this graph continues. Yo guys, I'm horrible at drawing. Let's do this. Okay, thank you. Something like that. So this position here, this displacement is what we just calculated in the previous question at a time of 4.08. Our displacement was 41.5 something. 41.58. 41,58. Okay, so 41,58 meters. So guys, for as long as you just show us the t values and the direction and everything, then we shall be good to go. And then other thing is about someone asked now, how about the acceleration time graph? How do they look like? So acceleration is not that hard. I'll just give you guys move. Raising is not working. Okay, so if we have an acceleration time graph, it's just let's okay. So that will be acceleration, and then this will be the time. So it's usually just straight lines. So this is an acceleration time graph, depending on which acceleration you're taking to be positive. So this will be 9,8. So it's just uniform since it never changes. Sometimes it can be drawn like this and then like that, depending on how the object is moving. Okay, guys, I think that's enough for the day. What we haven't looked at, probably in the next episode. Let's meet. Hello and welcome to this episode of Physics. Before we go into details, we need to know that electrostatics is just a branch of science. Okay, branch of science that deals with the study, of charges or charged particles. Okay, so from this branch of science, we know that like charges that are having the same charges that are the same. Positive and positive, or negative and negative, those charges will repel. And then the unlike charges will attract each other. Okay? Like charges will attract each other. So this we need to know. Now, what if we have charges that are at rest? Okay, so if we have charges at rest, then there is a force that will be acting between those two charges. It can either be a force of attraction or a force of repulsion. So for charges at rest, we know that the force between them is what's called the electrostatic force. Electrostatic force. So what does this force do between the charges? So one thing we need to know and remember is that there's a German scientist known by the names of Coulomb that did a thorough study. What really happens when two charges are at rest and what sort of force works between them and what the relationship of force is, the charges and the distance between the charges themselves. So upon his conclusion, he said that this force is directly proportional to the magnitude of the charges, the P.1 times product of magnitude of the charges, not forces, and then it is inversely proportional to the square of the distance of separation. So it's just more like related with the universal law of gravitation for Newton, whereby you look at the force being directly proportional to the masses and inversely proportional to the distance of separation. But in this case, we're focusing on the charges. So if the proportionality symbol was to be eliminated, then K will have to be introduced, whereby F is representing the force, that is the distance of separation. These are the charges, and then K is what we call electrostatic constant. Okay, the constant of electrostatics, which is the same as 9 times 10 to the positive 9. Constant that we need to remember. So for any given two charges at a time, this formula will be used. So this formula brings about what we call Coulomb's law. Coulomb's law of electrostatics. Okay, so what does that law state? We are saying that the magnitude of the electrostatic force is the magnitude of the electrostatic force. Magnitude of the electrostatic force in between 2-point charges. Between 2-point charges is directly proportional. Directly proportional. The product, okay, of the charges, or magnitude of the charges, magnitude of the charges, and inversely proportional. Inversely proportional, the square of the distance between them. So the square of the distance between the charges. Sometimes we even talk about the centers. Okay, so that is what the formula says. Force is directly proportional to P1 times Q2 over R squared. So that is Coulomb's law. We just need to know how we state that. So it's saying it's just similar to the universal, where there is a G, and in this case, we just have K. Now, what if we have, let's say, we have an example. We have this as our sphere number 1, I'll call it A. And then this is sphere number 2, I'll name it as a B. And then let's say we have distance from the centers, I'll just say 15 millimeters. Okay? Just for convenience, what if I use this as a 6 MC? And then I can use this as a 12 micro with a C. Okay? And then I need to get the force, the electrostatic force between the two. So both of them are positives, it's fine. I have no problem with that. So we know that our Q1, let me call this Q1, and then let me label this as the Q2. So if that's the case, so this N usually represents what we call nano. And nano is times 10 to the negative 9. So the overall charge is going to be 6 times 2 to the negative 9. And then this symbol mu represents micro in electrostatics times 10 to the negative 6. So the charge here is 12 times 10 to the negative 6 coulombs. This distance needs to be converted to the standard unit in meters. So my force, if I use that formula, is going to be K, which is 9 times 10 to the 9. And then I'm multiplying by 6 times 10 to the negative 9. And then I'm multiplying by 12 times 10 to the negative 6. And then I'm dividing it by the distance. We said it was 15 millimeters. When you're changing or converting millimeters to meters, you usually divide by 1,000. Okay, so you can do that, or you can multiply by 10 to the negative 3. whichever one is easier. That's going to be 0,015. Then I'll square that. Okay, so when I put that into the calculator, times 2 to the -6, and then I'm dividing by 0,015 squared. That becomes just 4,13 joules. Okay, so that is the force that is existing between the two. Now, one thing we need to know is that that force is what A is having on B, and then it's the same force that B is having on A. In other words, it's more like Newton's law, Newton number 3. As in opposite and reaction will be equal, but opposite. So the force that A impacts on A impacts on B is the same as that B impacts on A in the opposite direction. So since the charges are the same, which means it's going to be repulsion that takes place. Okay, that is just a simple scenario. Now, what if we have, let's say, 3 bodies? Okay, something like this. And then maybe we're given a distance of 12, maybe you're given a distance of 16 with different charges. I call this A, B, and then C. Let me call this 8 microcoulombs. I'll call this 9 microcoulombs. And then maybe 16 microcoulombs. For this internal problem. Now, if it is 3 charges, what we normally look at is you might be asked for the net electrostatic force. Okay, net electrostatic force of, let's say, A, net electrostatic force on A as a result of B and then C. The net electrostatic force on A as a result of B and then C. Or we can say the net electrostatic force on B as a result of A and C. So in most cases, it's all about combining the two charges. Let me see how we can do this very fast. Okay, so since I'm looking for the net electrostatic force on A due to B and C, step number 1, I need to get the force between A and B. Okay, so force A and B, remember we said QA times QB over the RAB squared. So when I do my substitution, that is 9 times 10 to the 9, and then times 8, we said micro is 10 to the -6. And then this is 9 times 10 to the -6. Distance of separation is 12 centimeters, which will be 0,12 squared. And I convert that to meters. So that's a 9 times 8 times 9 times 10. I'm gonna put that negative, okay. And then we're saying this is 0,12 squared. Okay, so this gives me just 45 Newton. Okay. Now that is the force on A as a result of B. So since the charges are opposite, then there's going to be a charge. So it's moving to the left. Okay, then I need to find also the force between A and C. The force between A and C. So the formula, that is QA QC over RAC squared. So 9 times 10 to the 9, that is 10 to the -6. Then 10 times 10, that's gonna be to the negative 6. Now the distance we have in 12 and then 16. Okay, so 12 plus 16, that is 28. That's 0.28, but squared. When I put that into my machine, 9 times 8 times 60, okay, then I'm dividing by 0.28 squared. I'm having 16.53. Yeah, Newton. Now, since the charges are the same, this is a positive and then this is also a positive, there's going to be repulsion. So that force is going to act to the right. Okay, so that is the right. Now, for me to get the net, I must get the F of AB plus the F of AC. I do the substitution. So if my left is a negative, then I'm going to have negative of 45 Newton plus 16.5. So negative of 45 plus 16.53, ending up with 28.47 Newtons to the left. Okay, so that will be the net electrostatic force if, let's say, I have 3 point charges. Then what if the point charges are just at an angle? Okay, an angle of, let's say, 90 degrees. Okay, let's say I have A here. Let's say I have another charge B, and then I have another charge that is C. Let's call the distance here, I don't know, let me call it a 2 meter. I'll call this a 3 meter, just to make it a bit easy. So I'm going to call this negative 3 nanocoulomb. I'll call this a positive 4 nanocoulomb, and then I'll call this positive 6 nanocoulomb. Okay? Now, if this is the case, and then they ask us to determine the net electrostatic force. Okay? Net electrostatic force on B, G2A and C. Okay, the net force on B as a result of A and C. Now, this represents what we call the 2D kind of electrostatics, whereby we have the horizontal as well as the vertical dimensions involved. So what we need to find the force that is acting within the vertical as well as the force that is within the horizontal. So this is F vertical, and then this is going to be F horizontal. So the net force for both needs to be found. So I'm going to get the force vertical. Remember I said AQA, QB over R squared. Force on B as a result of A. So if our A was a negative 3, that is 10 to the 9 times, we're saying 3 times 10 to the negative 9 because of the A. And then we are multiplying by 4 times 10 to the negative 9. Distance of separation is 2. I'll just square that. Okay. When I punch that into my calculator, having 9 times 3 times 4. Okay. Over that. This means 7 times 10 to the negative 9. That is Newtons. But since the charges are opposite, there's going to be repulsion. So this is going to act downwards. And then let's look at the force horizontal. With the horizontal force, I'll be looking at K QB times QC over R squared, 9 times 10 to the 9 times 4 times 10 to the negative 9 times 6 times 10 to the negative 9. I'm dividing it by 2 squared. Okay, so this is going to give me 24 times 10 to the negative 9. Now, since the charges are the same, it's going to be power. So that is to the right. Is it to the left or to the right? Does it matter? It does. To the left and to the right. So that's going to be, remember, let's go back. Let's just go back a bit. Remember, there's going to be attraction. Force is up, it's acting downwards. So this is going to be up. Okay? And then this is going to be to the left. This force is inverse. Just focusing on B alone. Okay. Then now, if we look at the forces, so it's going to be something like this. Force vertical and then the force horizontal. So this is a 27 times 10 to the negative 9. We're saying this is 24 times 10 to the negative 9. We need to find our resultant. Okay. For us to find the resultant, we use the theorem of Pythagoras. R squared is equal to x squared plus y squared. F horizontal squared plus F vertical squared is equal to our F resultant squared. So 27 times 10 to the negative 9 squared plus 24 times 10 to the negative 9 but squared. So I'm going to find square root so that I have my F resultant. Okay, I need brackets here. Is 10 to the negative 9. And then I'll square it with 10 plus 10 for brackets times 10 to the negative 9, but also squared. Okay, I'm having a very small number. It is 1, 2, 3, 4, 5, 6, 7. So 3,612 times 10 to the negative 8 meters. So that is the net electrostatic. Now we also need to find the direction. So with the direction, you need to use the fig where we look at the angle of inclination, which is the arctan of the F vertical over the F horizontal. Okay, shift tan. Our vertical was 27 times 10 to the negative 9 over 24 times 10 to the negative 9. If I put this into my machine, I'm going to have, what am I having? 8,37 or 37 degrees. So that will represent our angle, and then that is our magnitude. Alright, so that is if we are being asked to determine the electrostatic force or the net electric force. Then I just want us to look at what we call the electric field. Okay, so electric field is basically a region of space. A region of space where a charged body, sometimes it's a charged body, will experience force. At times we say it's a region of space in which an electric charge experiences a force. So the direction direction of the field at a point in space is the direction in which a positive one charge would move if it was placed. So direction that this force will be operating on that object is just the direction that a positive one charge would take if it was placed within that region of space. Then we also have what we have electric field point. Okay, maybe let us try that also. Electric field, the point where we say if the force per unit positive charge is placed at the point. The force per unit positive charge placed at that point. We shall go in details when we look at some examples. Then we also need to remember how to represent, let's say, the electric fields. An example, if you're looking at an isolated positively charged sphere. So we know that the field lines must be moved out of the sphere. So we normally use arrows in that sort of manner. What if it's negatively charged? Then the field lines should be seen just entering into the sphere. Okay. Now what if we have, let's say, two charged bodies? Remember we said positive and positive, there will be a repulsion. Okay. Now the technique with drawing this, the repulsion, we shall have, and then the field lines must not cross each other. Field lines must never cross path of each other. Must go in. So since they are positive, then the field lines seem just leaving. Same story here. Then the magnitude sometimes will also determine how many field lines leave the sphere or enter into the sphere. Sphere with a bigger magnitude will have more field lines. Those with smaller magnitude will see few field lines. And then if it's negative and negative, so still it's going to be repulsion. Yeah. You must touch the sphere. As long as we see the correct pattern and correct format of the field line. So the arrows should be seen entering into the sphere for as long as they are negatively charged. Now this region of space, there will be no force for, because the net force there is zero. So sometimes, let's say if you're talking about the electric field, sometimes you can put a positive Q here or a negative Q there, and then see what will happen. Then what if the charges are opposite? That's when we say it, we shall look at the attraction. A positively charged or negatively charged, we should be able to see field lines that are leaving positive spheres and moving into negatively charged sphere. Leaving something like that. Doesn't matter how it looks like, as long as we see field lines leaving the positive and getting into the negatively charged. Now the formula for electric field. The formula for electric field, we know, must be given as E is equal to F over Q, where E is the electric field, and then F will be that force at that point, and then Q will be the charge, magnitude charge. Now, if let's say we were to focus on the electrostatic force between the electrostatic force between, let's say, the big Q and then the small positive Q. From the Coulomb's law, we know that that would be K times Q, then times a small q over the distance of separation. So if we do the substitution, it's going to be K, Q, that Q over R squared times Q. So this is going to cancel that out, and that leads us to this other formula which we normally use, is equal to KQ over R squared. So remember, the force due to the test charge, then due to the test charge. So that we need to remember as well. Then if let's say we want that force, we can just cross multiply that, so that we get times the magnitude of that charge. Then one other thing that I can probably say is that whenever we have, let's say, the net electrostatic force or the net electric field being zero, simply means the charges must be opposite, or the electric field have to be opposite in direction. Okay, guys, that's a brief sort of start. Then let me just look at the examination guideline. So with the examination guideline, what is expected of us? Number one, we need to know how to state Coulomb's law, that the magnitude of electrostatic force exerted by one point charge on another is directly proportional to the magnitudes of the charges and inversely proportional to the distance between them. To be able to solve problems using this equation, this Coulomb's law, that is for 1D, where the charges are placed in a single line. And then solve problems with a 2D, where we have a 90-degree somewhere, somehow. And then we show, when we look at, let's say, the electric field, we need to be able to describe an electric field as a region of space in which an electric charge experiences force. The direction of the field at a point, the direction at a positive one charge. Okay, we need to be able to draw the field patterns for a single point charge. What if there are 2 point charges? What if they are charged spheres? Then we need to define electric field at a point being the electrostatic force experienced per unit positive charge placed at that point. We saw that. And then we should be able to use this formula, the E is equal to F over Q. Then solve problems with that formula, then calculate the electric field at a point, the number of charges, and so on and so forth. Okay. So this is the examination guideline, and that is what exactly is expected of us. Then we need to look at some worked examples, so exam type questions. This is okay. Question number 1. I can start from question number 1. All right. So question number 1 is telling us if we have 2 spheres, M and N. 2 spheres, M and N, on insulated tank M with a charge of -4 nanocoulomb, that is placed 30 millimeters away from from A. Is a point that is K, and so on and so forth. Then they are telling us that the net, in capital letters, the net electric field strength is acting east. So we don't know the magnitude of N, we only have E. So the innet is 2 times 10 to the 5. This distance needs to be converted to meters. Okay. You know that that's negative 4 times 10 to the negative 9 coulombs. All right, let's see. So define the term electric field point. So we say this is the force that is experienced, okay, but per unit positive charge. Per unit positive charge placed at that point. Placed at point or placed at that point. Okay, that is if they ask you to define electric field at a point. That would be it. Then calculate the magnitude and direction of the electric field at P as a result of electric field at P as a result of so electric field between P and M. So from our formula, we said E is equal to KQ over R squared. We know that K is 9 times 10 to the 9. Charge, we said it was negative 4, but we don't need the negative sign. Just magnitude, that's 4 times 10 to the negative 9. And then the distance of separation is 15 millimeters. Convert that to meters. So that's going to be 0,015 squared. Okay, when I put that into the machine, I'm getting 0.15 squared. I'm getting 1,000. Okay, 1,000 Newton per coulomb. Now, which direction is it? So, they want the electric field at P, the result of P. So since we're taking this to be a positive one, and then there's a negative, there's going to be attraction. Okay, so the force at P is moving to the east or to the right. To the right. Then they want us to get the magnitude of the charge on N. Magnitude of the charge on N. So since we have the net electric field, I think we can use electric field. Then we can find the electric field at P as a result of N, which will be K, the Q of N over R squared. So that at the end we have our innet being the E as a result of M plus the E as a result of N. Something like that. So since we have the first one, we just need to play around with that. So I'm going to say 9 times 10 to the next equals 9 times the charge of N over the distance between P and N, 15 and 14, which is 45, so 0,05 squared. Okay, when I put that into my machine, 0,045 squared, having a very big piece. This makes sense. 1, 2, 3, 4, 5, 6, 12. It's gonna make sense. It's gonna make sense for that's 12. I don't know. Let me just, okay, I'm having 4,44 times 10 to the 12 QN. Okay. So the net that side was 2 times 10 to the 5. So the net is 2 times 10 to the 5. We are saying this is equal to the 1,000 plus 4.44 times 10 to the 12 QL. Yeah. Okay. Now someone asks, why are we adding them? Now, since the net force or the net electric field is acting eastwards, which means all of the charges, all the electric fields must be in the direction. So we are moving this one in the east. So then I'll move this to that side. So 2 times 10 to the 5. Then I will subtract my 160 tau. My 160 tau, I'm getting 40 tau. Is equal to 4.44 times 10 to the positive 12 Qn. Divide by 4.44 times 10 to the 12. Divide by 4.44 times 10 to the 12. This cancels that. Remember, we said we're going to subtract when you transpose that. So Qn going to be 4.44 times 10 to 12. Okay, I'm having 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm having 9,01. Times 10 to the negative 9 coulombs. Or someone can say that is 9 nanocoulomb. Now with the charge, it will be positive. Then 1.4 is the charge on the sphere, positive or negative. Answer that. Positive. And then they want us to sketch the net electric field pattern due to M and N. Now we said it's positive, and then the original, this one, was negative. So that is a positively charged and negatively charged attraction. Unlike charges attract each other. So, unlike charges must repel. Whereas the like charges, unlike charges must attract. Whereas like charges do the repulsion. Then calculate the magnitude of the electric force that an electron will experience when placed. Calculate the magnitude of the electric force. Guys, how do we go about that? Okay. So we know that E is equal to F over Q. E is equal to F over Q. And what did we say? We say that so I'm still on the same question. Yes. Okay, calculate the magnitude of electric force an electron. Okay, since we're focusing on an electron, would experience when placed at that point. So since we have the electric field, the net electric field, we just need to multiply. So Q times E, we know the charge of an electron is going to be the one of times 10 to the negative, as I need the electron charge with my formula. Okay, so I'll get my net, which was 2 times 10 to the 5. And then I'm just going to multiply it by the charge of electrons, which is 1,6. And just confirm. So saying electron charge Okay. So it's 1,6 times 10 to the negative 9. Okay, so when I multiply to, you can put the negative sign, there's no problem. When I substitute that, 2 times 1.2, having 3,2 times 10 to the negative 8, it will be newtons. Guys, that will be it with that first question. Then my question number 2, they're telling me that the diagram below shows two spheres A having that much charge and sphere B insulated. Distance between them is that. And they want us to draw the two patterns. So a negative and a positive. You know what to do. Trash. Trash. So we just so field lines should be seen leaving. Field lines should be seen entering. What's wrong with me? This one lies. Things say. Same. Like that. All right, then 2.2, calculate the magnitude and direction of the force exerted by B on sphere A. Okay, so from electrostatic force, we said F is A P.1 Q2 over R squared. That's 9 times 10 to the 9. The charge on A is 4,5. 10 to the negative 5. 4,5 times 10 to the negative 5. That is 9,5 times 10 to the negative 5. Distance of separation is 0,35. Okay, and then I'll square that. Putting this into the machine, I'm gonna have 9 times 10 to the 9. That's 4,5 for the multiplication. Okay, then we multiply by the 9,5 times 2, okay, that much over 0,35 squared. Having 314,08. But since we're focusing on B on A, then the direction is going to be the right. B on A, the right. They give an attraction. Then calculate the strength of the electric field at P, the result of the strength at P. So we're gonna assume that instead of having the charge of P, just have a positive, because they're asking for the strength at P as a result of P. So that will be E is equal to KQ over R squared. 9 times 10 to the 9. And then we need the charge of A. So it was 4,5. And 10 to the negative 5 over the distance is still the same. Okay, so that's going to be 9 times 10 to the 9. Multiplying it by 4,5 times 10 to the negative 5 over 0,35 squared. Very short number. 3, 1, 2, 3, 4, 5. So I'll say 3,31 times 10 plus. Since the electric field is Newton per Coulomb, also going back to the right. Okay, question number 3. Two identical spheres again, A, B insulated and stands are placed This meters having 10 meters apart, shown the sketch. So the charge on A is negative 10 nanocoulomb, and then B carries some charge that we don't know. Then the net electric field that, so this is more like this question. Find electric field at a point. Remember we said electric field at a point is the force per unit positive charge that is placed at that particular point. I'm not going to write that. Then they want us to draw the field pattern A and B due to charges A and B. Now, since the net force is acting to the left, but it will be at this point, acting to the left. What do you think? Why do you say this? What do you think? So simply means that since it's negative charge and the net force is the left, so which means force between this and this is also left. So which means it's more like an attraction force. Okay? That means I'm going to have a positive, then I have a negative. What that means? Attraction. Okay? That is attraction. And then they want us to get the magnitude of sphere B. So in that case, I'm going to use electric field. Okay, so I need to get the electric field between A and P. And then the electric field between B and P. Then I use the net. Okay, so electric field of PA will be KQ over R squared. That's 9 times 10 to the 9. The Q we said was negative 10. Okay, I'm dividing by 2 centimeters, 0.04 squared. So put that into the machine, I'm having 9 times 10 over 0.02 squared, having 337,500 Newton per coulomb. Then I'm having the E to B, which is Q over R squared. That's 9 times 10 to the 9. That is the QB over 0.08 squared. Simplify that. Having 0.08 squared. Sure, very big number. Scale, I'll count 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. It's 1,41 times 10 to 12. I'll call that cubic. Then now look at our inlet being the same as the ETA plus the EB. Now the net that they gave us was 3,943. 3,943 times 10 to the 5 is equal to 337,500 plus the 1,41 times 10 to the 12, but QB. So I need to take this aside using subtraction. Okay. So when I do that, I have 3,945 times 10 to the 5 minus 337,500, which gives me 5. 1000 is 1,41 into the 12 cubing. Then divide both sides by 1,41 times 10 to the 12. That cancels that. Let's see 1,41 times 10 to the 12. Sorry for rounding off in advance, but it will make just little difference. So the charge on B, I'm having 1, 2, 3, 4, 5, 7, 8, 4,04 times 10 to the negative 8. Guys, that's that. Then they're telling us that sphere B is removed. State whether the electric field at P due to the charge A will increase, or remain the same. So, since P is removed, it's having an effect on the net electric field at P. If it's removed, automatically it's going to decrease. Okay, then question number 4. Okay. They are telling us that 300 microcoulomb charges ABC equals space 0 centimeters on a straight line in a vacuum. Distances are 3 that and so on. Define electric field at a point. We say it's a region. Is this a region of space? No. Of course, by unit positive charge that is placed at a point. Point 1 answered. Then they want us to draw electric field lines associated with A only. Since it's a positively charged sphere or object, then the field lines should be seen moving out. So direction, so straight line, getting lines. 4.3, they want the magnitude of the electric field strength at position where B is and B to A only. So the electric field at this point B as a result of A. So if we place a positive 1 there, we shall ignore the charge of B. So that's gonna be E being KQ over R squared. 9 times 10 to the 9, that's 100 times 10 to the negative. Distance 33 centimeters. 0,03 squared. So that's gonna be 9. So we start over 0.03 squared. So that's gonna be 1, 2, 3, 4, 5, 6. Let's sum 3, 9. So 1 times 10 to the 9. It's 10 per coulomb. Or you can write the whole billion there. Then Coulomb's law in what? Remember we said the electrostatic force. The electrostatic force, whether it's attraction or repulsion, between two charges. Is directly proportional. Directly proportional. The product of the charges, the product of the magnitude of the charges, and inversely proportional. Inversely proportional to the square of the distance between them. Distance between them. Okay, remember I said that it's if that is true, then they want us to get the net electrostatic force experienced by point charge P as a result of A. So they want the force because of P and because of A. Okay, so I'll just kind of redraw that for my convenience. What is this? Here's the 3 and the 4. Okay, so I need to get the first. I need to calculate the first. Between A and C. Okay, that's for convenience. So QA C over R squared. So 9 times 10 to the 9. That is 100 times 10 to the negative 6. 100 times 10 to the negative. Distance of separation is 3 and 3. It's 6. So that's going to be 0,06. That's good. Okay, put that into my machine. It's 10 to the 9. Multiplied by 100 times 100. That's over 0,0. Giving me 25,000. Okay, that is nothing. Since the two are positive odd, then let's go to that. Since the 20,000. Then I look at the first thing beyond. Okay, Q over R squared. It's going to be more or less the same thing. So 100 times 10 to the negative 100 times 10 to the negative 6 over 0,0. That is something that is, so that is 100,000. Okay, now when you look at this again, it's 2 to the right. Since it's 1,000, right? Then this is going to be less. Put it up in your right. Now, since the first force and the second force are in the same direction, the next just imagine this is okay. 25,000 plus 10, no, 100,000. So that must give us with 100 and 105,000. Yeah, it must. Okay. Then now, question number 5. That's what I want. Good. Okay, so we have a negative 3 nanocoulomb. P.1 plus 10 centimeters away from this diagram below. Draw the electric pattern. So positive and negative. Doesn't matter which one we call positive. That comes first. Yes, wrong. In this guy. That is that. Fine, guys, you can do whatever you want to do. As long as you see the two lines leaving from the positive and putting the negative. Okay, so now next we have 5.1. If there is a negative inside, then they want us to draw a force diagram showing the electric forces. Jot down O by Q1. So since positive and the positive is going to be repulsed. No. The negative, the positive, so attraction. This will move in the direction. This will move in this direction. Then since it's a positive and negative, to attraction. Okay, now since they want the force diagram on P2 alone, it's going to be then calculate the net force on P2 as a result of that. So since we drew our force diagram into the horizontal and the vertical,
I need to find those forces. If I can find the net result from this. So force horizontal Q1 over R squared. Okay. So negative 3, so it's going to be just 9 times 10 to the 9 times 3 times 10 to the negative 9, then times 4 to the negative. Distance is 10 centimeters, is the mass distance, which is 0.1 second. Yeah. Then I just need to put that into my machine. 9 times 3, and then I'm dividing it by 0.1. 4, 3, 8, 1, 2, 3, 8, Newton. Then the F vertical is over R squared, 9 times the negative positive 9. That's it. 2 times 10 to the negative 9. This time, 35. 0, 0, 5, 0. Okay, when I put that into the math, over 0.05 squared over 2.16 times 10 to the negative 5 meters 10. But since the vertical and horizontal, for us to find the net force or the result, we said we use the vertical squared plus the horizontal squared. So I do that, zero brackets, then 8.1 times the negative plus 2.1, 10 the negative 5, but squared. Okay, I'm having 2.31. Okay, that is 2.31 times 10, 1, 2, 3, 4, 5. Then that is 5. So with the vertical, I'm getting this. With the horizontal, I'm getting this value, and passing that to the calculator. Then we need to get the direction. We need to get the direction. So theta must be the 6 times the vertical over the horizontal. We do the substitution, like the 2.1 times 10 to the negative 5 over 8.1 and 10 to the negative 6. Here when you put that, you get 2.3. This is the magnitude of force, then it has to be. Then 5.4, we have an unknown charge R. It is placed 3 meters away from unknown charge. As shown, they are telling us that the charge on R is what we need. Okay? If the net electric field is so remember what we said, for net electric field to be 0, then the electric field from different angles, let's say the electric field this side, then the electric field this side, must working in opposite direction. And to the left and right, as long as everything is opposite. So we need to get electric field at P, sorry, at X as a result of P. So it takes Q over R squared, 9 times 10 to the 9. The charge is 8 times 10 to the negative 9. 10 to 6 centimeters, convert that to meters. And then when I put this into my calculator, punch that in the calculator, having E 180 thou. Okay, 180 thou meters per coulomb. Then when I look at this side, the E of X, R of X, it's gonna be K over, I'll call this R over R equal to. So 9 times 10 to the 9 is R divided by 0.01. So here when I try my luck with that, because I want to try again. So 1, I'm having 9 times 10 to the that's QR. Then remember what we said, for us to have a net of 0, must have the restricted strength epsilon in opposite direction. So if I do that, it means I take it to happen in the negative direction. Okay, so that's a 0 is equal to my 180 thou plus, let's say negative 9. So move the 180 to the left, or you can transpose that, so that I have 9 times 10 to the third is equal to 180 thou. Divide by 9 times 10 to the third, divide by 9, and that cancels that. And then my QR divide by 9. So I'm having 2 negative. So that can also change to nano, because taking that right. All right, so that would be that. Question number almost. Question number 6, they're telling us that two identical spheres, P1 P.1 insulating stones are placed via centers 2 millimeters apart. When P1 is brought into contact and then moved back to original position, gain the negative 12,15, sorry, 12,5. And the charge on each sphere is this. So, guys, one thing we need to remember is that when spheres are brought into contact, there is going to be equal distribution of charges. Look at the separation. The magnitude of charges has to be. So number one, they want us to draw the electric field testing around both spheres after they are touched and separated. So since both gain negative, so that between that are the contact, which means it's just gonna be a case of 1,000. That remember, the two lines have to be the same.
So this we have to enter. See, talking of a negative charge. Okay, that is that. And then 6.2, they're telling us that state the law of conservation of charge. So there are quite a number of ways and tell us the net charge. The net charge of an isolated or in an isolated the net charge and constant or constant. Or someone can talk about that charges can neither be created, charges can neither be created nor destroyed, nor destroyed. They are just transferred. That's what happens. Transferred from one body to another. Alright, so anyone of the two will work for us. They are telling us that an electron of negative, an electron, let's between P1 and P2, will the electron move to the left, to the right, or stay in the same position? Now they're telling us that the electron is one. And remember we said when there's a repulsion, this area or this region of space will experience what here. Nothing is going to happen to this electron. The force is equal but opposite. So gonna say it's the same position. Okay, it may be 7.4, 7.4. Or calculate the magnitude of the electric field due to the charge on sphere at 0.10 millimeters to the right, 10 millimeters to the right. So if we have a point, 10 millimeters, what will it be? So E, remember we said take Q over R squared. So K is 9 times 10 to the 9, but we told me to stay 7.5. Plus 7.5 times 10 to the negative 9 over the distance, they told us 10 millimeters. When you convert 10 millimeters to meters, it's going to be 0.01 square. Alright, so when I do my magic, having 67, 5,000 coulombs. Then they are telling us in 6.5 that the questions of all relate to the original charges. 1 and 4 were brought in context given in bold capital letters. What is the magnitude and sign of P1 and P4? So when we look at it, P1, P1, it's negative 7.5 coulomb. So it's a negative 7.5 plus it gained how much? It gained negative 12.5. What does this give us? Negative 10.5, that is 20. No, okay. So it is negative 7.5, gains us 1. We can write it the other way around. Okay. Same with your integer. So it has that much. Then for us to get what is left on this, we can do more or less the same.
where we look at -7.5 minus 4.5. Gaining is a plus, C is a minus. When you do that, you get a positive. That's alternative number 1. Other alternative is by looking at P.1 divided by 2 must be that right there. If you have your P.1 known, it will be just transposing that. So that is -25 plus. When you multiply both sides by 2, you're gonna get -2. This is 20.5. So when I move that aside, my is just gonna be 45. Then 6.5.2, they want the force between Q1 and Q2 before they touch. So the force should say Q1, Q2 over R squared, 9 times 10 to the 9, the Q1 is 20.5. Dividing by the distance, so that's it. Millimeters. So 0.3 squared. So when I put that in, then dividing by 0.03 squared, having 0.01. So that is the force that I'm having. Force that Q1 is just since the charges are opposite, tell us about. So Q2 equals to 5. Yeah, we can understand. Yeah, all the steps minus our correct. Q2 would have Q1. And then it's electric field pattern. 1 and 2 before they touch. As so remember, before they touch, we're having a positive and negative. And then after they touch, there was a pause. So now with multiple choices, we can use elimination format before we can get to the correct option. Okay. So we have various options that have been provided as possible answers, the following. Each question has only one correct answer, and we need to choose that correct answer and then write that in our answer book. Okay, so I'll start with question number 1. So which one of the following quantities is the tendency of an object to resist a change to its state of motion? Is it inertia? Is it impulse? Is it momentum or acceleration? So we know that acceleration cannot apply that. Okay, because acceleration is the rate in change of velocity. Momentum is the product of mass and velocity. Impulse, it's something else. So the correct option would be A, which is inertia, the tendency of an object to resist motion from Newton's first law. Okay, then 1.2, we have a ball that is dropped from rest at a height above the concrete floor. Okay, and then they're telling us that this ball strikes the floor and bounces vertically up and down on the same spot on the floor. So the velocity time graph is being drawn for us for the bouncing ball, with the points P, Q, R, S representing the different times during the motion. So this point here will represent the time when the ball was just at that height. And when it is dropped, probably it's moving, and then reaches the floor. Okay, and then it starts to move up. And then at this point, it's probably reaching maximum, because you can see that the velocity is 0 at Q. So probably that's the point where the ball reaches its maximum and then drops down, and then at point R, and so on and so forth. So what are we going to say? At which time does the ball reach its maximum height? After the first upward. Okay, so when you talk of first upward, remember here it's coming down. And then between this point and this point, the ball is going up. And then as it goes up, the velocity decreases. We have in that point where the velocity is 0. So point Q will be our answer, and that is option B. And then 1.3, we have two blocks, P and Q of masses M1 and M2, respectively, that are held at rest on a frictionless horizontal floor. Both of them are being compressed with a spring, as shown. And so blocks are released, and then the spring decides to drop to the floor. Block Q, this one moves to the right with velocity V. What will happen to P? So in normal cases, under the conservation of momentum or impact, we know that the momentum or the impact that Q will have on P would be the same, but just in the opposite direction. So in this case, they are asking us to determine the momentum of P. Okay. Now, since they were held together with a spring, and then the spring was removed, so we expect the reaction to be the same, but just in the opposite direction. So if Q is having M times V as its momentum, so it's M2 times V, then the same should be applicable to P, but in the opposite direction. If this is to the right, then this is going to be to the left. So we expect to have M2V, but to the left. Is there an option like that? M2V to the left. That is option D. Okay, then 1.4, they're telling us that the magnitude of the gravitational force that spheres X and Y exert on each other is F. So from Newton's law of gravitational force, if that is X and then that is Y, if these two are separated with distance R, what happens? So we know that the force is directly proportional to the product of the masses, and then inversely proportional to the square of the distances apart. Now the mass of X is doubled. So instead of us having M, we're going to have twice M, 1. And then they're telling us the mass of Y and the distance just remain the same. Okay, so which means our new F is going to be G, and then twice M1, and then M2 over R squared. We can move this 2 in front so that it is a G, M1, M2 over R squared. Okay, so we're seeing that this is representing the F, and it is the same thing that is this. So which means our final result must be 2F, or twice the original force. So remember, the force that X exerts on Y should be the same force that Y exerts on X, but in the opposite direction. Okay. So they're asking us which one of the following combination is correct for the magnitude of the forces that the spheres exert on each other. So remember I said they have to be the same, but currently our force has to be twice the original F. So this and that, which is option D. Then 1.5, hot air balloon, vertically downwards. Is moving vertically downwards at a constant speed. This is in capital letters, okay? So something is happening. So constant speed, so velocity is the same. Assume that the mass of the hot air balloon remains constant. So mass is the same, speed is the same. Okay, which of the following physical quantities associated with the hot air balloon will change during the motion? So is it the weight? They told us the mass must stay the same, so weight cannot. Okay, is it the momentum? Momentum, remember, is mass times velocity. So if the mass is the same and the velocity is the same, this must also be the same. So momentum is out. Is it kinetic energy? We know that kinetic energy is a half mv squared. So if mass and the velocity are the same, which means kinetic energy is also the same. What about potential energy? We know that potential energy is mass, gravitational force, and the height. The mass, gravitation, or acceleration due to gravity, and then the height. So the height will keep on changing. There's no way height is going to stay the same. So it's the potential energy that is going to change during the motion. All right, 1.6, a learner that is standing by the roadside records the frequency of sound waves that were produced by a siren of an ambulance, okay? So the ambulance is moving at a constant velocity along the road, and then they drew the graph for us. So the y-axis is representing the detected frequency or the frequency of the listener, and then as time passes. So what we can see is that the graph is below, which means the frequency starts by being low, and then all of a sudden the frequency increases. What does this tell us? So if the frequency of the listener overall increases, which means the ambulance is approaching the learner, or it's moving towards the learner. This approaches the learner. Okay, that is the kind of conclusion you can have. So probably it was moving from a distance and then it comes towards the learner. Okay, so which option of the following, which of the following statements concerning the motion of the ambulance is correct? So the ambulance approaches the learner and then passes the learner. You see, if it's approaching then passes, then we'll have another extension where the frequency drops again. Okay, so this is a 1-2 approach. It's either approaching or leaving. Okay, so because of this last statement, I'm nullifying A for now. Okay, then let's look at the second option. It moves away from the learner and then turns and approaches the learner. Moves away. So when it's moving away, the frequency is low. And then when it approaches the learner, the frequency increases. There's some truth in that statement. Let's see, option C. It approaches the learner and then turns and moves away. No, that is not correct, because if it was turning away, then the second part of the graph would be below, or would be lower than the first one. And then moves away from the learner and then stops. This is out. So I'll take option B because it has some bit of truth in it. It moves away and then turns and approaches the learner. So as it's moving away, the frequency is below or less. And then as it's approaching, the frequency that will be observed by the learner will be high. So option B is the correct answer there. And then 1.7, we have two identical spheres, X and Y, that are carrying +2 and then -6 Q respectively. Sphere X experiences a force F to the right, X to the right, when the distance is that, all right. Then the spheres are brought into contact and then return to the original positions. Which one of the following represents the magnitude of electrostatic force that X experiences now? So just like Newton's law of universal gravitation, it's just the same as the electrostatic force. Okay, what differs is just that This has a constant of K, not G. Okay, and then in this case, we're going to be talking about charges Q1, Q2 over R squared. Okay, I'm not going to simplify everything. I just need to look at what's going on. So I'll maintain the K, I'll maintain the R squared since those are constants. So this will be a 2 times a 6, okay, which will give me 12K over R squared. So currently, before the spheres touch each other, this is the force that each sphere will exert on each other, okay? Then when spheres are brought into contact with each other, okay, so a positive 2 and then a negative 6, the charges are going to combine, and then the resultant charge on each sphere will be divided, or will be a result of division between the sum of the charges. So this would be 4 plus negative 6, that's going to be negative 4 divided by 2, which means after the separation, each sphere must be a negative 2 charge. If the distance is still the same, then you try to look for the force, that is K, Q1, and then Q2. So that's over R squared. So that's a K. That is a K. I'm maintaining the K. Q1 is a 2, my Q2 is a 2 over R squared. So that's going to be 4K over R squared. Remember, this was 12K over R squared. This is 4K over R squared. So this is the new force. This is the original. So which one of the following represents the magnitude of the electrostatic force right now? So when you divide 12 by 4, or when you divide this force by this force, it's going to be 3 times smaller. Okay, so if it is 3 times smaller, which means it's 1 over 3 of the original force. Get this new force, divide by the original force. So the option I'll go with is B. That is 1.7. Okay. Then 1.8 in a circuit diagram below, R1, R2, and R3 are identical resistors. So identical simply means they have the same value, and the battery has negligible internal resistance. Okay. What happens to the power that is dissipated by R1? No, they're telling us the power dissipated by R1 is P. Okay. So if the power dissipated by R1 is P, the question is asking us, what happens to the power that is dissipated by R2? Now, if I were to assume that, okay, so I'm saying if I'm to assume, let's say, since they're identical, I can call this 2 ohms, as well as 2 ohms. I can just come up with I can set 10 volts as my voltage there. Just I want to bring about the picture of everything. So the effective resistance within this parallel combination, remember we are 2 resistors, so product over the sum, that's going to be 4 over 4, which is 1 ohm. Okay, that is for the parallel combination. Now, since this parallel combination is going to be in series with R1, I'll plus the 2 ohms, which means my effective resistance is going to be 3 ohms. Then if I want to find the current, because I need the current that is passing through, current is going to be given as V over R. Okay, so if I have 10 over 3, which will be the same as 3 comma something. Okay, let me just leave it as 10 over 3 ohms. Okay. Then I know that from the formulas of power is given as IV. Okay. Or I can use the combination that has what? Because now this 10 over 3 is the current that is flowing through this entire circuit. and it's the same current that is going to pass through the R1. So if I were to look at, do I need the voltage? I can use I squared R, okay? Let's say I'm looking for the power of R1. So it's going to be 10 over 3 squared times the 2. Just 10 over 3 squared, that's going to be 100 over 9. Okay, and then times 2. That's going to give me, I need the fraction. It's going to give me 200 over 9 watts. Okay, that's the power in this. Then what will be the voltage of R1? Voltage of R1 is going to be 10 over 3 times the 2, which is going to be 20 over 3 volts. But if my original was a 10, then I'll have 10 minus 20 over 3. Okay, 10 minus 20 over 3, which gives me a 10 over 3 volts as well. Okay, so we're saying that this voltage is going to be the voltage of the parallel combination. Okay, now we have the voltage, we can get the current that is passing through the, or we can directly look for a formula that has voltage, because we know the voltage across R3 is going to be the same voltage across R2. Okay, the power formula that combines voltage and resistance, voltage and resistance, is P is equal to V squared over R. Okay, so when I get my voltage, which is 10 over 3 squared, and then I divide it with my R, which is a 2. Let's see. That's going to be 100 over 9, and then I'm dividing it by 2. What do I get? I end up with a 50 over 9. So this is the power in 2. This is the power in 1. So now the question is asking, which one of the following represents the power that is dissipated by R2? Okay, so the question is, how does this, remember, for R1 is the same as P, this P. So how does this relate with this? Okay, how does this 200 over that relate with that? So what I'm going to do, I'm going to say if I have 50 over 9, then I divide it by 200, still over 9. I'm getting 1 over 4. Okay. So I'm saying 50 over 9 divided by 200 over 9. Then I'm getting 1 over 4. So which means this R2 is a quarter of P. And the correct option is A. So I just had to come up with numbers just to create an idea of what's going on there. Then 1.8, they're telling us that the following is a simplified drawing that represents a DC motor. Okay, so one thing we know about DC motors or AC motors is that they use what we call the Fleming's left-hand rule. Okay, that's the basic thing we need to know. They are asking us, okay, that the diagrams below indicate some changes that we made to the motor. So you can see the north and the south being switched around. And then you can see that the terminals are also being switched around in the second option. And so on and so forth. Okay, what is the question asking for? Which of the changes to the motor above will change the original? Okay, what changes are going to change the original direction of rotation? Okay, so what we need to know is from the original, this is the positive and this is the negative, which means current is going to flow in this sort of direction. because current flows from the positive towards the negative terminal. We know that the field is from the north to the south pole. Okay. Then if we apply our Fleming's left-hand rule, okay, what is happening? All I can see is that this structure of ours, or this plate of ours, or coil, is going to rotate in which direction? Which direction is this? Okay, this is going to be downwards. So which means it's rotating in the anti-clockwise direction. Okay, if I use my Fleming's, I'm going to end up having something like that. Okay, if this is my force, so this is my thrust of the force, this is the field, and then this is the current. I'm just looking at this part alone. The field, current, then it's going to go down. Okay, once it goes down, then the rotation is going to be anti-clockwise. Okay, so the question is asking us what change, or from the given drawings, which one is not going to be anti-clockwise? In other words, which one is going to be clockwise? So changes were made. If I'm to get the question correct, which of the changes will change the original direction? So we want something that's going to create a clockwise direction. Okay, so let's see from diagram number 1. So current is moving in the same direction, but what has been changed is the polarity of the magnets, that now the field will be moving in that sort of direction. So if I look at, I don't know, I will still just look at this side alone. Okay. Okay, so from our Fleming's left-hand rule again, when I try to twist this kind of thing, okay, so I'm looking at this green line. Does that make sense? Green line, green line. Yes, this is going to be moving upwards. Okay, because current is moving that side. So if I'm to draw more or less the same thing, where this is at 90 to each other, it's going to be moving upwards. And if it's moving upwards, this is a clockwise direction. Okay. Let's try to look at option number 2. Option number 2, the field is to the right, current is moving in that sort of direction. Okay, with my Fleming's left-hand rule, let me just look at just this portion. Just this portion, okay? Current is moving in this direction, and so this one is moving upwards also. So which means it's a clockwise. Okay? Let's look at option number 3. If I focus, current is moving in this sort of direction. If I look at my field, and focus on this, that current is moving in this sort of direction. Okay. Current, where are you? See, your field is moving that way. So it means it's going to move downwards. This one moves downwards, which is the anti-clockwise. Okay, anti-clockwise. So, which of the following changes will change the original? So, number 3 is original. Okay, so 1 and 2 are the changes that are going to change the original direction, since both of them are giving us the clockwise. So 1 and 2, which is option A. And then 1.1.0, 1.10. An atom has a ground state energy, that is X. When the atom moves to a higher energy state, which is Y, there's a line spectrum that is observed. Okay. So one thing we know is that when atoms move, so we say if the energy at ground is X and the energy at the higher state level is Y. When that happens, there's an absorption that will take place when atoms move from low energy levels to higher energy levels. That is absorption that is taking place. When they move from high energy levels to low energy levels, that's when they emit their energy. Or that's when they emit light in the form of that. Okay, so our options have to be C and D. Okay, since there is absorptions moving from a low energy level to a high energy level. Then the change in the energy, since this energy is higher than this one, so the change is always highest minus lowest. So Y minus X, and then that's the absorption. So I'll go with option D. Okay. If there's any difference, please let us know under the comment section. Okay. Then question number 2. Question number 2. They're telling us that a block A of mass M is connected. A block of mass M is connected to block B of mass 7.5 kilograms by a light inextensible rope passing over frictionless pulley, as we can see. Okay, we have a height of 1.5 meters above the ground, and so on and so forth. All right, let me just try to decrease this so that we can see the entire question. All right, I think that's much more better. Okay, this is our height, that's all that. All right. So while block B is released, okay, remember, initially it's been held at this point without moving. When B is released, it moves vertically downwards and strikes the ground with 3.41 seconds, or meters per second. Okay, if we are ignoring friction, can we show by means of calculation that the magnitude of the acceleration of block B is 3.88 meters per second squared, while the block was moving vertically downwards? So what I can see is that if our focus is on block B alone, then we shall assume something like a free fall in that case, where the motion is entirely under the influence of acceleration due to gravity. It's more like a vertical projectile kind of scenario, okay? And if I'm to look at it in that form, then I'll have to apply those equations of motion, okay? In this case, I could say that, what do I have? I have my displacement. So change in Y is 1.5. What else do I have? I have my final velocity, which is 3.41 meters per second. What is our initial velocity? It's a 0. Okay. Is there anything else we need? Is there anything else we have? We want the acceleration. Okay. Projectile. Okay, that's fine. So I can say that if I have V squared, Bf squared is equal to V I squared plus 2A delta Y. Okay. So I know my final my initial, acceleration is what I want. I have my displacement. Okay, so this is going to be 3,41 squared is equal to 0 plus this is 2 times 1,58. Okay, when I have 3,41 squared, that's going to give me 11,6281 is equal to 3a. Then I'll divide both sides by 3. And then what is my a? My a is 3,876. When I round it off, I'll get 3,88 meters per second squared. Okay, so that is how I would go about answering 2.1. Then when I look at question 2.2, okay, 2.2, they're asking me to draw a labeled free body diagram showing all the forces that are acting on B. So when you look at B, there's just weight that is acting downwards, and then this tension force that is within the rope. Okay, so my free body would be just tension, and then we're saying this is the weight. That is just enough. And then 2.3, can we state Newton's law, Newton's second law of motion in words? Okay, so there are different formats, there are different scenarios to this law, but they are just some keywords that we normally want. Okay, and so one can say that the net force that is acting on a body, an object, is directly proportional. Okay, the net force acting on an object is directly proportional to the acceleration. The net force is directly proportional to the acceleration and inversely proportional to the mass of the object, the net force acting on an object is directly proportional to the acceleration and inversely proportional to the mass of an object. Okay. And one thing we know is that this acceleration will always be in the direction of the force, directly proportional to the acceleration and inversely proportional to the mass of the object, and acts in the direction of the object, direction of motion of the object. Okay, just play around with those words, but for as long as we see this word of directly proportional, okay, so that the force is directly proportional to the acceleration, at least it must be within your statement, and then inversely proportional to the mass, and then acts in the direction. So they're just keywords that we're interested in, but play around with the English. Then 2.4, they want us to calculate the value of M. Okay, M is the mass of the second body by applying Newton's second law on each block. Okay, so when I look at my object A, I have tension that will be acting upwards, and I know weight will be acting downwards. So from Newton's second law, we know that F net is equal to MA. Okay. And then when I look at, we're saying body A, my F net is going to be the tension, which, because I'm assuming if the whole direction is moving downwards, whereby B is moving downwards, which means A is going to move upwards. And for A to move upwards, the tension must be slightly greater. Okay, so I'm going to say tension minus the weight of A must give me the mass of A times the acceleration. Okay, I can do my substitution. I don't know my value of the tension, so I'll say weight is given as the product of mass and the gravitational force. So I'll say weight. Why don't I just move everything so that I can make tension the subject, so that I have mass times my acceleration minus my weight, which is going to be mass times the gravitational force. So what is this going to become? Mass is common. I don't know the mass of A. So that's going to be my A, which is 9, sorry, the acceleration that we got, it was 3,88. Okay, that's 3,88. When this one moves that side, it's a plus, sorry, it's not a minus. And then that's 9,8. So guys, I'm factorizing out the mass. I'll be left with the acceleration and then the gravitational force. So which means my tension is gonna be, what's 3,88 plus 9,8? I'm getting 13,68, 13,68 M. I'm gonna call this equation number 1. Okay, and then when I look at body B, okay, with body B, remember we said the weight from the free body diagram that we drew. Okay, the weight is moving downwards, so which means the weight has to be a bit greater. So we're saying F net is equal to MA. So we're saying the weight minus the tension must give us the mass and the acceleration. And so the weight of B, remember our mass for B was 7,5 times 9,8. From the definition of weight, we said mass and the gravitational force. We are subtracting the tension, which we don't know, should give us the mass, which is 7,5 times 3,88. Okay, so when I simplify, or I can even substitute at this level. Okay, but let me first simplify. I know I have 7,5. Hello, 7,5 times 9,8. That's 73,5. Minus my tension is equal to 7,5 times 3.88. That's giving me 29,1. Okay. I can move the 73,5 to that side. I transpose it. So negative T is going to be the same as 29,1 minus 73,5. When I get 29,1 minus 73,5, I'm getting negative 44. Okay, 4. Divide both sides by negative. So which means our tension is 44,4. Then I'll get this tension and substitute it into origin, the first equation, which means 44,4 is equal to, that was 13,68. 13,68 M. And then I can divide both sides by 13,68, divide by 13,68. Okay, when I do that, I'm getting 3, so my M becomes 3,2456, which is the same as 3,25 kilograms. Okay, so that is that with that question. And then 2.5. So we've answered 2.4, now we're going to 2.5. They want the maximum height above the ground that block A is going to reach. Now, for as long as there's motion and the entire system is moving, the entire system is going to move with the same acceleration of 3,88, because that would have been the other option that we could have used to get 2.4. okay, when you're calculating the n. But since they wanted on each block, that's why we worked it out separately. So with 2.5, since the whole system is using the same acceleration, which means when this block B strikes the ground, okay, that would be the velocity with which block A will also be moving upwards. Now, since block B is going to move 1.5 meters down, we expect block A to also move more or less the same distance up. But because of the 3.41 meters per second, and because of inertia, this body will continue moving upwards till this velocity dies to a zero. Okay? So what we need to know, or what we need to differentiate, is that after the 1.5 height, 1.5 meters height, this body A is still going to continue the 3.41, since at that height, body B is halving the 3.41. It's a system, so everything is more or less the same. Okay, so we're going to say at a height of 1.5 meters, at h of 1.5 meters, A will have what we're calling the VI of 3.41 meters per second. And we know that at maximum height, at height maximum, the final velocity must be a zero. Okay, the question is asking us to find the displacement. So we need to find the height that the object moves. Good people, what do you think? What do you think? What do you think? What do you think? So I can use that formula of the VF squared is equal to VI squared plus 2G. If I use G, I can use A. I don't need to use G as such. I can use A delta Y. Okay. When I apply my substitution, we are saying our VF is 0 is equal to the VI, which is 3.01 squared plus 2. Why am I using a plus? It should be minus, since the body A is moving upwards. So I can say plus, then I can use negative 9, that's negative 9.8. Will it make sense? Makes sense for me to say that. Use 9.8. Why can't I use my acceleration, which is 3.8? 3.88 delta Y. Okay. Then I can move this to that side. I know that 3.88 times 2 is going to give me 7.76 delta Y, and then 3.41 squared is giving me 11.62. Does that make sense? Guys, I need to change this because remember, after the height of 1.5, this is going to behave as a projectile. So negative 9.8. It cannot be positive, the 3.8, because the system would have stopped moving because of the block B. Okay, so this must change to a 19.6. Okay, because 9.8 times 2, that's 19.6. Then I can divide both sides by 19.6 over 19.6. Okay, when I do that, Then my y is going to be 11,6281 divided by 19.6. That's giving me 0.59. Okay, 0.593. So which means this is the extra distance that the block moves upwards before it reaches the maximum height. Now, since the question is asking for the maximum height above the ground, then we're going to get our 1,5 plus the 0.593. And then that's going to give us 2,093 meters or 2,09 meters. Okay, so that is question number 2. Let's look at question number 3. Number three. We have a ball A that is dropped from rest. Okay, the keyword there rest, and the height is 15.2 meters high. Then after ball A has fallen, just a small distance of 3.2 meters, a second ball is projected upwards from the ground. And then after a while, the two balls strike the ground at the same time. Okay. Let's see, define the term free fall. So one thing we said about free fall is that this is basically a motion of an object that is entirely under the influence of acceleration due to gravity. And so the motion of an object or motion that is entirely influenced or that is entirely influenced by acceleration due to gravity. Okay, that would be my mini description. Okay, then they're asking us to determine the time that it takes for ball A to strike the ground. So when we look at ball A, what do we know about ball A? Okay, this is 3.2.1. So for ball A, we know that the initial velocity is a 0. The displacement that it must go through is 15.2 meters. Okay, is there any other information that was given? They want us to find the time. Okay, that is what we need. We know the final velocity. Oh, we know the final velocity. So, good people, what do you think needs to be done? So when I look at this question, which equation of motion are you going to use? Because V final is equal to V initial plus this won't work. But since we don't have our final velocity, we can use this one, where we look at V initial times time plus a half G times delta T squared. Okay. So our displacement is 15.2. Our initial velocity is 0. So that is going to die out. Since the object is moving downwards, I'll treat it as positive. So that's a half times 9.8 T squared. Okay, so 15.2 is equal to a half of 9.8 is 4.9 T squared. Then I'll divide both sides by 4.9. So 15.2 over 4.9 is equal to T squared. And then I'll take square roots on either sides. So 15.2 over 4.9 gives me that square root of the answer. I'm getting 1.76 seconds. Okay, so that is what they want us to find for 3.2.1. Then 3.9.2, 3.2.2, that's wrong with me with 9. They want the magnitude of velocity with which B was projected. So guys, what I can see, remember, since we have our time as 1,76 seconds, we need to find out how much time did this object travel a distance of 3,2. And then perhaps if we can subtract that, then we could get the time with which object B is going to travel. Okay, to go up and even come down. Okay, the total time for object B. So I'll say that I'll say this is 3.2.2. Time taken for A to travel 3,2 meters. Okay, so I can still use the same formula of delta Y, delta T plus a half delta T squared multiplied by G. So where there's delta Y, I'll have my 3,2. You say that is a 0 plus, remember object A is going down, so I'll still take my G to be positive. So that is a half times 9,8 delta T squared. Then I'll have 3,2, I'll divide it by 4,9 is equal to T squared. And then I'll take square roots. Okay. So square root of 3,2 over 4,9 is giving me 0,81 seconds. Okay, so this is the time that the object A had traveled just for this small distance. Now, if that is 0,81, then how much time is left for object B? Okay, I'll say time of travel for B is going to be 1,76 minus the 0,81. Okay, 1,76 divided by 0,8, so minus. Okay, so we said 1,76 minus 0,81, and that gives me 0,95. Okay, seconds. Now, remember the question wants the initial velocity for B. Okay? So if this is the time of travel, the total time of travel, I can look at a point where this object goes. I don't know where it ends now, but then it's going to come back down. So it's saying the total time is the 0,95 seconds. So I'm going to take my displacement at that point. Okay, so my displacement, I'm going to take it as a 0 because it went up with a positive displacement and then it came down to the point of projection. So my displacement is 0. My time is this. I need my initial velocity. So initial velocity is what we want. So from delta Y is equal to VI delta T plus a half G delta T squared. Okay, so where there is delta Y, I'm saying I'm going to use a 0. Initial velocity is what I need times 0,95 plus, I'm going to say a half times, since the object is moving upwards, then my gravity is going to be negative 9,8, but with a T squared. I simplify this. I'm going to take this, I'm going to move this to that side, to the left, the equal signs. So that's going to be 4,9 T squared is equal to 0,95. What's happening? What's wrong with me? Why am I not replacing t with 0.95? Okay, 0.95 squared. Okay. Then if I simplify this, I have 0.95 times 4.9. Okay, I can just cancel this with just one of these, just quick, so that I have my V initial as 4.655, which is approximately 4.66 meters per second. Okay, so that is that. Or if not, simplify this whole thing with the square and then divide by 0.95. You get the same thing. All right. Then the next question is telling us that on the same system of axes, can we draw a position time graph to show the motions of ball A as well as ball B? After time it was dropped and reaches the ground, we're taking the ground to be the zero position. We need to label the graphs A and B, and we need to indicate the following. So there is one thing we need to know. Let's see. With the initial velocity of 4.66, how far is the object going to go? Let's say I'm looking for the maximum height. So delta y is equal to vi delta t plus a half. Does that make sense? Let me use v squared is equal to v initial plus 2 g delta y. Okay, so my final is 0. That's 4.66 squared plus 2 times negative 9.8 delta y. So 4.66 squared gives me 21.716. It's going to be equal to 19.6. 19.6 delta y. And I divide both sides, 21 divided by 19.6. I'm ending up with a very miserable answer, guys. 4.66 squared. Okay, that is 21. So which means this object is going to move just a small height and then it drops back. So which means it's not going to go beyond the 15.2. That's what I was looking for. So if this is our position, I can say delta y in meters. This is our time in seconds. So if this is my 15.2, this object is just going to move to that point. So if this is our time that we said it was 1.76. The second body, I'll call this A. Body B, we said starts at 0.81 seconds. It moves up, reaches its maximum, and then falls back within the same sort of time. Then I'll call this my B. So guys, this is how the graph for 3.3 would look like, according to me, guys, no? According to my understanding of the question. Then let's look at question number 4. So question 4 is telling us that trolley A that is having this mass moves 0.4 meters per second to the right in a straight line on a horizontal front, collides with a stationary. So if the velocity is 0.4 meters per second, which means the initial velocity here is 0, then after the collision, they're telling us that the trolley is locked together. In other words, they move as a combined body to the right. State the principle of conservation of linear momentum in words. So what we know about conservation, we can say that in an isolated system, Okay. And say that the total linear momentum. That is spelling of momentum. It's constant. So what that means that it stays the same. Total linear momentum before collision is the same as that after collision. Then 4.2, they want us to put the magnitude of the velocity of the trolley is immediately after the collision. So from the law of conservation, we know that mass A, velocity initial of A, plus the mass of B times the velocity initial of B must give us the velocity combined of mass A plus mass B, since they're going to have the same velocity after the collision. So the mass of the body A was 7,2. So this is 7,2 times the initial velocity. We told us is 0,4. Plus, we know that the mass is 5,3 there, times the velocity 0 is equal to V into 7,2 plus 5,3. So we know that 7,2 times 0,4 is going to give us 2,88. We know this is a 0, so on my left I'll have 2,88, and then 7,2 plus 5,3, that's a 12,5 velocity. And I'll divide both sides by 12,5, divide by 12,5. So this cancels that. And then my velocity is going to be, what is it? I'm having 0,23. 0,2304. So just 0.23 meters per second. 0.23 meters per second. So that is the velocity of the combined, okay, 0.23 meters per second. Then 4.2.2, they want the average net force exerted by A on B during the collision, if the collision time or the time of contact is 0,02 seconds. Okay, so remember, they want the average net force. Average net force. So we know that F net is the same as mass times the acceleration. We know the acceleration now. You can say that acceleration is the same as the rate in change in velocity. Okay. So which means it's M, which is V final minus V initial over delta T. Or someone can look at it as the net force being the change in momentum. Okay, the change in momentum, so that it is F times T is equal to that. Then what we say from this, we know that our mass, we're going to use the mass of B, which is 5,3. The final velocity that we got was 0,23. The initial velocity of B was 0 since it was stationary over the 0,02. So when I substitute that into my calculator, this is 0,23 minus 0. Let's say 0, okay, over 0,02. The answer that I'm getting is 60.95. This is force, which means it will be measured in newtons. Guys, that is question number 4. Let's look at question number 5. Number 5, they're telling us that we have an electric motor that pulls a 20 kg crate from rest at point A up an incline by means of an inextensible rope. The inclined plane makes an angle of 18 degrees with the horizontal. We have B, C, and D are points on the incline, and the distance between A and C is 15,6. Then the motor exerts a force. Okay, this is important. So which means like the force applied is 96,8. And then there's a frictional force of 13,5. It's constant. Okay, define a non-conservative force. So we know that a non-conservative force is one where the work done, okay, is dependent, where the work done, let's say, depends on the path is taken by that force. Is a force where the work done depends on the path. Remember, for a conservative, it's independent. All right, then 5.2. 5.2, use the energy principles to calculate the speed of the crate when it reaches point C. So what I see is that, let's say this crate is somewhere there at point C. What forces will be acting on this crate? I can see the force applied. I just want the forces that are acting along the incline. And since it was moving upwards, then there's a frictional force somewhere there. And then there's also the FG parallel that will be acting along the incline as well. So since we say the work done depends on the path, I can try to look for the work done by each individual forces. And that work done, remember, is equal to the change in the kinetic energy. Okay, we know that work done is the force times the displacement, and then the cos of zero, or the cos of it in that case. So what I'm going to do, I'm going to say work done, or the net work is going to be F delta X, and then the cos of Z. Okay, but remember, this is our F net. Let's get the F net. F net, since the what? I'm going to have the 96. Why don't I just call it the force applied first? Okay. Plus, we can see the frictional force that is acting in the opposite direction. And then plus the FG parallel that is also acting in the opposite direction. Okay, so I'll just attach the negative signs just because they are working in the opposite direction. So this is 96,8. Okay. Minus, they say the frictional force was 13,5. I'm not changing that. Okay. And then minus FG parallel. Remember, FG parallel is given as mg, the sine of the angle of inclination, which is 18 in this case. So it's going to be 20 times 9,8 multiplied by the sine of 18. I'm just looking for the F net. When I punch this into my calculator, 733 times my delta X. Remember, delta X is the displacement, which is 15,6. And then I'll say the cos of 0, since it's acting in the direction of motion. Okay, so I'll multiply this times 15,6. That's gonna give me 354. 5.63 if I'm to round it off. Okay, these are joules. But we're saying net work done is equal to the change in kinetic energy. So initially, the question was specific and told us that the initial velocity was at rest or zero. Okay, where is that statement? So the constant and that the mutex, that's this and that's when it reaches C. Okay, so which means I'm gonna have my 354.63 is equal to a half m, that is V final minus V initial, that's squared. Okay, so that's gonna be, what am I looking for? I'm looking for the velocity. So 354.63 is equal to a half times 20. Remember, my final velocity is what I'm looking for. Initial velocity is 0. So that's going to be V final squared. So that is 354.63. When I multiply a half of 20, it's going to be 10. Divide both sides, I have my VF squared, and then I'll find my square root. All right, so the square root of 85.463 is giving me 5.955. 5.955, which is approximately 5.96 meters per second. Okay, so that is what I'm getting. 54 to 5.96 meters per second. Okay, so guys, that's what we have. Then we look at the next question. They're telling us that when the crate reaches point C, the rock breaks. Okay, the crate continues moving up the inclined plane, and then it comes to a stop at point D. Okay, so at point D, the crate has stopped moving. Then the question is asking us, after stopping to move, it slides down past point B. They want us to draw a label diagram of this crate when it is moving down at point B. Okay, so at this point B, if it's moving downwards, remember there will be no longer the applied force. So what will be affecting this will be the frictional force and the FG parallel. Okay, this side, no, it's just the FG parallel that will be acting downwards, and the frictional force will be acting upwards. Shall have the normal force and then the FG perpendicular in that manner. So which means my free body diagram is going to have my frictional force. This is the FG parallel. You can have the FG perpendicular, then the normal force, Fn. So just that, how many marks is it? Question is 3 marks. 4 forces, it's reasonable. Then 5.5, they want us to draw a velocity time graph for the entire motion of the crate. So what I can see, okay, is that the initial velocity of the crate was 0 before it started pulling or being pulled. Then it reached a maximum of, we said 5.96. Okay. And then from there, the block continued slowing down. Okay, this is going to be velocity in meters per second. Okay, it slowed down and it got to a point, probably D, where the final velocity was a 0. And then it started dropping or coming down, sliding downwards. So remember, this must be straight lines, but this doesn't look like it. Okay. So I'm just going to draw straight line. So we're saying this point is the point D, where the velocity is 0. After it snapped, it continued a little bit till the final velocity was 0, and then it came down. All right, so what do they want us to do for the entire motion until it passes point P, again on its motion down the incline? So we can just extend this limits. There's no harm in that. This was time in seconds. Okay, guys, I think that's that. Question number 6. Question number 6. A car is moving at a constant velocity of 20 meters per second on a horizontal road towards a stationary device, which can both emit and detect sound waves. The device emits. Okay, so this is the frequency of the source. Waves that are reflected off the car and then they are detected by the device. Define Doppler effect or state Doppler effects in words. So we know that Doppler, it does skip a question, guys. It does skip a question. That's 5.5, no? Yeah, remember skipping question. So okay, so we're saying Doppler effect. Doppler effect. What is Doppler effect? Doppler effect. Doppler effect, Doppler effect. Okay, so we say is the apparent change. Doppler effect is the apparent change within the frequency. Okay. Apparent change within the frequency of the source. Frequency of the source when there is relative motion. When there is relative motion, relative motion, not motive, relative motion between the source, okay, between the source and then the observer. Okay, something like that. Apparent change. Okay, assume the change when there is relative motion between the observer and then the listener. Sorry, observer and the source, because listener is the same as observer. Okay, then 6.1.2, they're telling us that if the speed of sound is 340, calculate the frequency of the reflected waves detected by the device. Okay. Question is 6 months, guys. Because when you look at it, frequency of the listener. Something is fishy here. Okay. Let's see if we can break it down. Because 6 marks for was frequency of the listener from the formula. You know that it's V plus minus velocity of the listener over V plus minus velocity of the source times the frequency of the source. Okay. Let's see. So we know that the frequency of the source is 24,000 hertz. Then the velocity of the source is 0. frequency of the listener, we don't know it as yet. Then we need to find what's gonna be the velocity of the listener. We said it's 22 meters per second. And then our V is 340. Okay, let's first find the frequency that the person in the car is gonna observe. So from FL, we have V plus minus, we said VL over V plus minus PS times Fs. Now, since the listener is approaching the source, then we expect the frequency to increase, which means we're going to have a plus on top and then minus down. So that's going to be 340 plus frequency of the listener. Sorry, the velocity of the listener is 22 over 340. That's minus 0 times the frequency of the source, which is 24,000. Okay. This looks to be for 6 marks, which means there's something else that needs to be done as well. Okay, I have that multiplied by 24,000. I'm getting to 5,552,94 hertz. I can write this in circuit notation. There's no problem in that. 2,94 hertz. Okay. So that is the frequency that the listener is going to observe. But what is the question asking for? Calculate the frequency of the reflected sound detected by the device. So which means when this frequency is reflected, now the car acts as the source. Okay, so which means the frequency of the source is 25552,94 hertz. Now we want the frequency that is detected by the device. Okay, we know that the velocity is still 22, that is velocity of the source. Okay, velocity of the listener is going to be 0 now. Then we do the same thing, apply V plus minus VL over V plus minus VS times the frequency of the source. So that is 340. Listener is going to be 0 since the difference is not moving. And then that's going to be 340 minus 22 times 25552,94. So 340 over 318 times 25552,94. Okay. 340 over 318 times 255,2,94. Is it going to make sense though? Let me try and lift two decimals. Doesn't going to make sense. So I'm having 27,320,75 hertz. Okay, so this becomes the frequency that they want, that the machine detects, because there's a bouncing of, which means there is a trip of 2. There's going, and then there's coming back. Okay, then 6.2. They're telling us that the spectral lines observed from a distant star will show that the star is moving away from the Earth. Explain by referring to the frequency how one can deduce that the star is moving away from the Earth. Okay, so one thing you need to know is that when the star moves away, the distance increases. In other words, the wavelength increases as the star moves away. The star moves away. And one thing we also know is that from V is equal to F lambda, we know that our frequency is inversely proportional to the wavelength. So what we can say is that as the wavelength increases, okay, the frequency must decrease, or the frequency decreases. So what does this mean? It simply means that there's going to be a redshift. There is what we call a redshift, where the lines, or the spectral lines will move towards the red, the orange, and the yellow kind of thing. So that's what we call a redshift. So talk about the wavelength increasing and then the frequency decreasing, since the wavelength is inversely proportional. So we can just say wavelength or frequency is inversely proportional to wavelength. We don't need this, and just use this. Okay, and then just for a conclusion. So there's a redshift towards a smaller frequency. Okay, then question number 7. Question number 7, they're telling us that 2-point charges X and Y are held at 0.03 meters apart as shown on the diagram. Then the charge X is this, Y is that. State Coulomb's law in words. So that is 7.1. 7.1, Coulomb's law. Coulomb's law. Okay. Okay, so we know that for any 2-point charges that are placed next to each other, the product, okay, or we can say that the force between the charges is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance apart. That is Coulomb's law. But the force between any 2 charges is directly proportional to the product of the magnitude of the charges and inversely proportional to the same product of the charges Q1, Q2 over the square of the distance of separation. You know that when that is removed, when you have your Q1, Q2 divided by R squared, where K is a constant. Remember, it's 9 times 10 to the positive 9. Okay. Then they want us to draw the net electric field pattern due to the 2-point charges. So what we can see is that the magnitudes are the same, 7.2 and 7.2, as much as the signs are completely different. Okay. So I'll say I have my negative there, and then I have my positive. So from Coulomb's law, we know that like charges will repel, and then unlike charges will attract. Okay, just draw the line. What's wrong with me? Why is it moving in that direction? So the field lines must be seen to move from the positive up to the negative charge. Okay, we can have this, that, and then remember, these field lines should not touch or should not cross each other. The lines must be seen. I can add another line somewhere. So remember, since the magnitudes are the same, which means the number of fluid lines leaving one must be the same as number of fluid lines that are reaching other. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay, something like that. That is 7.2. Then 7.3, they want us to get the force, electrostatic force that Y exerts on X. Remember, this force has to be the same as the one that X exerts on Y. It's just the directions that will be opposite. So we know that the electrostatic force is K times P.1, P.2 over R squared. So we say that is 9 times 10 to the 9. The first P.1 is 7.2. Don't need to really stress about the sign. That's -9. And that's 7.2 times 10 to the -9. I'm dividing this by my distance of separation, which is 0.03, but squared. Okay. So when I punch this into my machine, 7.2 times 10 to the -9 times 10 to the -9 over 0.03 squared. Okay, I'm having 5.18 times 10 to the -4. Okay, since this is a force, so you can say newtons. Now someone will talk about the direction. Magnitude that force Y exerts on X. It's not a big deal. So that is the magnitude of the force. Then 7.4 has information that a third point charge Z with unknown positive charge. So which means there's a positive charge somewhere there. It's positioned that point X on the line. All right. Can we draw a labeled vector diagram showing the directions of the electric fields at a point X, at a point where X is positioned? So all we can see is that the electric field as a result of this is going to act in that direction. And then in this case, it's going to act in that direction. Since the signs are opposite, so there has to be attraction. Okay. So that, then it's going to be that. I can call this E, the result of XY, E as a result of XZ, or EZ and E. It's okay. No problem. So that has to be our vector there. Then 7.5, they're telling us that the magnitude of the resultant electric field. Okay. Remember, electric field is given as KQ over R squared. Okay, so I need to first of all get, we need the magnitude of Z. So we're gonna get the electric field in this direction, and then the electric field in this direction also. So I'll say the electric field, EXZ, it's gonna be KQ over R squared. So which is 9 times 10 to the 9 times my Q here, which is gonna be a Z over 0.01, but squared. Okay, so that's 9 times 10 to the 9 over 0.01 squared. That is giving me 9 times 10 to the 13Z. Okay. And then when I look at the electric field, XY, it's going to be the same. The Q that I'm using is the Y. The Q that I'm using is the Z over R squared. So 9 times 10 to the 9 times, we say 7,2 times 10 to the negative 9 over 0,03 squared. Okay, when I punch this into the calculator, 7,2 times 10 to the negative 9 over 0,033. I'm having 7,2 times 10 to the 4. Okay. But now they are acting in opposite directions. Okay. So one is going to be positive, one is going to be negative. So we're saying E net is going to be E xz, okay, plus the E xy. Let me try to do my substitution into the formula so that I can see what I get. So they gave us the net as 4,91 times 10 to the 5. Exz is 9 times 10 to the 13z plus, this is going to be negative 7,2 times 10 to the 4 xy. All right, then I'm going to move this to that side. I'll move that to that side. So that's going to be 4,91 times 10 to the 5 plus 7,2 times 10 to the 4 is equal to 9 times 10 to the 13z. And I simplify the 4,91 times 10 to the 5. Okay, but I'm adding the 7,2 times 10 to the 4. That's giving me 5,63 times 10 to the 5. I'm dividing this by 9 times 10 to the 13. So what is my z? 9 times 10 to the 13. That gives me 6,25555. So that's 6,26, I think, times 10 to the negative 9. But since it's a charge, so I can call it coulombs. Or someone can call it 6,269 coulombs. No problem. No problem. Question 8. Question 8. They're telling us that a battery of some unknown EMF and some unknown internal resistance. So we don't know this, and we don't know the internal resistance as well. It's connected to 3 resistors and a high resistance voltage, 2 switches and 2 ammeters of negligible resistance. All right. They want us to state Ohm's law in words. They want us to state Ohm's law in words. So with Ohm's law, all we need to know is that the potential difference across a conductor, potential difference across a conductor is directly proportional. Directly proportional to what? To the current. Okay, but at a constant, to the current across the same conductor at a constant temperature. At a constant temperature. So that is Ohm's law. Then if both switch S1 and S2 are closed, the ammeter reading A1 is 1,5. Can we get the reading of the voltmeter? What's going on? Okay. So what I'm gonna do, since this and that are in series, I can combine this so that I have a total of 7 ohms. Okay. So the current through this is going to be 1,5. So I can say that the resistance, let me just say 8.2.1. The resistance at the bottom is going to be 2 plus 5, which we are getting as 7 ohms. And then the current is 1.5. We can get the voltage. V is equal to IR. And that is going to be 1.5 times 7. What is the question asking for? We want the voltmeter reading. So we need to get the voltage across. 1.5 times 7, I'm having 10.5 volts. So this must be the voltmeter reading. And then 8.2.2, they want us to get the reading on the ammeter, A2. So this ammeter reads the total current that is passing through the circuit. Okay. Now we know that this 7 ohm, if we combine these two and we get one single equivalent resistor, the 7 ohm and the 3 ohm are going to be in parallel. Okay. So since we know our voltage as 10.5 across, we need to get the effective resistance of the circuit. Okay. So effective resistance, I don't know, someone can get the effective resistance, but why should I go the long way? I feel like that is a long way. I know I don't need to combine. The voltage across a parallel combination is the same. So 10.5 is across this, 10.5 is across the 3 ohm. Why can't I just get the current? Okay. So I'll say from Ohm's law or from the Ohm's formula, V is equal to IR. The current across the 3 ohm is going to be 10.5 divided by 3. 10.5 divided by 3, which is 3.5. And then the total current through here is not the same as 1.5. So 1.5 comes when I combine the two, I'll get my total current. So it's saying 3.5 plus 1.5, which gives us the 5 amps. Okay, 5 amps. I feel this is shorter. And as much as someone that finds the effective resistance, okay, effective resistance within the parallel combination of 3 and 7, remember it's the product and the sum. So product over the sum, which will be 21 over 10. When the voltage is still the same, so the current is going to be voltage over resistance, which is 10.5 divided by 21 over 10. And simplify that, we should be able to get 21 over 10. Okay, it also gives us 5. Okay, so whichever way, so this is a bit long. This is quite cheap and quick. All right, so whichever option you choose, guys, for as long as we get the same answer, okay? Then 8.2.3. They are asking for the power that is dissipated within the 3 ohm resistor. Power dissipated within the 3 ohm resistor. Now, since we have the current of the 3 ohm, okay, the same current within the 3 ohm, we got it as 3.5. We have our resistance as 3. All we need is the formula of power, the equation of power that has current and resistance. Formula of power with current and resistance is I squared R. So which means it's going to be 3.5 squared, okay, times my 3. So when I simplify that, that is 3.5 squared times 3. I'm getting 36.75 watts. Alternatively, I can use the voltage approach where I have V squared over R, because you know the voltage across the 3 ohm is 10.5. Okay, and then I'll divide by 3. 10.5 squared divide by 3, I still get the same thing of 36.75 watts. So whichever option you take to use, we shall be happy for you. So that is 8.2.3. Then we move on to the next condition. S1 is open. Okay, so if S1 is open, which means our main focus is just the 3 ohm. Means which one is open and which one is closed? S2 is opened. S2 is opened. So which means S1 is closed, and we shall have just the 2 ohm and then the 5 ohm. So they're asking us to calculate. No, skip the question, guys. Sorry. S1 is opened while S2 remains closed. The reading of the ammeter changes to 3.64. Can you calculate the EMF? Okay. If S1 is open, which means these 2 resistors are out, we're just focusing on the 3 ohm. And the current through would be 3.64. So I feel there is a simultaneous that we can solve. Okay, this is 8.3. From the EMF formula, we know that it's current into capital R plus the small r. Okay, we don't know the value of the small r and all of that. So initially, our EMF would have been, we say the current, the total current that is passing through the circuit. What answer do you get for 8.2.2? 8.2.2.5. So that's going to be 5 into the effective resistance for the total circuit. Remember, this is a 3, that is a 7 combined. So the product is 3 times 7 over 3 plus 7, which is 21 over 10. 21 divided by 10 is going to be 2.1. Let me just use it as 2.1 plus R. I can simplify this further so that my EMF is going to be 2.1. 2.1 times 5. That gives us 10.5 plus 5R. I can call this equation number 1. And then now when I look at the condition that I've been given, the ammeter reading changes to that. So which means my EMF currently now, the EMF, the current is 3.64. The total resistance, so the resistance external is going to be just 3 ohms plus R. Open this up. I'm going to have 3.64 times 3, having 10.92 plus 3.64 R. I can call this my equation number 2. Since the EMF is the same, I can equate equation 1 and equation 2. So that my 10.5 plus 5R is equal to 10.92 plus 3.64 small r. Let me move the r's this side, let me move the constant that side. So 5 minus 3.64 is going to give me 1.36 r. And then 10.92, when I subtract 10, plus 3.64 times 0.309, I'm having 12.04 volts. 12.04. Our focus is now the 7 ohm. combination. They're asking us, how does the voltmeter reading change? We need to choose increase, decrease, or remains the same. Okay, so what I can see is that looking at the combination, this was in parallel, okay? And we got the effective resistance to be 2.1. Now, if we remove the 3 ohm, the effective resistance is now going to be 7. In other words, the resistance external is going to be 7 ohms. So what I'm seeing is that one, resistance is going to increase. Okay, the resistance is going to increase. And if resistance increases, what happens to the current? The current through the circuit decreases. Okay, which means the V external is going to decrease. But then the V internal, which means the IR, must increase to make sure that the voltage across or the EMF is maintained. So if the internal voltage increases, which means even the voltmeter reading is going to increase. Since remember, the voltmeter is connected across the battery source. Okay, let's answer the question. So say this is 8.4. 8.4, so saying it's gonna increase. Reason being that opening S2, you can say just cuts off the 3 ohm, hence increasing the resistance external, and this decreases the current in the circuit. Okay. Therefore, the V external will decrease, but then the V internal will increase. That's the increase in the voltmeter reading. That's the increase in the voltmeter reading. All right. Question number 9. They're telling us that the simplified sketch below represents an AC generator. So guys, remember, before we move forward, motors use the Fleming's left-hand rule. Before I forget, this is motors. Generators, they use the right-hand rule. Fleming's right-hand rule. Okay, with a coil that was initially horizontal between the poles of the magnet, X and Y are 2 points on the coil, YA is one of the poles of the magnet. All right. So the question is asking us that when the coil of the generator rotates clockwise, just as indicated, between the 2 poles, the direction of the induced current is from X to Y, okay, as shown above. Is A the North Pole or the South Pole? So remember what we did when we were looking at the multiple choice question. So if I focus on this and I apply my Fleming's right-hand rule, okay, I look at the current on that side, and then the direction is upwards, which means my force is going to be moving in this sort of direction. Okay, so since this is an AC generator, this is going to be our EMF measured in volts. And this can be the time in seconds. Since it's EMF, time graph for 2 complete rotations. But they are telling us that we must start from the position of the coil as shown. Okay, so when the coil is horizontal, that's when we experience the maximum EMF. Okay, so what I'm gonna have is something like this. Okay, that is one rotation. And then I'm gonna have another rotation, something like that. So that would be my EMF time graph. In the 9.2, they're telling me that an electrical device is connected to the AC generator, and then the root mean square potential difference across is 200 volts. So RMS is 200 V. Okay. And then the maximum current. Okay. Current maximum is 6 amps. What does the question want? They want us to get the resistance of the device. So before we get the resistance, I need to change this maximum current to the root mean square current. So IRMS is going to be the same as 6 over root 2. Okay, since we know that I max is the same as IRMS over root 2. Then from Ohm's law, V is equal to IR. Since I'm looking for resistance, it's the voltage over the current. So it's VRMS over the IRMS. So 200 divided by 6 over root 2. When I punch this into my calculator, 200, not 2000, okay, over 6. And that's the root 2. I'm having 47.14 ohms. Okay, that is 9.2.1. Then 9.2.2, they want us to get the energy that is consumed. Energy that is consumed by the device in a time of 2 hours. So time is 2 hours. We need to change these 2 hours to seconds. That's 2 times 60 minutes times 60. Okay, what we get? That is 7.2 seconds. From the formula of power, we know that power will be the work done over the time. The work done over the time. Okay. What do we have? We have the power, current, and the voltage. We can use that. We want the energy. Okay, so one thing we know is that it will be the energy divided by the delta time, because we know that work done over time, we know that work depends on the energy. Okay, because under the definitions of energy, we will tell you that it's the ability to do work. That's why then the units are usually the same. So I'm going to just put it that way, so that for me to get my energy, I'll get my power times delta T. So since I have my voltage and then I have my current, I also have my resistance, I can use any of these. So I'll prefer to use the IV and then delta T. So the current that I'm using is the root mean square RMS. So that is 6 over root 2 times the 200 for the voltage from the previous question. That's what we stated. Okay. And then I'm multiplying this by my time. We said it's 7.2. So simplifying this, root 2, okay, that's times 200, and then times 7.2. I'm getting something weird. Okay, getting something weird. Let me just punch it again. Okay, so my weird answer is 6,11 times 10 to the 6 joules. Then 6,11 times 10 to the 6 joules. So guys, that is question number 9. Let's move on to question number 10, which is photoelectric effect. So in an investigation of photoelectric, light of different frequencies was radiated on each of the two metals, we have A and B. Then the graph of maximum kinetic energy of the ejected electrons from metal A and the frequency of the incident photons is shown. This is the energy. And then that is that frequency is times 10 to the 14. Then 10.1, they want us to write down the numerical value of the gradient of the graph. So it's a 1-mark question, which means it's kind of direct. So in any graph of photoelectric effect, the constant, which is the gradient in this case, is what we call the Planck's constant. Okay, and Planck's constant is usually given as 6,63 times 10 to the negative 34 units. Okay, 6,63 times 10 to the negative 34. That is the gradient. Then 10.2, they want us to define what work function is. Work function is basically the minimum energy. Okay, the minimum energy that is required. Minimum energy that an electron in the metal its minimum energy that an electron in the metal needs, okay, or the minimum energy that a metal needs for an electron to be moved off its surface. I don't know, that's better. Remember, work function is just the minimum energy, the minimum work that must be done to remove an electron from a metal surface. So whichever way you put it, but there has to be minimum involved. Minimum energy that is needed. Minimum energy needed to remove an electron from a metal surface. Okay. Then 10.3.1, they want us to get the work function of A. So usually, where the graph starts from along the horizontal axis, that represents the minimum frequency, or the frequency of the work function. So we know that work function W naught is given as H times frequency naught, because this 5 represents our frequency naught. So Planck's constant is 6,63 times 10 to the negative 34. Then we are multiplying this by, and so we're multiplying by 5 times 10 to the 14. Is that true? Yes. Okay, so what I'm going to do is just punch this into my calculator. 6,63 times 10 to the negative 34. I'm multiplying this by 5 times 10 to the 14. I'm having a weird answer, guys. Again, which is 3.32 times 10 to the 19, but negative. That will be joules, since it's work function, work done. Okay, so guys, we're done with, oh, we're not done. They told us the work function, okay? So we got the work function as 3.315 times 10 to the negative 19 joules. We know that our E is going to be H multiplied by the frequency is equal to the work function plus the EK max. Okay, so at the point of EK max, where we need our E, we can see that the frequency is 12.54. So I'm going to say 6.63 times 10 to the negative 34 times the 12.54 times 10 to the 14 is equal to our work function, which is 3.315 times 10 to the negative 19 plus the EK that we want. Okay, then we multiply on the left. I'm getting something like 8.314 times 10 to the negative 19 is equal to 3.315 times 10 to the negative 19 plus the EK. Then I can move this that side, and then I'll subtract. Okay. When I insert this into the machines, 8.314 times 10 to the negative. Okay, what's happening? Saying 8.31. We said 1414 times 10 to the negative 19. Okay. We're subtracting 3.315 times 10 to the negative 19. That becomes 4.999 times 10 to the negative 19. So if I round these two decimals, it's just going to be 5 times 10 to the negative 19 joules. We're looking for kinetic energy. Okay, then the next question. The next question, which is going to be 10.4. 10.4. 10.4, 10.4. Okay, so 10.4, how will each of the following be affected if the light of the frequency 12.54 times 10 to the 14 hertz, but of a higher intensity? So we're using the same sort of frequency light, but the intensity is the one that changes, okay? How will this have an effect on the value of X? So now one thing we need to know that under the factors that influence kinetic energy, intensity is not one of them, okay? So in this case, it's just going to be the same. The kinetic energy is going to be the same. It has no effect on the intensity, or kinetic energy is not affected by intensity of the light. And then 10.4.2, how about the number of photoelectrons emitted per unit time? So this will increase. Okay, these are going to increase because as the intensity increases, which means the number of photons that are being released will also increase. Then 10, they are telling us that metal B has a larger work function than metal A. it has a larger metal function. It has a larger work function than metal A. Can you redraw the graph above in answer book, not include values? On the same set, sketch the graph of B and label this. So one thing we know that one thing that we discussed before, we said work function is directly proportional. Okay, said work function is directly proportional to the frequency. So if the frequency is high, which means even the work function is going to be high. And then if the frequency is small, which means even the work function is going to be lower. So from the graphs, okay, I don't need to draw. I'll just maybe just use this. If this is our graph A, okay, with this sort of work function, the graph B has a higher work function, which means it must be drawn somewhere there. And then we call this a B, because let's say if this is a frequency, if this frequency is high, which means even the work function is going to be high. So in your drawing, in your answer book, all you needed to do is just draw something like that and draw something like that. Call that A and call that B. So this is the frequency of A, and then this is the frequency of B. So guys, that's what we had to do, and that is what will be expected of us. So thank you very much for watching. Let's meet in the next paper. Thank you. Hello, welcome to this episode where we shall be talking about physical sciences, paper 1, the May, June 2023. The paper was out of 150 and the duration was 3 hours. Okay, the instructions will always be the same. The paper is having 10 questions. Try to see what could have been done in this paper. Remember, this is just the suggested memorandum. It's not the official one. Okay. So question number 1, which is the multiple choice, they're telling us that various options are provided. We know that. Then 1.1, a constant net force is applied to a block. Okay. Now, which one of the following is correct? Okay. Is the block going to move with a constant velocity? No. So that is out. Is the block going to move with a constant acceleration? There is some bit of truth in that. Then will the block move with a constantly increasing acceleration? No. Constantly decreasing? No. So for as long as the net force is constant, which means the acceleration, is the block going to increase? No, the acceleration will be constant, will not increase. So B would be my option for 1.1. Then 1.2, they're telling us we have a crate of mass M that is stationary on a plane inclined at an angle of theta with the horizontal. Which of the following statements regarding the magnitude of the frictional force that are acting on the crate is correct? So one thing we know is that the forces that are acting on this object will be the FG parallel. Okay. And since there is no other extra force, let's say the applied force or anything of that sort, we expect this block to slide down. But since it is stationary, which means the frictional force should be acting upwards to keep this block in one place. Okay, so they're telling us that the magnitude of the frictional force acting on the crate is equal to the component of the weight, which is parallel. That is correct. Let's explore the other options. The frictional force is greater than the weight. So if frictional force was greater, then what would that mean? Then this object would be sliding upwards, so which doesn't even make sense for me. Okay, frictional force is equal to the component of the weight that is perpendicular. So the perpendicular part is wrong. And then is larger than the component of the weight. Frictional force is larger, that is perpendicular. So the perpendicular part also makes it wrong. Okay, so between option A and B, but in this case, since the object is not moving, I'll choose option A, since the net force is gonna be 0. Is that true? But that is my option anyway. If you have anything different, please, you can slot it under the comment section. Then the next one, 1.3, they are telling us there's a ball that is projected vertically upwards from the top of the building. Points P, Q, R, and S represent the different positions during the motion of the ball shown in the diagram. Okay. So if you are ignoring the friction effects, between which 2 points will the ball undergo the greatest change? Okay, so greatest change in kinetic energy. So we know that for kinetic energy, okay, let's say the change, if you have m, you can say v final minus v initial, you can even square that, or you can just look at it independently. Vf squared minus the vi squared, this multiplied by half m. So if we look at P and S, if this object has a velocity, which we know, let's say, because we're not dropping this object, we are throwing it up with some magnitude of velocity, okay? Unless we also have this, the change between P and S is not that significant, okay? Let's look at P and R between this. It won't make it, because we know that at S, this ball or this object will have the greatest velocity, okay? The V maximum will be at S. Then at Q, that's when the body is gonna have the V minimum, the minimum velocity. So this maximum and the minimum, we know the minimum velocity is gonna be a 0. So this change of the maximum and the minimum will be the greatest. Okay, then 1.4, telling us a ball is dropped from a height h, okay, and strikes the floor with a momentum v. The ball is then dropped from a height which is a half of h. If we are ignoring friction again, which of the following represents the momentum of the ball when it strikes the floor after being dropped from that? So what we need to look at in this case is basically, we can look at the formula of momentum where we have mass multiplied by the velocity. But we don't have the velocity. We know that the ball is just having the same mass, whether dropped from h or half of h. So if I try to kind of look for the velocity and I use the v final squared is equal to, I can use v initial squared plus 2 multiplied by g delta s or delta x for the displacement. In this case, it can even be a delta y since we're moving in the y direction. Now, since we are dropping, I'll take g to be positive in this case, and our initial will automatically be a 0. So if I consider the h, okay, so at height h, my v final will be the square root of just this, since that is a 0. So 2 times 9,8, I'll just say h. Okay, let me call this, why can't I say vh? We're saying 2 times 9,8h and the square root. Okay, then I'll do the same thing for v when it is a half of h. I'll still be left with the same thing. So this will be a 0 again, since I'm just dropping the object. Then I'm going to have 2 times the 9,8 times now the half of h, which is h over 2. Okay, so then for me to simplify that, I can see that this 2 is going to cancel that, and I'm only going to be left with 9,8h under the root sign. Now, if I try to get the momentum, the masses are the same. So basically, I'm comparing. If I call this P1, Okay, it's going to be √2 multiplied by the root of 9,8h. Okay, and then my P2, which is the momentum at a half, is going to be, let's just call this one. That's the way they're calling it. That this whole thing is a P. And then momentum 2, we just have the 9,8h multiplied by the mass. Now the question wants us to compare this second momentum. How does it relate with the first one? Okay. So we can see that we have this and we have that. The only difference that we don't have is the square root of 2. So the option that I'll go for will be a P, because the second momentum will be half or 1 over √2p. Okay, then 1.5, they're telling us a box moves on a horizontal surface. Diagram below shows all the forces acting on the box. Which of the following combination of forces will do the work on the box? Now pay attention to the direction. So we're looking at moving on a horizontal surface. So it's moving horizontally. Regardless of the direction, fine, horizontal. So our interest will be basically the horizontal forces. Okay? So we know that this Q will have a component of the Q cos of the angle of inclination, okay, that will act horizontally. So the forces that are going to do work will be basically this S, and I'm seeing this Q. Is there friction? There is no friction in this case. Okay. Work will not be done by the weight, work will not be done by the normal force, since those are vertical forces. So I'm gonna go for S and Q. So the option I have is Q and S in that case. Then 1.6, a train that is moving at a constant velocity towards a stationary listener emits sound waves at a constant frequency. Which of the following statements about the sound waves observed by the listener is correct? Now remember, the listener is stationary, not moving. So as the train is approaching this listener, we expect the frequency to increase, okay? And if the frequency is increased, which means the lambda, the wavelength, must be smaller or shorter in that case. So let's see, they're telling us that the observed frequency is higher than the emitted frequency. That makes sense. They're telling us that the wavelength is longer, which is wrong, because we said if the frequency is high, the wavelength must be shorter. And the frequency is lower, no. The wavelength is equal to the emitted wavelength. That is also wrong. So I'll go with option A. And then 1.7, if we are referring to the diagram below, they're telling us Q and R are small spheres that are suspended by light insulated strings. When a negatively charged rod is brought close to Q, sphere Q is repelled. And then when a negatively charged rod is brought close to R, there is attraction that takes place. So which of the following combinations below can be possible for the nature of that? Now, we know about the signs or charges, that like charges will repel and then unlike charges will always attract. So automatically, since Q is repelling a negative rod, Q will be negatively charged. Okay. Now, with attraction, there are two scenarios. Attraction can take place between two opposite charges, let's say negative and a positive. But attraction can also take place between a negatively charged rod or charged sphere or object and a neutral object as well. Okay, there will still be attraction. So R can either be positive or it can be neutral. But we're saying Q is a negative. So where is Q negative? We have option A, and then we have option D. Then we're saying R we only have two options. It's either positive or neutral. So A is out. We shall go with D. Okay, then 1.8, 4 voltmeters, V1, V2, V3, and V4 are connected in the circuit as shown below. So which voltmeters will have the same reading as V1? So our focus is V1 that is connected across the terminals. So connected across the positive and the negative. So when you look at V2, V2 cannot have the same reading since it's just connected, not across the terminals. V3, I feel is the correct option because connected across, okay? We have the positive and then we also have the negative this side, for as long as the switch remains open. So V3 becomes the option because V2 and V4 are basically in the same sort of scenario. So this is out, that's out, and then that is also out. So B would be my best option for that. Then 1.1.1.9, they're telling us that a split ring commutator connects the coil of a generator to the external circuit. Okay. Which of the following combination is correct of the magnitude and direction of the induced current within the external circuit? So focusing on the generator and then about the external circuit. So the magnitude of the induced current, since, so we need to ask ourselves, which generator uses the split ring? Is it an AC or a DC? Okay. If we can tell that, then we shall be able to look at this or to determine that. So the generator that uses the split ring, remember for the motor, is the DC motor that uses the split ring. Okay, but then which generator uses the split ring? Okay, so since we have a split ring commutator, I'll go for a DC generator. Okay, and with the DC generator, what we know about the magnitude of the induced current is gonna keep on changing. Okay, so I have option C and D for the magnitude of induced current. But the direction, since it is a direct current, it has to stay the same. Okay, so option C would be my best. It would change if it was an AC. Then 1.10, light of a suitable frequency is shown on to the surface of a metal and electrons are ejected from the metal. Which of the following is equal to the ratio of the work function to the threshold? So from our formula page, we have something like this. Work function is equal to H times F naught. Okay, so they want the ratio. It's like we are dividing W naught over F naught, the threshold frequency. So this will only be left us with H. And this H is what we call Planck's constant, which is A in that case. So that is question number 1. Question number 2. Question number 2. They are telling us that two blocks A of mass 4 kgs and then the 9 kg are connected by a light string. The blocks are held at rest on a plane which is inclined at an angle of 35 degrees with the horizontal. There's a constant force F that is acting prior to the plane applied on B, as shown in the diagram. Okay, state Newton's second law in words. Wow. Okay, so what we need to say is, okay, we shall say that if a resultant force, okay, if a resultant force acts on an object, or we can simply say that an object experiences a resultant force that causes it to move. Okay, so in this case, I'm saying when a resultant force okay, acts on an object, it causes it to accelerate in the direction of the force, okay, and then the acceleration is directly proportional, okay, and then the acceleration is directly proportional to the force, and the acceleration is directly proportional to the force. So that's how we need to just put it up, okay? So when the resultant force acts on an object, it causes the object to accelerate the direction of the force, and then the acceleration is directly proportional to the resultant force. Acceleration is directly proportional to the resultant force. Okay, so we can stop there, or you can even add the inverse proportion to the mass and all of that. Remember, that is F net is equal to ma. That is Newton's second law. The acceleration is directly proportional to the net force. Okay, so that is 2.1. Then 2.2, they want us to draw a free label diagram, okay, that are acting, or for the forces that are acting on object A. So when I look at object A, it's on an incline, so there is this tension. I'm going to have the FG parallel, and then is the incline rough. Okay, so we're not told whether the incline is rough or what, but definitely, no, we have it here. They told us the kinetic friction, so it's rough. Okay, so I'm going to have the FG parallel. I can have the FK there for the kinetic friction, and then I can have my tension. I can have my Fn for the normal force, and then I can have the weight there. So it can be in that format, or you can just do it just in this sort of format. What's wrong with you? Something like that, for as long as you indicate the forces correctly. So that will be tension. We're going to have the Fg parallel, the frictional force, the normal force, and then that is the weight. Something like that. So at least 1, 2, 3, 4, minimum of 5 forces, a minimum of 4 forces, maximum 5, no problem. Then 2.3, they want us to get the tension in the string. So for me to get the tension, since I have my frictional force on A as this, okay, I can get my FG parallel, and then that, yeah, so I can basically look at just body A, okay? So I'm going to say when I look at body A, let me just redraw my, so we say that is tension, this is FG parallel, this is FK, the normal force, and then the weight. Okay, so since the motion is just along the incline, I'm just going to focus on the tension and then these two forces. So I'll say my F net is equal to MA. Do we know the acceleration? Yes, they told us that the block is accelerating like that. Perfect. So my F net, I'll say T minus or plus, and then I'll indicate the negatives this side. So I'll subtract my Fk, I'll subtract my Fg parallel is equal to the mass times the acceleration. So my tension will be the mass acceleration plus the Fk plus the Fg parallel. Okay, so this mass, the body is having 4 kilograms, okay? So that is 4 multiplied by the acceleration, which was a 2. So 4 times 2 plus my frictional force was 5.88. Okay, that's 5.88 plus we know that Fg parallel is given as mg, the sine of the angle of inclination. So that is 4 times 9.8, the sine of 35. Okay, I don't need to indicate this, the cos 180 on the frictional force since I've already been given the magnitude. Okay, so when I punch this into my calculator, let's see what we shall have. So that is 8 plus 5.88, come on. Plus I have
4 times 9,8 sine of 35. Is the inclination 35? Perfect. What are we having? I'm having 36,36 newtons. So that is my tension force. Okay, so if it is a 36,36, now they want us to get the force, which is a 3-mark question. So with the force, I can just look at the block B. Okay, the free body of block B is going to have just the force applied. We're going to have the friction. We're going to have the FG parallel. And then we're also going to have the tension. Yeah, basically. So I'll say body B. When I look at body B, so I'm saying my F net is equal to MA. So it's saying our applied force minus the FG parallel minus the frictional force minus the tension must give us the MA. So F will be mass acceleration plus the tension plus the frictional force plus the FG parallel of that block B. So since the block is having 9 kilograms, that will be 9 multiplied by 9,8. The tension we got was a 36,36. The frictional force on that body is 13,23. Okay. And then the FG parallel, remember it's mg sine of something. So that is 9 times 9,8, the sine of 35. Okay, so when I just punch that into my calculator, 36,36 plus 13,23 plus 9 times 9,8 sine of 35. Okay, I'm getting 188,38 newtons. Okay, that's just one approach. The other approach would be for someone to just consider the entire system, whereby you get the F minus the frictional force of A minus the frictional force of B, then minus the FG parallels of A and B all together. And you equate it to, wait a minute, I think this is wrong. Why am I using 9,8? It has to be a 2. Sorry about that, guys. It's a 2, not 9,8. So it's going to change this entire thing. Let's change that to a 2 because the acceleration is 2, not 9,8. Not looking at G. So it's just 118,18 newtons. 118,18 newtons. So that is the force. And then they're telling us that the angle that the plane makes with the horizontal is now decreased. So in other words, it's somewhere there. So what normally happens is that a decrease in the angle will lead to an increase in the frictional force. That we need to know, because when you look at the slope has decreased, which means a lot of work needs to be done to move this thing downwards. So how will this change the kinetic frictional force on block A? So I'm going to say it's going to increase. Okay, because when the slope is high, the block can easily slide down. Okay, so what is the explanation? So we know that the frictional force is given as the mu, which is a constant, times the normal force, which normal force is given as mg cos of theta. Okay. So you can say that increase in the theta, no, it's a decrease, it's not an increase. Okay, so a decrease in theta leads to an increase, let's say in cos theta. Okay, so if the cos theta increases, which means the normal reaction
Okay, normal reaction will increase, and we know that kinetic friction is direct proportional to the normal reaction. That's the increase. That's the increase in the kinetic friction. Okay, so this cos theta affects our normal reaction, since mass and the gravity will be a constant. Okay, so that is question 2. Let's move on to question 3. I'm telling us that there's a ball of mass 0.5 kilograms that is thrown vertically upwards from the top of the building, which is 15.3 meters high. The ball reaches maximum height of that much above the top. Okay, as shown in the diagram. Then the question is asking us to define what free fall is. So we know from our notes that free fall is basically a motion that is under the influence of acceleration due to gravity entirely. Okay, so motion of an object, that is entirely under the influence of gravity. Motion of an object under the influence of only the acceleration due to gravity. Or you can just say just under the influence of gravity, something like that, or motion under the force of gravity only. Motion of an object under the influence of only gravity. That is free fall. Then 3.2, they want us to use the equations of motion to calculate the speed at which the ball was projected. So they want the V initial. So I'm just gonna use just this first section, okay, of the motion. Since I know my displacement, the change in Y, as 5.89, I know that my V final is a 0 because that's the maximum height. And then I'm looking for the initial velocity. So using just equations of motion, so the best I can use is the Vf squared is equal to Vi squared plus 2G, I'll say delta Y. So our Vf will be a 0. And then our Vi is what we're looking for, plus 2. I'll take the G to be negative in that case. So that's going to give me negative, and then times the 5.89. Okay. When I transpose, V squared is equal to, I'm having 2 times, that's 19.6. Okay. Having 2 times 9.8 multiplied by 5.89. That is giving me 115.444, and then I can take square roots. Okay, so square root of the answer, I'm getting 10, so my Vi becomes 10.74 meters per second. Okay, so that's what I'm getting, 10.74 meters per second. Okay. Then they're telling me that after the collision with the ground, the ball leaves the ground with a speed of 11.92. Now they want us to calculate the amount of kinetic energy that is lost. 5 marks. So for me to get the amount of kinetic energy lost, I need to find my final velocity. So final velocity, I can either start from the maximum point, whereby my initial velocity is a 0. Then from there, I can focus on my last velocity at this point, which will be the Vf. Then I look at this distance, the 15.3 plus the 5.89. That's going to give me 21.19. So if I say that my displacement, okay, is 21.19 meters, I don't have the time, I only looking for the Vf, my Vi is going to be 0 in this case. So I can still use the same equation of Vf squared is equal to Vi squared plus 2G delta Y Okay. Now, since I'm just looking at a portion of the motion of the ball, I'll just assume that this is a different trajectory, whereby now my direction is downwards. So I'll take it to be positive. So my VF squared is equal to my VI, which is a 0 squared, plus 2 times 9,8 multiplied by my change in displacement, or my displacement, which is 21,19. I multiply that and find the square root. Okay, that's going to be 2 times 9,8 multiplied by 21,19, which gives me 415,324. Okay, square root of the answer, I'm getting 20,38 meters per second. Now, this is just the final velocity. Now, they're telling us that when the velocity, when the ball leaves the ground, it's having this much. So it's my choice to determine the kinetic energy with which the ball hit the ground, and then the kinetic energy with which it leaves, and then I can subtract the two. Okay, so let's see. This is 20,38 is 11,92. Okay, times the mass, which is 0,5 and 0,5. Okay, so let's see. So for EK final, it's going to be a half mv squared. That's a half. The mass is a half also, multiplied by my velocity, which is 20,338. It's 38. I square that, then I'm subtracting a half, multiplied by a half, times the velocity, which is 11,92 squared. Okay, they want the energy that is lost. So a half and a half, let's just make sure it's a half. Okay, a half and a half multiplied by, it's 20,38 squared. Oops, I'm subtracting a half times a half, multiplied by 11,92 squared. So that is giving me 68,31 joules, since it's energy. Okay, then 3.2, calculate the time that is taken for the ball to reach point P. Now we know that point P, that is now the bounce. Okay, the velocity with which the ball left, in that case, is 11,92. They gave it to us. So our initial is 11,92. Our final, since P is the maximum point of the bounce, is going to be a 0. We're looking for the T. Okay, but we know that our G is 9,8. So you can use that first equation of motion. So V final is V initial plus, we can say 80, which 8 is going to be our G. Okay, so our V final, we're saying is 0. Our initial is 11,2 plus, that's going to be negative 9,8 T, since the ball is moving upwards. I'll transpose, so my T will be 11,92 divided by 9,8. 11,92 divided by 9,8, that's giving me 1.22. Okay, so T becomes 1.22 seconds. Then 3.4, there is a velocity time graph for the motion of the ball. Okay, from the instant it was projected and up until it reaches point P. So write down the numerical values indicated by each of the following. So K is the velocity with which the ball left the ground, which we said is 11,92. They gave it to us, but then that would be meters per second. Okay, then they want us to get L, which L is the initial velocity, which initial velocity is what we calculated to be 10,74. So that is a 10,74 meters per second. And then the difference between T2 and T1, remember T2 is the time, let's say the difference, T2 and T1 is basically the time that is taken for the ball to move from the ground up to point P, which we got as 1,0 to 2 seconds. So that is question number 3. Question number 4, a wooden trolley of mass 2.7 kilograms moves to the left with a constant velocity of 3 meters per second. A bullet of mass 0.03 kilogram is fired horizontally from the left into the trolley. Then the bullet strikes the trolley and comes to rest in 0.02 seconds. The average net force exerted on the bullet is this much. The bullet trolley combination will move to the right as indicated in this diagram. So if we are ignoring the friction and the rotational effects, they want us to write down the magnitude and direction of the average net force that the bullet exerts on the trolley. Now, since, okay, from Newton's third law, since the trolley is moving to the left, the force that the trolley exerts on the bullet will be in that direction, but it will be of the same magnitude. So we're going to say 591 newtons. Wait. Write down the magnitude and direction, average force that the bullet exerts. The bullet is moving to the right. So we're gonna say to the right. Exerted by the trolley and the bullet is this. So the trolley will be to the left, this will be to the right. Okay. And then 4.2, calculate the magnitude and the velocity with which the bullet strikes the trolley. Okay, so with 4.2, this is what I said. I looked at my F-net being the change in momentum, the rate change in momentum. Okay, so since our F-net is 591, change in momentum will be the mass, V final minus V initial, something like that, then over the time. So we know that the mass, I'm just focusing on the bullet, is 0.03. Our final was a 0 since it came to rest. Our initial is what we need. Is that true? Yes. And then we are dividing it by the time, which is 0.02 seconds. Okay, so when you do the magic with the calculator, that's gonna be 591 times 0.02 divided by 0.03. Okay. So that's going to be 591 times 0.02 divided by 0.03. I'm getting 394 meters per second. So that's how fast this bullet was moving. But now, since we're having a negative sign, which direction? Wait, does that make sense? Magnitude? No, they want just the magnitude. So that is moving in the opposite direction of the trolley. Okay, then 4.3 state the conservation of linear momentum in words. So we know that in an isolated system, saying isolated system, the total linear momentum is constant. In other words, there is no change. Momentum before is the same as momentum after, as long as we don't have any extra forces. All right, then 4.4. They're telling us to calculate the magnitude of the velocity of the bullet trolley combination after the collision. So when we look at this, okay, we can use the conservation where we say the mass of the bullet, the VI of the bullet, plus the mass of the trolley, the VI of the trolley must give us the mass of the bullet plus the mass of the trolley multiplied by our V final. It's a combined velocity. So why am I even saying this? It's okay, no problem. So we know that the trolley, which of the two are stationary? A bullet, no, nothing is stationary. So both of them are moving. So the mass of the bullet is 0.03. Our velocity was 394. plus the mass of the trolley was 2.7. The velocity, I'm going to say -3 since it's moving in the opposite direction. Okay, this must give us the combined mass. So that is 2.7 plus 0.03. That gives me 2.73 F. Okay, when I do the magic, simplify that, multiply by 0.03, I'm getting 11.82. I'm subtracting 8.1 is equal to 2.73 VF. When I subtract 11.82 minus 8.1, I end up with 3.72. And then I divide by 2.73. That will give me my VF value. Okay, 2.73, which gives me 1.36. 1.36 meters per second. So that becomes my velocity of the combined system. So guys, that is 4.4. All right. Then question 5, they're telling us that we have learners that conduct an experiment to determine how the kinetic energy given to the trolley affects the distance that the trolley moves. Okay. The experiment is repeated with a trolley that is moving on the same rough horizontal surface, but with different initial kinetic energies at point A. So we are ignoring any friction or any rotational effects of the wheel. And they want us to draw a free body diagram showing all the forces that are acting the trolley during the motion after passing A. So we expect this to be a rough surface. So which means since we have kinetic energy that is pushing the trolley forward, but it's not acting. Remember, it was pushed up until point A, and then it was released. So we're going to have the weight, we're going to have the normal force, and then we're going to have the frictional force is acting in that direction. Okay. Then name the independent. So independent, which is not affected, will be the kinetic energy. So initial kinetic energy is going to be my independent variable because it depends on the amount of kinetic energy. Then state the work energy theorem in words. So we know that the net work done, okay, net work done is equal to the change, is equal to the change in kinetic energy. Net work done is equal to the change in kinetic energy. All right, so that is question number 5. Ne? Then question number 6. Question number 6, they're telling us that an ambulance is moving away from a stationary listener. Ambulance is moving away from a stationary listener. So I'll say velocity of the listener is a 0. The velocity of the source is that much. Okay, then the siren of the ambulance emits sound waves that are having this frequency. Why don't I do this? Velocity of the listener is 0, velocity of the source is 25, frequency of the source is 550, then frequency of the listener is 512.64. And then the first question is asking us to state Doppler effect in words. So we know that Doppler effect is more like the apparent change in the frequencies. Okay. So how do we put it in words? How do we put that in words? Okay, so we can say that the change in the frequencies, the change in the frequencies, does that make sense? a change in the frequencies. What did we say? Let me see what I wrote on my paper. Because Doppler effect is the apparent, I just say the apparent change. Okay, in the observed frequency, and why don't we say the apparent change in the frequency observed by the listener, apparent change in the observed frequency by listener due to the relative motion. Okay, relative motion of the source, relative motion of the source and the observer. Okay, so there's going to be a change in the observed frequencies because of the change in the motion of the observer and the listener. Okay, so then 6.1.2, they want us to use the information to calculate the speed of sound. Okay, I'll just jot it down here. So we know that frequency of the listener from the Doppler formula is plus minus velocity of the listener over V plus minus velocity of the source times the frequency of the source. Now, since this ambulance is moving away, so we expect the frequency observed to be low. So which means it's going to be V plus. Is that plus? No, it's going to be a minus. That's going to be a minus. VL over V plus Vs. Okay, multiplied by Fs. Now, when do the substitution, the frequency of the listener is 512.64. My velocity is what I need, minus velocity of the listener, who is stationary, which is 0, over V plus the source is moving at 25 meters per second, multiplied by the frequency that is produced, which is 550. Okay, let's do the math now. Divide both sides by 550. So 512.64 divided by 550 will give me V over V plus 25. Okay, so now simplify this side. I'm having 0.93207. I multiply by that. I'll be left with just a V. Opening this up, 0.93207 V plus this is going to be a 23.302 is equal to V. Then move this to that side to be a subtraction. Okay, so I'll be left with a 0.0679 V is equal to 23.302. Divide both sides by the 0.0679, divide by 0.0679. That cancels that. So which means my V is a 343.04 meters per second. Here we're not rounding off. So yeah, it's round about that because we know that the normally given value is 340. So it makes sense. Then 6.1.3. If the ambulance moves away from the stationary listener with a constant velocity, which is greater than 25, how will it affect, or how will each of the following change? Okay, we just have to use increase, decrease, or remain the same. So the speed of sound will not be affected whether the ambulance is moving towards or away. So this, we're gonna say remain the same. Okay, the frequency of the sound waves, frequency of the sound waves remember, is the velocity that is making an effect. The frequency is still not affected by the velocity. So I'm still gonna go with remain the same for the second part. Okay. Will that make sense? Let's see. Frequency of the sound emitted. This V is velocity of the source. So how does velocity of the source relate to the frequency of the source? So velocity of the source is directly proportional. Okay, we would take increase here, but because now if the frequency that is detected, so which means I'm gonna say increasing. And then the frequency that is detected by the listener, this one is going to decrease. Because the velocity is gonna be moving at a faster rate. And we know that frequency of the listener is inversely proportional to the velocity of the source. So if this one increases, this one must decrease. For the second part, yes, I'll stick with the increase because velocity of the source is directly proportional to the frequency of the source. Okay, then 6.2. 6.2, they're telling us that the spectrum of a distant star, when viewed from the Earth, is a redshift. So we need to know, what is a redshift? Okay. So we know that a redshift is more like if light from the galaxies is shifted to longer wavelengths. Okay. So what this means is that the wavelength is increasing. So if the wavelength is increasing, then it will be moving away. I don't know if that is a redshift. Is a shift from shorter wavelength towards the longer. So I'm just gonna take moving away. So away from. And then what will be the explanation is just gonna say the increase in the wavelength. Increase in the wavelength. So just explain what a redshift is for 6.2.2. Okay, so you're moving from shorter wavelength to longer wavelengths. Okay, there is an increase in the wavelength. I don't know, just put it in some nice English there. Then question number 7. Question number 7. They're telling us that 2-point charges A and B, each with charge 3 times 10 to the negative 9 coulombs, are stationary on a horizontal surface, R meters, 2 R meters, and so on and so forth. Define what an electric field is. So electric field is just a region of space. Okay. It's a region of space in which a charged particle experiences an electric force. It's a region of space in which charged particle experiences an electric force. Then draw the resultant field pattern due to charges A and B. So we can say that both charges are positively charged. So we expect repulsion to be taking place there. So we can say that is A, and then that is B. And just draw spheres, but it's fine. Let me use the dots. There's no difference. So that is A, and then that is our B. What's happening now? It's acting up now. This thing is acting up on me now. Okay, so the repulsion, we're gonna just draw something like that. Have that and that. Doesn't matter. The field lines could be the same. So just need to show the arrows moving out. Okay, just something like that. You can draw the sphere or remember these out point charges. So it's better I use that. I can call this A, then I can call that B. For as long as there is a repulsion that's taking place, that's what's going to count. Then the magnitude of the net electric field at P is given as 27 Newton per Coulomb. Calculate the value of R. So we know that the formula of electric field is given as E is equal to KQ over R squared. So I'm going to calculate the electric field at P due to A. So I'm going to say EA. That is KQ. Let me just substitute 9 times 10 to the 9. The charge is 3 times 10 to the negative 9 over. That's going to be R squared because the distance between A and P is just R. Then I do my magic with the calculator. So that is just the 27 over R squared. Okay. Then I'm going to look for EB, the electric field at P as a result or due to B. So that's going to be still be KQ over R squared. That's 9 times 10 to the 9. That's 3 times 10 to the negative 9. But the distance is going to be twice R squared. And I simplify that. I'm just going to get 27 over 4R squared. Now, I need to know the direction. Okay. So one thing I know that since this point charge is a positive, there's going to be repulsion that is taking place. So at P, the first force A, the EA will be acting east or to the right. And then the EB, that's also going to be repulsion. So which means it's going to be acting to the left. But then the net is a 27. So I'm going to say my EA plus my EB must give me 27 Newton per Coulomb. So my A was a 27 over R squared. My B is now negative 27 over 4R squared. Is that true? Is that true? I think it is true. Then it's equal to the 27. Then we just need to simplify. So the 27, 27, 27. So what I can do, I can multiply through by 4R squared. Okay, so that I don't have to work with denominators. So multiply by 4R squared, multiply by 4R squared, multiplied by 4R squared. So this cancels that. This R squared cancels that R squared. I have 27 times 4. Is it going to make sense? It's fine. Let me just do it the hard way. Okay, that's going to give me 108. I'm subtracting a 27 is equal to 108 R squared. So 108 minus a 27, I'm getting 81. Okay, so 81 is equal to, let me just, okay, it's fine. Let me not rush it. Over 108 over 108. So that cancels that. So R squared, let me just say R is the square root of 81 over 108. So square root of 81 over 108, that's going to give me 0.866 meters. Did they tell us centimeters or meters? Meters, okay. So which means that is my value of R. All right, then 7.3. They want us now to calculate the magnitude of the net electrostatic force that an electron would experience at a point P. So we know that F is K Q1, Q2 over R squared. Okay, that's electrostatic force. But if we look at this, this will give us what we call the electric field. So which means the force must be electric field multiplied by the charge of interest. Okay, because electric field is the force over the charge of interest. So you can use small q. But now, since we're focusing on an electron, we're going to get the net electric field, which is the 27, multiplied by the charge on an electron, which is negative 1,6 times 10 to the negative 19. Okay, when I simplify that, I'm getting 432 times 10 to the negative, yes. I'll just say 4,32 times 10 to the negative 18. That is going to be newtons. So that is how I would get that. So that is question number 7. Question number 8 is electricity. They're telling us that the circuit diagram below shows a battery with an EMF of 12V and an internal resistance of 0,5 ohms connected to 3 resistors. There's a light bulb, a switch, and an ammeter. Okay, connecting wires. The ammeter and connecting wires have negligible resistance. Now they want us to state Ohm's law. What is Ohm's law, guys? So we know that the relationship between that the potential difference across a conductor is directly proportional. Okay, so across the conductor is directly proportional to the current, directly proportional to the current at a constant temperature. At a constant temperature. So you can just design it or reframe it in a way, but we know that V is equal to IR. Okay, so this PD, which is the V, is directly proportional to the current at a constant temperature. Okay, then they're telling us that switch S is initially closed. Okay, just the way it is. Now the question wants us to get the total external resistance. Okay. There are 2 ways to this. Okay. They give us the EMF. Yes, they gave us the EMF. Which is that? Do we know the current? We don't. So which means we need to go the long way. So we know that this pair is in parallel. But then this pair and this are going to be in series because this bulb is having also some bit of resistance. Okay. Then the result we get is going to be in parallel with the 15 ohms. So what I normally do with 2 resistors in parallel, for me to get the effective resistance, if I call this A, I'll just get the product over the sum. So that is 10 times 10 divided by 10 plus 10, which is a 20. So 100 divided by 20, I'm just going to get 5 ohms. Okay. So that is 5 ohms. So which means that this combined pair is giving me just 5 ohms. Now, when I look at these 5 ohms and the light bulb, they are in series. So I'll get the 5 ohms plus the 10 ohms, which gives me the 15 ohms. So this entire part can be reduced to just the 15 ohm combined. Now, this 15 and this 15 are in parallel. So I'll say R3 and RL, they're in parallel. So I can still do the same thing since I'm looking at just one resistor. So the product over the sum again. So that is 15 times 15 divided by 15 plus 15. So 225 divided by 30. Is that true? 15 times 15 is 225. Dividing it by 30, I'm getting my effective resistance to be 7,5 ohms. So the answer for this is just going to be 7,5 ohms. That's how you get the 5 marks. Okay, so start by getting the effective resistance of this parallel, combine it with the bulb that is in series, and then combine them. All right, then the reading on the ammeter. Where's the ammeter? The ammeter is here just reading the current. So for me to get the current, I'll just use my EMF formula and say that EMF is given as the current into R plus small r, which is the internal resistance. So my current will be the EMF over capital R and small r. So that is a 12 over the 7.5 plus the 0.5. That is 12 over 8. So 12 divided by 8 is giving me 1.5 amps. So that is my current, or that is the reading of the ammeter. Then the power that is dissipated by R3. So we need to know where our R3 is. So R3 is this 15. Okay. So what is happening there in R3? So what we need to do, how many marks is 4 marks? So we need to first of all get the voltage. Okay, the voltage that is across. So remember, this entire top part is going to be in parallel with this bottom part of the 15 ohm R3. So which means the external voltage is going to be the same across. So let me get the voltage. Is that going to make sense? Yes, it will make sense. I need to get the voltage of the internal. So which means my EMF is equal to V external plus the V internal. So from the EMF formula, I have my IR plus my I small r. So my I small r is going to be 1.5 times the 0.5. Okay, 1.5 times the 0.5, I'm getting 0.75 V. And then I'm just going to subtract this from the 12. So which means my V external is going to be 12 minus 0.75. Okay, that is going to give me 11.25. So remember we said since they are in parallel, within a parallel combination, the voltage is always constant. The current will change. Now, since we have our voltage, we need to look for a power formula that combines voltage and resistance. And the power formula I found was the V squared over R. So our V squared will be 11, we say 25. Let's just confirm 11.25. So 11.25 squared, we're going to divide it by 15. 11.25 squared divided by 15. So what does this give us? 11.25 squared. I'm dividing it by 15. Eyeball. Oh, okay. It is what it is. I'm getting 8.44. 8.44 watts. So that becomes the power dissipated. Then 8.3, they are opening the switch. Okay, let me just remove this. They are opening the switch, which means that this resistance will be out. Okay, the 15 will be out. We shall be only left with, remember our effective resistance was 7.5. Now, if 15 is removed, we shall only have this 5 and a 10, which gives us a 15, which means there's an increase, okay, by 2 times or 2 times the increment. So if now the resistance is 15 ohm, they're asking us if the resistance of the light bulb remains constant, okay, how will the brightness of the bulb be affected? Is it going to increase or decrease or remain the same? So regardless of the current that is flowing, remember this bulb is more like connected in series with the circuit for as long as this is open. Okay, so the same current will be flowing upwards. So the total resistance within the circuit has increased. So the current that is getting to the bulb will have to decrease, okay? And when the current decreases, even the brightness will have to decrease, okay? So that is a decrease. Now, what is the explanation? We're gonna say that there's going to be an increase within the total resistance, or we can say that the V external will increase, okay? Since we know that V is the same as IR. So if we increase the resistance, even the external voltage will definitely increase. So increase in the V external, okay, will lead to a decrease in the resistance. Or we can talk about the resistance decreasing, which leads to a decrease in the V external. That's why the brightness has decreased. Question number 9. Okay, there's a telling us a simplified DC electric motor is shown. Okay. This is what we can see. Now they're asking us to write down the name of component A. So we know that A is the split ring. Okay, split ring, you can say commutator, or just a split ring. That's enough. Okay, so then 9.1.2, they want us to state the energy conversion that takes place in the motor. So we know that the motor is an electrical device that converts, okay, is it mechanical? No, it's electrical to mechanical. So we're gonna say electrical to mechanical. Okay, so electrical energy to mechanical energy. So that's the energy conversion that takes place within a motor. The 9.1.3, in which direction is the coil going to rotate? Choose either clockwise or anti-clockwise. So if we look at our terminals, this is the positive, which means the current is moving in that sort of direction, okay? And then when we look at the field, let me just put this. So the field is moving in that sort of direction from right to left. Then we can use, okay, the left-hand rule of Fleming. So, which means that our field is gonna be that side. Our current is in this direction. Automatically, the force must be up. Okay, so this is gonna move up and then this is gonna move down. So the rotation is going to be clockwise. Then state 2 changes that can be made to the motor for the coil to rotate faster. So number 1, we can increase the magnetic strength or the field strength. Okay, so if we say increase, changes that can be made to the motor, okay, increase the field strength. Okay, that's number 1. We can increase the number of turns, increase the number of turns. Okay, that is. Then the last one that we can use is we can increase the strength of the current. Okay, increase the strength of the current. So all these 3 can be applied if we want to make the motor to rotate faster. The 9.2, they're telling us the circuit diagram below shows the electric kettle and the toaster that are connected to an AC source with RMS voltage 220 V. The ammeter, connecting wires and switches have negligible resistance. And then they're asking us for what the term root mean square current is. So we know that root mean square will be basically, I'll say the DC current, okay, that dissipates, this writing, that dissipates just the same amount the same amount of power, as the average. Okay, I can say the average that is dissipated by the AC. Dissipated by the AC. So in this case, DC current is this. That current, the root mean square current is a DC current that is more like equivalent to the same current that is dissipated by the AC current. So I'm saying the DC current that dissipates the same amount of power as the average dissipated, same amount of power as that average dissipated by the AC current. So it's like a comparison between the AC current and then the DC. So the equivalent of the AC is what we call the root mean square. Then 9.2.2 are telling us that when S1 is closed, okay, we're closing this, and S2 is open, the maximum current through the circuit is 3.6 amps. Can we calculate the root mean square of the current? So the RMS current, normally abbreviated as IRMS. For me to get this, I must find my Imax divided by the square root of 2. So our maximum current is 3.6 divided by the square root of 2. So 3.6 divided by square root of 2, what do we get? I'm getting 2.55. Okay, that will be amps since it's current. The 9.2.3, we're being told that switch S1 is now open. Okay, and then they choose to close S2 so that they look at the toaster. And then the root mean square current is 2.62. So the IRMS of the toaster is 2.62 amps. Calculate the energy that is consumed within 2 minutes. So we know that if I look at power, it will be the work done over the time. So which means that my work done will be the equivalent of the energy that will be consumed. So my work done will be the power multiplied by the time. But what I have, I'll just say the average power in this case, the power average. Since I have the current, I do not have the voltage. No, do I have the voltage? Yes, we have the voltage, which is 220. So which means the VRMS is 220. We don't need the resistance. You can calculate it if you want, but it's not a big deal in this case. So from our formula page, we can look for a formula that combines voltage and current. Ne? Voltage and current. We need the work done. I think we can even use this. Voltage squared over R times T for us to get the work done straight away. Or we can just say voltage squared over R and then multiply by the time afterwards. Okay, so what I'm going to do, I'll just get my V squared over R multiplied by T. So what's our V? It's 220. So 220 squared over, wait a minute. Do we know the resistance? No. I need to use the current since I have the current one. So let me look for the formula with the current. Is it the P is equal to IV? Does that make sense? Yeah, I can use this. VIT. Okay, so I'll say VI and then T. So it's 220 The current is 2,62. The time should be in seconds. So that is 2 minutes multiplied by 60. When I punch this into the calculator, 220 multiplied by 2,62 multiplied by 2 multiplied by 60. That is giving me some big answer, which is 69. Okay, 168 joules. For someone can say 61,17 kilojoules. No problem. So that is the work done, or the energy that is consumed by the toaster in 2 minutes. Question number 10. Question number 10. We're being told that two small spheres, okay, two small spheres, A and B, both of them are made up of pure zinc at rest, okay, and they're 0,1 meters apart on the wooden table. Sphere A is negatively charged, okay, and is free to move on the table, while B is fixed and it's uncharged. All right, so we have that. We have high intensity ultraviolet light of this frequency that is now shown on to sphere B. The work function of zinc is this much, so that is W unit. This is the frequency that is given. Can we define what work function of the metal is? So work function is just the minimum amount of energy required, or we can say the minimum energy needed, or say needed or required to remove or to extract an electron from a metal surface. My friends, forgive me for my handwriting. Okay, so minimum energy required, needed to remove or extract an electron from a metal surface. That is the work function of a metal. Then 10.1.2, they want us to explain, using suitable calculation, why the ultraviolet that is shown on B will be able to eject electrons. Okay, so eject is more like to remove or extract. So for us to answer this question, we need to calculate the work function, okay, of the ultraviolet or of the zinc metal. So we know that work function will be given as H multiplied by the F naught, the threshold frequency. So what we know is we are given the work function of zinc, which is this. Now let's get the work function. Will it make sense? Yes, the work function, if we have the ultraviolet light that was shown. So what I'm gonna do, I'll get the Planck's constant, which is H, which is 6,63 multiplied by 10 to the negative 34. I'm gonna multiply it with the frequency, which is 2,8 multiplied by 10 to the 6. No, I don't need to do this. I can just, okay, this formula is fine, but I'll just look for the energy, okay? I'll look for the energy itself, which is HF, the energy that will be produced by the ultraviolet light. So when I punch this into the calculator, I'm getting 1,856. What's going on? Okay, we're saying 1,856 multiplied by 10 to the negative 6. But this will be joules. Okay. If I'm to compare it to the work function, I'll have 185,6 times 10 to the negative 19 joules. Now we can see that 85 is greater than the 6,63. Then we can draw the conclusion that the energy that is produced by the ultraviolet light is greater than the work function, is greater than the work function. So since the work function of zinc, the minimum energy required is 6,63, and then 185 is way greater, so which means we shall be in position to extract electrons from that metal surface. And then 10.1.3 sphere A carries this charge and then requires a minimum force of this much. Calculate the minimum number of photons of ultraviolet light that must strike in order to remove, or in order to move sphere A from the rest position. Okay, so what I did in this case, I tried to look at that electrostatic force of K, P.1, P.2 over R squared. If that is A and then that is B, I want to see the charge on B that is going to cause an attraction, and then I'll take it from there. So since our net force is 0,027, that's what the question says. I'm not assuming my own things. They told us this is the force that is required. All right, so that is the Emax. Okay, so this is 9 times 10 to the 9 multiplied by the first force, which is 5,4 times 10 to the negative 6. I'm multiplying it by the QB over the distance of separation, which is 0,1 squared. So do the maths, 0,027 multiplied by the 0,1 squared. Then I'll divide this by the 9 times 10 to the 9 multiplied by the 5,4 times 10 to the 6. That will give me my QB. Then QB, what are we getting? I'm getting 5,56 times 10 to the negative 9. Okay, this is just the charge. Now, if I look at the Q is equal to NE, okay, I think I'll just use this approach. For me to get the N, I'll just say Q over E. Then my charge is the 5,56 times 10 to the negative 9, dividing it by 1,6 times 10 to the negative 19. Okay, and I simplify that. I'll have a total of 3,47 times 10 to the 10 electrons. Okay, so that's what I'm seeing, because they're asking us for the number of photons. Remember, photons are just packets of light, and it's more like electrons themselves move from the rest position. So that's what I would have done for that question. Then question 10.2. I'm telling us a beam of light. This is why it is shown through cold gas. So the keyword here is cold gas. Okay, then the emerging light dispersed, and then the line spectrum is observed on the screen. What type of line spectrum is this? So this is the absorption. I don't know if that's the spelling. So that is the absorption spectrum. Absorption spectrum, and then they want us to describe or define it. So this is a type spectrum where, or a type of spectrum that consists of frequencies of light that is transmitted with dark lines when electrons absorb energy with the ground or from the ground state so that they can reach the higher stages. So in other words, in this type of spectrum, the electrons will gain energy, okay? And that energy will enable these electrons to move from levels of low energy to levels of high energy or high energy levels. So which means they move from the ground state to higher energy levels. They're telling us that diagrams below indicate some possible energy transitions that are made by the electrons or by the atoms. Which of the diagrams will represent the type of spectrum? Now, since we said from our description that energy has to be obtained from low energy levels, and then the electrons or the particles we observe to be moving to higher energy levels. So I'll go with B, since with absorption, energy will be gained. All right. Which of the following? Choose A or B. So I'm choosing diagram B. I'm choosing diagram B. So guys, that is that. If there's any feedback, please, you can leave it in the comments. If there are any deviations, please, you can still slot them under the comments. We are more than welcome and we appreciate your positive feedback. It helps us grow. Thank you very much, guys. All the best in paper 2. Good day and welcome to yet another episode where we shall look at the suggested memorandum for the Physical Sciences Paper 1, grade 12, 2023. Okay, so looking at the paper, we have 10 questions, and let's try to see what could have been done in this paper. Remember, this is just the suggested memorandum. It's not the official one, okay? So question number 1, which is the multiple choice, they're telling us that various options are provided. We know that. Then 1.1, a constant net force is applied to a block. Okay, now which one of the following is correct? Okay, is the block going to move with a constant velocity? No, so that is out. Is the block going to move with a constant acceleration? There is some bit of truth in that. Then will the block move with a constantly increasing acceleration? No. Constantly decreasing? No. So for as long as the net force is constant, which means the acceleration will increase. No, the acceleration will be constant, will not increase. So B would be my option for 1.1. Then 1.2, they're telling us we have a crate of mass M that is stationary on a plane inclined at an angle of theta with the horizontal. Which of the following statements regarding the magnitude of the frictional force that are acting on the crate is correct? So one thing we know is that the forces that are acting on this object will be the FG parallel. Okay, and since there is no other extra force, let's say the applied force or anything of that sort, we expect this block to slide down. But since it is stationary, which means the frictional force should be acting upwards to keep this block in one place. Okay, so they're telling us that the magnitude of the frictional force acting on the crate is equal to the component of the weight, which is parallel. That is correct. Let's explore the other options. The frictional force is greater than the weight. So if frictional force was greater, then what would that mean? Then this object would be sliding upwards, so which doesn't even make sense for me. Okay, frictional force is equal to the component of the weight that is perpendicular, so the perpendicular part is wrong, and then is larger than the component of the weight. Frictional force is larger, that is perpendicular, so the perpendicular part also makes it wrong. Okay, so between option A and B, but in this case, since the object is not moving, I'll choose option A, since the net force is going to be 0. Is that true? But that is my option anyway. If you have anything different, please, you can slot it under the comment section. Then the next one, 1.3, they are telling us there's a ball that is projected vertically upwards from the top of the building points P, Q, R, and S represent the different positions during the motion of the bus shown in the diagram. Okay. So if you are ignoring the friction effects, between which 2 points will the ball undergo the greatest change? Okay, so greatest change in kinetic energy. So we know that for kinetic energy, okay, let's say the change will be a half m, you can say V final minus V initial, you can even square that, or you can just look at it independently. Vf squared minus the Vi squared, this multiplied by a half m. So if we look at P and S, if this object has a velocity, which we know, let's say, because we're not dropping this object, we are throwing it up with some magnitude of velocity, okay? Unless we also have this, the change between P and S is not that significant, okay? Let's look at P and R between this. It won't make any change that is significant. But my option, R and S, let's see, R and S, not really. My option would be D, between Q and S. Because we know that at S, this ball or this object will have the greatest velocity. Okay, the V maximum will be at S. Then at Q, that's when the body is going to have the V minimum, the minimum velocity. So this maximum and the minimum, we know the minimum velocity is going to be a 0. So this change of the maximum and the minimum will be the greatest. Okay, then 1.4, telling us a ball is dropped from a height h, okay, and strikes the floor with a momentum v. The ball is then dropped from a height which is a half of h. If we are ignoring friction again, which of the following represents the momentum of the ball when it strikes the floor after being dropped from that? So what we need to look at in this case is basically, we can look at the formula of momentum where we have mass multiplied by the velocity. But we don't have the velocity. We know that the ball is just having the same mass, whether dropped from h or half of h. So if I try to kind of look for the velocity and I use the V final squared is equal to, I can use V initial squared plus 2 multiplied by G delta S or delta X for the displacement. In this case, it can even be a delta Y since we're moving in the Y direction. Now, since we are dropping, I'll take G to be positive in this case, and our initial will automatically be a 0. So if I consider the H, okay, so at height H, my V final will be the square root of just this, since that is a 0. So 2 times 9,8, I'll just say H. Okay, let me call this, why can't I say VH? We're saying 2 times 9,8H and the square root. Okay, then I'll do the same thing for V when it is a half of H. I'll still be left with the same thing. So this will be a 0 again, since I'm just dropping the object, then I'm going to have 2 times the 9,8 times now the half of H, which is H over 2. Okay, so then for me to simplify that, I can see that this 2 is going to cancel that, and I'm only going to be left with 9,8H under the root sign. Now, if I try to get the momentum, the masses are the same, so basically I'm comparing. If I call this P1, okay, it's going to be root 2 multiplied by the root of 9,8H. Okay, and then my P2, which is the momentum at a half, is going to be, let's just call this one. That's the way they're calling it, that this whole thing is a P. And then momentum 2, we just have the 9,8H multiplied by the mass. Now the question wants us to compare
this second momentum, how does it relate with the first one? Okay. So we can see that we have this and we have that. The only difference that we don't have is the square root of 2. So the option that I'll go for will be B, because the second momentum will be half or 1 over root 2. Okay, then 1.5, they're telling us a box moves on a horizontal surface. Diagram below shows all the forces acting on the box. Which of the following combination of forces will do the work on the box? Now pay attention to the direction. So we're looking at moving on a horizontal surface. So it's moving horizontally. Regardless of the direction, fine, horizontal. So our interest will be basically the horizontal forces. Okay? So we know that this Q will have a component of the Q cos of the angle of inclination, okay, that will act horizontally. So the forces that are going to do work will be basically this S, and I'm seeing this Q. Is there friction? There is no friction in this case. Okay. Work will not be done by the weight, work will not be done by the normal force, since those are vertical forces. So I'm going to go for S and Q. So the option I have is Q and S in that case. Then 1.6, a train that is moving at a constant velocity towards a stationary listener emits sound waves at a constant frequency. Which of the following statements about the sound waves observed by the listener is correct? Now remember, the listener is stationary, not moving. So as the train is approaching this listener, we expect the frequency to increase, okay? And if the frequency is increased, which means the lambda, the wavelength, must be smaller or shorter in that case. So let's see, they're telling us that the observed frequency is higher than the emitted frequency. That makes sense. They're telling us that the wavelength is longer, which is wrong, because we said if the frequency is high, the wavelength must be shorter. And the frequency is lower, no. The wavelength is equal to the emitted wavelength. That is also wrong. So I'll go with option A. And then 1.7, if we are referring to the diagram below, they're telling us Q and R are small spheres that are suspended by light insulated strings. When a negatively charged rod is brought close to Q, sphere Q is repelled. And then when a negatively charged rod is brought close to R, there is attraction that takes place. So which of the following combinations below can be possible for the nature of that? Now, we know about the signs or charges, that like charges will repel and then unlike charges will always attract. So automatically, since Q is repelling a negative rod, Q will be negatively charged. Okay. Now, with attraction, there are two scenarios. Attraction can take place between two opposite charges, let's say negative and a positive. But attraction can also take place between a negatively charged rod or charged sphere or object and a neutral object as well. Okay, there will still be attraction. So R can either be positive or it can be neutral. But we're saying Q is a negative. So where is Q negative? We have option A, and then we have option D. Then we're saying R, we only have two options. It's either positive or neutral. So A is out. We shall go with D. Okay, then 1.8, 4 voltmeters, V1, V2, V3, and V4 are connected in the circuit as shown below. So which voltmeters will have the same reading as V1? So our focus is V1 that is connected across the terminals. So connected across the positive and the negative. So when you look at V2, V2 cannot have the same reading since it's just connected, not across.
the terminals. V3, I feel is the correct option because connected across, okay? We have the positive and then we also have the negative this side, but as long as the switch remains open. So V3 becomes the option because V2 and V4 are basically in the same sort of scenario. So this is out, that's out, and then that is also out. So B would be my best option for that. Then 1.1.1.1.9, they're telling us that a split ring commutator connects the coil of a generator to the external circuit. Okay. Which of the following combination is correct of the magnitude and direction of the induced current within the external circuit? So focusing on the generator. And then about the external circuit. So the magnitude of the induced current, so we need to ask ourselves, which generator uses the split ring? Is it an AC or a DC? Okay. If we can tell that, then we shall be able to look at this or to determine that. So the generator that uses the split ring, remember for the motor, is the DC motor that uses the split ring. Okay, but then which generator uses the split ring? Okay, so since we have a split ring commutator, I'll go for a DC generator. Okay, and with the DC generator, what we know about the magnitude of the induced current is gonna keep on changing. Okay, so I have option C and D for the magnitude of induced current. But the direction, since it is a direct current, it has to stay the same. Okay, so option C would be my best. It would change if it was an AC. Then 1.10, light of a suitable frequency is shown on to the surface of a metal and electrons are ejected from the metal. Which of the following is equal to the ratio of the work function to the threshold? So from our formula page, we have something like this. Work function is equal to H times F naught. Okay, so they want the ratio. It's like we are dividing W naught over F naught, the threshold frequency. So this will only be left us with H, and this H is what we call Planck's constant, which is A in that case. So that is question number 1. Question number 2. Question number 2, they are telling us that 2 blocks A of mass 4 kgs and then the 9 kg are connected by a light string. The blocks are held at rest on a plane which is inclined at an angle of 35. And for the June examination 2025 for grade 12 physical sciences, paper 1. So this was a 3-hour paper with marks of 150. The paper was to be done in 3 hours. So we have 15 pages, okay, and 3 data pages. We're dealing with 9 questions, okay, that we shall have to work on. So let's see how we should have fared within this paper. So question 1, which is always the multiple choice, they are telling us that we have various options as possible answers, but each has just one correct answer. You just need to choose the correct option. Okay, 1.1. Which of the following forces will always act perpendicular to the surface on which the body is placed? So that is option C, which is the normal force. Okay, tension, friction, gravitational do not apply. So number 1.1 is C. And then 1.2, we are being told that a car of mass M moves along a straight line at a constant velocity V in the easterly direction. The velocity of the car decreases to 1/3 of the original speed in t seconds, okay, as shown. And then they telling us that it is not drawn to scale. And then the question is asking for the change in momentum of the car. And so one thing you know about the change in momentum is that it is mass multiplied by the V final minus the V initial, okay? So our mass is M. Our V final is 1 over 3V, and then we are subtracting the V initial, which is just a V. When we simplify this, okay, our M is gonna be 1 over 3 minus 1. That's gonna be negative 2 over 3, okay, negative 2 over 3, but V. Meaning that the overall change in momentum is going to be negative 2 over 3V. Now, since the initial direction was easterly, okay, the negative aspect simply indicates the opposite direction. So meaning that our change in momentum will be within the west, okay? So 2 over 3V, but west. 2 over 3, we're talking of MV, okay, because we don't have the value of MV. So 2 over 3 MV west, which is option D. All right, then 1.3. An object Y exerts a gravitational force of 1,000 newtons on object Z when the distance between the two objects is R, okay? The two objects have a mass of M each. Which of the following will increase the force to 4,000? Okay, so initially the force was 1,000, and now we're going to have 4,000, which means we're focusing on 4F. So for us to increase the force, the distance need to be halved. Okay, so which means it will be like R squared over 4 to give us 4. So half the distance, so half the distance between the centers, which is option B. Then 1.4, we're being told that a ball is kicked across the floor and it comes to a standstill after T seconds, okay? Which of the following statements describes the total mechanical energy and the net work done on the ball? Okay, so the first one, total mechanical energy, one thing we know is that for as long as the ball is rolling, we know that the floor is rough, and because of the presence of friction force, the ball will come to a standstill, okay? Now, the kinetic energy will decrease because the final velocity is a 0. And then the potential energy might stay the same, okay? But now, when the ball is rolling, we know that the combination of kinetic energy and the potential energy is going to be bigger than the potential energy only at the end when it is rested, okay? So in that case, the fact that there's a difference between the energies or the mechanical energy, so you're gonna choose not conserved, okay? Then the work that's gonna be done, the net work done, only force that is acting on this ball to bring it to rest is just the frictional force. And friction always works in the opposite direction. So I'm gonna go for negative, which is option A. And then 1.5. They're telling us that a crate is given an initial velocity and it slides up a frictionless incline until it comes to a stop. Which of the following graphs shows the correct relationship between the kinetic energy and the potential energy? So we know that when the crate is sliding up, okay, the moment it stops, at that point, the EK is going to be 0. So in other words, with the graphs that we're looking at, we should be focusing on the EK being a 0 at the end of the graph. So B is out, D is also out. Then as this one is a 0, the body will only have what we call the EP max. Okay, the maximum potential energy is what will be left. But initially, the potential energy was a 0. So when I look at A and C, these seem to be the best options. But is there friction? They are telling us up a frictionless. So if it is frictionless, then I'll choose option C. Okay, if there was friction, then option A would make more sense. Then 1.6, for a light redshift indicates that the light source is moving away from the observer. So option A is going to be the best there. And then 1.7, 2-point charges, 7 nanocoulomb and negative 5 nanocoulomb are brought together up until they touch. Immediately after, they are returned to their original position. So one thing we know is that when charges are brought together, after the separation, the charges must have equal magnitude, okay? So a 7 minus a 5 is going to give us a 2. You divide by 2, meaning that we're going to have a nanocoulomb on each of the spheres, okay? Now, since these nanocoulomb are positive, okay, the charge is positive, we expect a repulsion. So option C is out, option D is also out because the field lines are crossing each other, and of which they shouldn't. Option A and B, since they are positive, the field lines should be moving outwards and not getting into the sphere. So option B becomes the best option there. Then 1.8, a non-ohmic conductor can be described as a resistor for which. So we know that ohmic obeys Ohm's law. Okay, non-ohmic does not obey. Okay, so Ohm's law is valid. So this is out for a non-ohmic. Current potential difference produces a straight line. This is for ohmic. The resistance does not vary with a change in temperature. Well, with ohmic conductors, we remember Ohm's law. Normally it talks about the temperature being what? Being constant. So if the temperature increases, even the resistance will definitely change, whether it is ohmic or non-ohmic. So option D, the resistance is not constant, okay, and then it varies with the applied potential. So option D would be the best for me, okay? And then 1.9, 4 identical resistors are connected as shown, which connection will result in a total resistance of 4 ohms. Let's see, resistor by resistor, okay, option by option. So here we have 2 series, okay, meaning that when we plus the top, we're going to have a 4, and then we're going to have a 4. Then these 2 will be in parallel, okay? So for me to get the effective for the parallel, it will be 1/4 plus 1/4, which will give us a 2/4, meaning that the effective resistance is just a 2. Alternatively, use the product over the sum, meaning that it is 4 times 4 over 4 plus 4. So 16/8, which is 2. So this is out. Let's look at this one. We have a 2 and a 2, so these ones are in parallel. Let's start with this. So you're going to have the product over the sum, 2 by 2 over 2 plus 2, which gives us just a 1. Then if that's a 1, plus 2, that is 3, plus 2, which gives us a 5 ohm. Okay, let's look at the next one. With this one, we know that these 2 and these are in series, né? So technically, there is no difference between option B and option C, the way I'm looking at it. The way I'm looking at it. But let's see. Let me pause on this one. Let's try option D. So 2, 2, and 2, that's going to be 1/2 plus 1/2 plus 1/2, which gives us 3/2. Then the actual resistance, okay, is going to be 2/3. And then when you plus the 2, that's going to be 6 plus 2, that's going to be 8/3, which is not a 4. Then this one, for me, I believe it's more like the same as this. Okay, so if I take it to be the same as that, but I've already taken out A, I've already taken out B, and then I've taken out D, so I'm only left with this option C. I'll go with C for the sake of just choosing an option. Okay, but I wouldn't also agree with C, but I'll take it for the sake of just choosing an answer. Then 1.10, they're telling us that a kilowatt hour refers to the use of electrical appliances. Nope. The power of electrical appliances. Nope. 1 kilowatt of electricity used for 1 hour. Very correct. So 10 is going to be a C. And then question number 2, a person pulls a block of mass 12 kgs to the right using a light inextensible rope T. The block is pulled from point A to B at an angle 40 between the rope and the horizontal surface. The coefficient of kinetic friction is 0.31, and the block is pulled at a constant velocity of 10. Okay, so meaning the acceleration is 0. Okay, then the first question, define the term kinetic frictional force. So we know that kinetic frictional force is just the resistance force. Okay, let me just call it resistance force or resistive force that is acting. I mean, resistance force doesn't sound proper. Resistive. Okay, resistive force that is acting between, okay, we can say between two surfaces, acting between two surfaces in contact. So the surfaces need to be in contact and then they have to be moving, okay, when they move relative to each other, relative to each other or relative to one another. Okay, so there has to be motion for us to have the kinetic friction force. Then 2.2, they want us to draw a body diagram of all the forces that are acting on the 12 kg. So number 1, we have this tension. Then we have the frictional force, Fk. Then we're going to have the normal force, Fn. And then we're going to have the weight downwards. So for me to draw the free body, 2.2, let me put it this side and say 2.2. Okay, so this, we say the tension is at an angle. The weight is, what's happening? Why am I writing skew? My book is Q. So something like that. And then we say the frictional force is going to be the Fk, and then we're going to have the normal force, Fn. All right, and then 2.3, they want us to get the magnitude of the tension. So when we look at the tension, we have two components. Number 1, we have the vertical component, which is going to be T, the sine of 40, and then the horizontal, which is T, the cos of 40. Now, if I look at just the horizontal, I'll be focusing on this being equivalent to the frictional force. Okay, so I'll say that F is equal to ma since it's moving, but we say that we're going to have a 0 this side since it's moving at a constant velocity. So our T, cos of 40, okay, T cos of 40 plus a negative Fk should give us a 0. So T cos of 40, we know that frictional force will be given as mu multiplied by the normal reaction, okay? So that is mu K multiplied by N. But our normal force is going to be affected, okay? Because it has the T sign included, okay? The T sign is part of our normal force, which is, so we're gonna get the weight and then we subtract this whole T sine of 40, and then we're good to go. So I'll say that T cos of 40 minus the mu K into my mg minus T, the sine of 40, should give us a 0. Okay, let's just substitute and as we open up. So T cos of 40 minus the mu, which is 0.31, into the mass is 12 times 9.8 minus T, the sine of 40 should give us a 0. Okay, so when we open this up, it's T cos of 40. But why don't I simplify cos of 40 once? Okay, so from our calculators, what is the cos of 40? That is 0.766. Is that correct? We're saying the cos of 40
is 0.766t minus, when I multiply this entire thing, okay, 0.31 times 9.8 multiplied by 12 is giving me a 36.456. 36.456, this and that, I'm going to get a plus. What is the sign of 40? Sign of 40 is 0.643t is equal to 0. Then I need to add this and that. Okay, so when I get that answer of mine and then I plus the 0.766, I end up with a 1.4087, which is a 409, is equivalent to 36.456. Then I'll divide both sides. Okay, there's a t there. Divide by 1.409, 1.409. Then what is t giving us? What is t giving us? Why am I having someone says our answer is kind of not right? It's fine. What did we do wrong? We did not multiply by the 0.31. Multiply this by the 0.31. Thank you very much. So 0.643 times 0.31, which is 0, so this is a 0.766t plus 0.199t. Okay, when you simplify that, what do we end up with? We're gonna have 766, which is a 0.965, 0.965t. So instead of us dividing both sides by 1.4, we're just going to divide. So it's a 36.456 divided by 0.965. And this gives me an answer of a 37.78 newtons. Okay, so this is out. Okay, so that is what we had to do for the, have we answered the question for the tension? Yes. Then 2.4, they are telling us that the block is moved a distance of 24 meters, okay, from there up to there. Calculate the time it will take. So we know that speed is given as distance over time, and then we're looking for the time, meaning that our delta t should be the displacement divided by the velocity, or the change in the velocity itself. Okay, so that's going to be a 24 divided by 10, which gives us 2.4 seconds. Okay, then 2.4.2. If the block's velocity is now increased to 20 meters per second, how will the frictional force be affected? I mean, increasing the velocity has no effect on the friction. The friction will basically stay the same. So we're going to say it remains the same. Okay, then 2.5. The angle between the rope and the horizontal is increased to a 50. Okay. What will be the effect on the kinetic frictional force acting on the block? Now, initially it is horizontal. When it is horizontal, all the normal force will be equivalent to the weight. Is that true? No. It's not horizontal. We're looking at a 40. Okay, but now we're saying that we are increasing it to a 50. Okay, so let's see, between the cos of 40 and the cos of 50, which one is bigger? So cos of 40 is 0.766, and then the cos of 50 is 0.64, meaning that increasing the angle, okay, will decrease the normal reaction. And if the normal reaction is decreased, meaning that the frictional force will also decrease. So this is going to be a decrease. Explanation is that increase in the angle, okay, will lead to the decrease in the normal force, hence the frictional force will also decrease. Okay, so that is the explanation that we could be having. Question number 3, a rocket of total mass m is launched from the surface of the Earth. The initial weight, remember we're talking about weight, is 5,38 times 10 to the 6 newtons. The mass of the rocket decreases due to the loss of fuel that is used to propel the rocket. When the distance between the center of the rocket and the surface of the Earth is 9,000 meters, the rocket experiences a gravitational force of this much. Okay, the diagram below is not drawn to scale. That's what we have. And then they ask us to state Newton's law of universal gravitation. So we know that for any two bodies, okay, in space or in the universe, okay, they experience, or each body, because we can say that each body experiences or exerts a force that is directly proportional, okay, that is directly proportional to the product of the magnitude of the masses, okay, and inversely proportional. So inversely proportional to the square of distance, of the square of the distance between them or between the centers. So something of the sort. Then 3.2.1, they want us to get the total mass of the rocket before it is launched. Now, the question gave us the weight, okay? They want us to get the mass. So we know that weight is given as mass times gravity. So for us to get the mass, we shall get the weight divided by the g, meaning that we shall get our 5,38 times 10 to the 6, and then we divide it by the 9,8. So 5,38 times 10 to the 6, we're dividing it by 9,8. This gives us 548,979,59. This is going to be kilograms. All right, then we move on. That is 3.2.1. Then 3.2.2, they want us to get the mass of the rocket when it is 9,000 meters away from the surface of the Earth. So we need to use the universal gravitational force. So we know that that is given as F being the same as G, M1, M2 divided by the R squared, okay? So we were given the force as, what's gonna be the force? Because now if the force is acting here, and this is our distance to the center, but then they told us when it is 9,000, meaning that we need to add the radius of the Earth. So 5,04 times 10 to the 6. So I'll say 5,04 times 10 to the 6 should be equivalent to 6,67 times 10 to the negative 11. Then we know that the mass of the Earth, okay, mass of the Earth is given as 5,98 times 10 to the 24 multiplied by the mass of the rocket, which we don't know. And then we are dividing this by the 9,000 plus the radius of the Earth, which is 6,28 times 10 to the 6 squared. Okay, so that's what I have. Then I just need to do the cross multiplication, meaning that the mass of the rocket is going to be 5,04 times 10 to the 6 multiplied by the 9,000 plus 6,28 times 10 to the 6 squared. And then I'll divide this by 6,67 times 10, that. Okay, times 10 to the 24. So the answer that I'm getting, maybe I should just round it off and give it in a scientific notation. So it's 5,16 times 10 to the 6 kilograms. This one, we can also write it in that same form, okay? Meaning that it will be 5,49 times 10, 1, 2, 3, 4, 5 kilograms. Okay, then the next question. They want us to get the mass of the fuel that was consumed. So for us to get the mass of the fuel, we're going to get the answer in 3.2.1, subtract the answer in 3.2.2, and get our answer for the mass of the fuel that was consumed. So we're saying 3.2.3. So mass of the fuel is going to be the initial mass, which was 5,49. Okay, that's 5,49 times 10 to the 5. We are subtracting 5,16 times 10. Does it make sense though? This is to the 6. Okay, so when I tried to subtract this looks impossible. So there's something I might have messed up somewhere, somehow. So I'll just go back here. This is supposed to be a 3.8. Okay, so when I punch that, I'll get my answer, but this is supposed to be a 5 as well. So meaning that it is a 5. This is also, is it a 5,49? Is that what we got here? Yes, 5,49. Now it's fine if the exponents are both the same and it makes life easy. So 5,49, we are subtracting 5,16, meaning that we have a 0,33. And then when we multiply it by 10 to the 5, we're getting 33 of fuel, okay? Or 3,3 times 10 to the 4. So that is how I would have approached that question for 2 marks. Then 3.3. 3.3, they are telling us that the rocket is on its way straight to the moon, okay? So as the rocket is moving to the moon, it simply means that the distance between the Earth and the rocket is increasing, while the distance between the rocket and the moon becomes smaller, okay? So what will happen to the gravitational force between the moon and the rocket as the distance increases? So the explanation here is going to be as the distance decreases, the distance decreases, the force must increase. Okay, increase would be the best option for that part. Then question number 4. Okay, question number 4. They're telling us that a hot air balloon moves upwards at a constant velocity when a block B is dropped from the side of the balloon and falls to the ground. The balloon is 50 meters above the ground when the object is dropped. The graphs below show the motion of both the balloon and the block, and then the graphs are not to scale, ignore. So upwards, positive, no calculations. It's not really a big deal there. Then velocity time graph for this, we have 5, we have V. So I'm assuming T2 is when the block hits the ground. Okay, I'm just assuming because it's not telling us anything of the sort. Then which of the two, the hot air balloon or the block, is in free fall? So I'm going to say it's block B. Okay. Why is it block B? Because we know that this hot air balloon moves up at a constant velocity. Okay. Then when you look at the block is just dropped. Okay. When it is dropped, it's like there's no initial velocity to it. So block B will be under the free fall. And what is the reason? We're going to say that its motion, okay, its motion is entirely under the influence of G, influence of the acceleration due to gravity only. Then 4.2,
can we use only the equations of motion to calculate the following values? Number one, they want us to get the size of T1 or the time T1. Now we know that T1, because this is the motion of the block, we're seeing that the initial velocity, the final velocity is 0 here. One thing we need to remember is that when objects are thrown from a hot air balloon, okay, they will momentarily take on the inertia principle, whereby they will continue moving with a 5 meters per second upwards up until they reach a maximum and then they drop, especially for this block in particular or in question. So we know that our V initial is going to be 5 meters per second, but we're saying that our V final is a 0. So meaning that at T1, that's when block B reaches the maximum height, okay? So you're gonna say V final is equal to V initial plus A delta T, okay? Let's start by the equation or the formula, and then we do the substitution. So our V final is a 0, our V initial is a 5, okay? And then plus, since it's moving upwards, gonna be negative 9,8 multiplied by T. Okay, then you transpose that, meaning that the 9,8T should give us a 5, then divide both sides by 9,8, and then 9,8, meaning that our T becomes 0,51 seconds. All right, so if that is 0,51 seconds, what's the next question? They want us to get the velocity of block B. Velocity V of block B. So velocity V is more like the final velocity when the block hits the ground. So what I'm going to do here, I can use the VF squared, that formula, and say VF squared is equal to V initial squared plus 2A delta. In this case, we can say delta Y or delta X. Then let's do the substitution. We're looking for V final squared. So VF squared is equal to the initial, which was a 5, né? So that's going to be 5 squared plus 2 multiplied by the negative 9,8, and then the displacement is also going to be negative 50. So VF squared gives me 1005. And then when I find the square root of that, I'll end up with a 31,7, but that is meters per second. So V is a 31,7 meters per second. Then they want us to get the time T with which the block hits the ground, time taken to hit the ground. Okay, so with that, I'll use the delta Y is equal to V initial delta T plus a half A delta T squared. Let's do the substitution. So it's going to be a negative 50. Our initial is a 5 and T. This is going to be plus a half negative 9,8 and then T squared. Okay, then when I do the magic, that's going to be 4,9 T squared minus 5T minus 50 is equal to 0. If we use our quadratic formula, negative B plus minus square root of B squared minus 4AC over 2A. What do we get here? Let's see, 4,9. Minus 50. So I'm getting two answers, negative 2,72 seconds. Oh, it's going to be a 3,75 seconds. So we know that time can never be negative. Ne? So in this case, our T of interest is going to be at 3,75 seconds. Okay, then we move on to 4.3. They want us to sketch a position time graph of block B from the moment it is dropped up until it reaches the ground, okay? Using the ground as a reference of 0. We need the initial height, the time taken at the maximum, and then the time. Okay, so I'll have this. So this is my delta Y in meters. This is my time in seconds for 5 max. Ne? Okay, so initially, this block was dropped at 50. Okay,
Then it went up momentarily, reached the maximum, and then came down. So the time when it reaches the ground here, the t we are saying is a 3.75 seconds. Okay, that's the position 0. Then when it reaches the maximum, that's our T1, which is the 0.51. So basically, that's what the question wanted. So the 50, the maximum, and all of that. They say the time. They don't want the maximum height, just the time. Okay, so that is 4.3. Then question number 5. Question number 5, we have a vector diagrams below that show the momentums of car A of this mass, which is traveling to the right before and after collisions with the stationary car B. The collision lasted for a period of a half of a second. And then after the collision, car B moves to the right with a speed of 20 meters per second. Okay. Calculate or state the principle of conservation of linear momentum. So we know that in an isolated system, we know that the total linear momentum is conserved or remains constant. In an isolated system, the total linear momentum remains constant or remains the same. 5.2.1, they want us to calculate the velocity of car A before the collision. So what we have is the momentum, okay? And we know that momentum is given as the mass multiplied by the velocity. So we know the mass of A. So it's just going to be 30,000, okay, divided by the mass, which is 2,000, which gives us 15 meters per second. Okay, so that is 15 meters per second. And then they want us to get the mass of B. So here we can apply the conservation. Okay, we apply the conservation of the momentum. So meaning that we're going to have, so mass of A, V initial of A, plus mass of B, V initial of B should give us the mass of A, V final of A, plus the mass of B, V final of B. Here we have the momentum already, so there is no need of calculating that. So we're just going to say 30,000. Okay, so that's a 30,000 plus it was at rest, so that is a 0. The final momentum is 10,000, okay, in the same direction. And then the final here is going to be mass multiplied by the 20, since they told us that the body is moving at 20 meters per second. So let's move this 10,000 to that side, meaning that we're going to have a 20,000 divided by 20. So this gives me 1,000 kilograms. All right, then 5.3, they want us to draw a labeled vector diagram showing the magnitude and direction for the change in momentum. So we know that change in momentum is the mass, or we can say momentum final minus momentum initial. So it's the 10,000 minus, that was a 30,000. Meaning that we're going to have change in momentum of negative 20,000. So the 20,000 is acting in the opposite direction, which is the left. So we're going to have something like that. So this is 20,000 kilogram meters per second. Okay, then 5.4, can we calculate the magnitude of the net force that the car exerts on car B? So we know that F net is the same as the rate of change in momentum, okay? So our F net, because the formula says F net delta T should give us the change in momentum, the impulse, okay? Then for us to get the F net, we have our change in momentum, which we said is a negative 20,000 over the change in time, which is 0.5. So this gives us a negative 40,000. So it's going to be, but they said A, magnitude of the net force that A exerts on B. Okay, so that is the answer that we have. Then 5.5, use the impulse momentum theorem to explain how the airbag. Okay, now we know that the change in momentum must give us F net delta T. Okay, this is the impulse, and then that is the change in momentum and all of that. So one thing that happens, okay, with the airbags of cars is that the aim is to basically increase the time of contact between the airbag and the driver so that the force will definitely decrease. So to reduce, okay, the force, we're saying that there is need to increase the time, okay, over which the momentum changes, So increase in the time will lead to a decrease in the force. You can even write this kind of expression whereby the F net is inversely proportional to delta T. Okay, something like that. Then question number 6. Question number 6. Is that the correct part? This is 11. This is 12. Okay. Question number 6. They're telling us that a 20 kilogram kg box initially at rest at point Y on a rough horizontal surface. The box is pulled to the right by a constant force parallel to the surface, and then the box is moved the horizontal distance 4 meters, and it experiences a frictional force of 65 newtons. Can we define the term the non-conservative force? So we're saying this is a force, okay, is a force in which the work done, okay, force in which the work done by the force depends on the path taken, depends on the path that is taken. They name the non-conservative force or forces that are acting on the 20 kg. So we have the 100, which is the 100 newtons, or we can also have what we call the frictional force. Okay, so this is applied force. Let's call it applied force, the 100. And then we also have the frictional force. And then 6.3, using energy principles only, can we determine the speed of the box at Z? Now, what I can do, or what I'll look at, I know that the net work done is equivalent to the change in kinetic energy, okay? So this box is having frictional force in that direction. We have the applied force. So it's only two forces that are acting on this body. So for me to get the network, I'll get the work done by the applied force and then the work done by the frictional force, and then I'll equate it to the change in the momentum, or sorry, the change in the kinetic energy for both of them. So let me come this side and say that this is 6.3. Okay, 6.3, we're saying W net is equal to the change in EK. So we say the work done by the applied force plus the work done by the frictional force should give us the change in the EK. So the applied force is 100 multiplied, because we know that the work is force delta X cos of theta. So 100 multiplied by 4, the cos of 0, plus the 65 multiplied by 4, the cos of 180 should give us a half the mass. Okay, the mass is 20. Okay, so that's 20 into the V final squared minus the V initial squared, which is a 0. So this is going to be a 400. Okay, then 65 times 4 gives me a negative 260 is equivalent to 10 VF squared. So 400 minus 260 gives me 140. I'm dividing it by 10, and then I'm finding the square root for me to get my V final. So square root of 14 is 3,74. So that's what I'm getting, 3,74 meters per second. Okay, then 6.4, can we calculate the average power that is dissipated by the 100 Newton force between Y and Z? So we know that the power average is given as the force multiplied by the velocity. Our force is 100, okay, and the change in velocity is going to be the 3,74, okay, minus the zero, the initial, which is 3,74 here. Okay, the change in velocity is 3,74, meaning that we're going to have a 374 power is given in watts. Okay, then 6.5. The box is now pulled upwards by 100 Newton force on an original surface, which is now at an incline with an angle that we don't know. Can we draw labeled free body diagram showing the conservative? The first question was the non-conservative. Now we're talking about the conservative. So we're going to have one, the weight, and then we're going to have the normal force. So we're just going to say weight, and then we're going to have the Fn. So those are the two forces for 2 marks. Then 6.5, will the box still have the same speed after the 4 minutes? Or the 4 meters, as in question 6.3, right? Only yes or no, and so on. Now, when we look at the incline is going to present two components of the gravitation, of the weight, and of which our frictional force depends on this component, the mg cos of theta. Okay, so instead of it depending on the entire weight, it's just depending on a component, just a portion of it. So meaning that the frictional force is going to decrease. So will the box have the same speed and what? So if the frictional force decreases, meaning that the distance that this object can move is going to be more than 4 or equal to 4. Will it still have the same speed after the 4 meters? Wait, will the box still have the same speed after 4 meters as in question that? So the answer is going to be a yes for me. Okay. The reason is going to be there is less friction. It's a yes because the friction has decreased. So if the friction decreases, meaning that it can even move at a greater distance. Okay, then question number 7, a hawk emits a sound at a frequency of 90 hertz. The speed of sound is 340. Can we state Doppler effect in words? So we know that Doppler effect is basically the apparent change, okay, in the frequencies observed and emitted. Okay, we can say it's the change, okay, the change in the frequency detected by the observer, the change in the frequency detected by the observer. Okay, when there is relative motion between the source, the observer, between the source and observer, okay, between the source and observer in a medium, in a wave medium or in a medium, something of the sort. So for as long as you talk about the apparent change within the frequencies, the observed frequency and the emitted frequency, as a result or because of the change in the velocities of the source and the observer. Then 7.2, a stationary observer will get 88 hertz. Is the hawk flying towards or away? The answer is that it is flying away, because when it flies away, the frequency is smaller than the emitted one. Then calculate the speed of the hawk. So from our this is gonna be 7.3. And then 7.3. What is going on here? Okay, let's try this side. 7.3, so from the formula of Doppler, we know that V plus minus VL over V plus minus Vs multiplied by the frequency of the source. So what's going to happen then is that we already have our velocity of the listener, okay, which is 0. Velocity of the source is what we need. The V is a 340. Frequency of the source was a 90. Frequency of the listener is 88. Now, since the Hawk is moving away, meaning that our frequency of the listener is V minus VL over V plus Vs times Fs. This is what we're going to use. So the listener is 88. This 340 minus 0 over 340 plus Vs times 90. Let's do the cross multiplication or the switching. That's going to be 340 times 90 over 88 is equal to 340 plus Vs. Okay, so when I punch this in the calculator, we have 340 times 90 divided by 88. It gives me 347. 727272. So when I subtract the 340, meaning that our Vs is just 7,2. What am I saying? Because 347,72. So it's going to be 7,72 meters per second. But 27, which means it's a 73. So 73 meters per second. So that is what we would have done with question number 7. Question 8, 3-point charges A, B, C placed in diagram as shown below. Can we state Coulomb's law in words? So these laws we need to know. We need to remember how to state because these are just a giveaway. Okay. So if we have 2-point charges or if we have 2 charges in space, we're saying that the force, the electrostatic force, okay, we normally say the electrostatic force between them is directly proportional, okay, directly proportional to the product, okay, of the magnitude of the charges, okay, and inversely proportional to the square of the distance between them. So something like that, for as long as you know how to, Q1, Q2 over R squared. It's just putting this in words. Then 8.2, they want us, they don't want us. They're telling us that the net force on A due to B and C is 0,866. Can we calculate the distance D as indicated in the sketch for 5 marks? Okay, so we need to get the force FC, the force AB. Okay, so let me just start with it here. So with our FAB, it's going to be K. Okay, let me put this side because I don't have space there. We're saying FAB is K Q1 Q2 over R squared. So 9 times 10 to the 9. The Q1, which is the A, is going to be 5 times 10 to the negative 6. This one is 2 times 10 to the negative 6 divided by the distance, which is 0,5 squared. Okay, when I punch that into the calculator, what are we getting? So this gives me 0,36 newtons, okay? Then the FAC is going to be the same. It's going to be a K Q1 Q2 over R squared.
which is 9 times 10 to the 9 multiplied by the 5 times 10 to the negative 6. Then this force is 7. Okay, times 10 to the negative 6. We're dividing it by d squared. Okay, so when I simplify this, I'm getting something like a 0.315 over d squared. So this is the force of AC. Then, since we're talking about the net force being 0.866, okay, I'll say that our F net is 0.866. For the three forces, we're going to have some sort of a right angle triangle. One for the vertical, because there's attraction, and then there's also attraction then. And then one for the horizontal. So the Fy, the F horizontal, and then the F vertical. So if this is 0.315 over d squared, and then this is 0.36 squared. Let's use the theorem of Pythagoras. Okay, is it Pythagoras? Yes. We're going to use Pythagoras and then proceed to get the net force and then do the substitution as required. So we're saying that our F net should be the 0.36 squared plus the 0.315 over d squared. This should be squared. Okay, this is F net squared. Meaning that if we have the 0.866, we square this. Okay, should give us that 0.36 was direct. Okay, that's fine. Then I'm going to have this. Why don't I just subtract once so that we save time? Okay, so minus 0.36 squared must give us the 0.315 over d squared. Everything is squared. So for me to get rid of this square, I need to find square roots on either sides. Okay, so let's punch that and see. It's going to be 0.866 squared. You're subtracting 0.36 squared. I'm ending up with a 0.788. Okay, is equivalent to 0.315 over d squared. Okay, so let me transpose and switch, meaning that our d squared is going to be 0.315 over 0.788. For me to get the d alone, I must find the square root there. So the fact that we are having a lot of decimals, it might kind of affect our level of accuracy. But the answer I'm getting is 0.635, which could be rounded off to 0.64 meters. I don't know. That's what I'm ending up with. So it could be round about that range. All right, then 8.3. They are removing C, and point P is 0.2 meters to the right of B. Can we define electric field at a point? So this is basically the charge, okay, per unit area. The charge per unit area that will be experienced is the force. It's not it's charge, it's basically the force per unit area, because it will be in a charge format. So the force per unit area that is experienced at that point, at a given point. All right. Then can we draw a labeled vector diagram for the electric field of P as a result of A and B? So when you look at A and B, sorry, A and P, there's going to be attraction. So meaning that's going to be on that side. Okay. And then B and P, there's going to be repulsion, meaning that's going to be in that sort of direction. So for me to combine everything together, it should be, this is going to be the electric field of B and P. And then this side, we're going to have the electric field of A and P. All right, so that is 8.3.2. Then 8.3.3, they want us to calculate the magnitude of the net electric field at P. So one thing we know about the electric field is given as the E being equal to KQ
over R squared. So if I look at the AP, first of all, it's going to be 9 times 10 to the 9. And then my A is 5 times 10 to the negative 6. Okay, 5 times 10 to the negative 6 divided by, remember we're looking at A, so it's going to be 0,5 and 0,2, which is a 0,7. So 0,7 squared. What does this give us? Gives me a very big answer. So 91836,7, I can say 3. Okay. Then let me look for the electric field as P and P, which is going to be 9 times 10 to the 9 times, in this case, we're looking at 2. Okay. Times 10 to the negative 6. And then I'm dividing it by the R squared, which is 0,2 squared. When I punch that in the calculator, I'm getting a 450,000. That is Newton per coulomb. Then no, Newton per meter. It's Newton per meter. Okay, then since we're looking for the net, we're just going to do the subtraction. So 450 minus the 91. Okay, so 450 minus the 91, 836,73. So this gives me a rough answer of 358163,27, which is approximately 3, maybe 58 times 10 to the 5, not 8. Okay, Newton per meter. All right, then 8.3.4. If point P was now put between A and B, okay, the net electric field would never be equal to 0 at any point. Can we explain the validity? Can we explain the validity? Now, if P is removed and placed somewhere here, the fact that this is a positive charge and this is a negative charge, there's going to be a transfer of field lines, okay? We can only get a net of a 0 if the forces are sort of, if the charges are the same and there is some bit of repulsion in that manner. But in this case, the signs are opposite, which means there is an attraction force that must be always greater than 0. 8.4, the relationship between the electrostatic force and the charge is illustrated below. Okay, so this is the force F, this is the charge Q. Okay, what mathematical relationship between the electrostatic force and charge can be deduced from the graph? So if you look for the gradient, okay, we know that F over Q, which will be the same as F over Q, is the same as the electric field. People call it intensity. Okay, so electric field intensity. Let's just leave it as electric field. Then 8.4.2 use the information to calculate the magnitude of the electric field. Then they talk about it there. Okay, when it experiences a force of 0,05 newtons. Okay, so what I'm going to do, we know that the electric field is given as the force divided by the charge. So that's going to be 0,0005, 0,005 over the charge. In this case, it's 0,05 goes with a charge of 1. So 1 times 10 to the negative 6. Okay, when I divide that, this is 1 times 10 to the negative 6. I'm getting 5,000. Okay, this is Newton per what? Per coulomb. So I use the same batteries used, and all the resistors are identical with resistance of 3 ohm each. The battery has EMF and internal resistance of unknown values. Voltmeter readings are indicated as we can see. Define power. So power is the rate at which work is done. Okay, rate at which work is done, or the rate of doing work. Rate of doing work. Then 9.2 focuses on circuit A. What would 2 through R2? So one thing we know is that this is 2,4 amps. Okay, this current is flowing through these resistors. But they told us that each resistor is a 3 ohm resistor. Okay, we don't care about the 3. Okay, what we care about is that they are equal in magnitude, and for as long as they're equal in magnitude, which means even the current that is passing through them will be split into 2. So that's gonna be 1,2 amps. Okay, it's the same as 2,4 divided by 2. The 9.2.2, they're asking us for the power that is dissipated by both R2 and then R3. So I know that power is given as IV, okay, the voltage and then the current. So I know that the voltage across R2 and R3 is 3,6, but then the current that's going to pass through both of them, the total current is going to be the 2,4, because they are only having 2 parts. So it's going to be 2,4 multiplied by 3,6, which gives me 8,64 watts. You can use other approaches, okay, whereby you look at the individual power, okay, and even the power here, because we know the current is 1.2, 1.2, and then you just multiply it by 2 or you plus them together. You should be able to get the same answer. The 9.3 is using circuit B. They want us to get the energy, okay, used for resistor R1 if the current flows for 10 minutes. Now we know that these resistors are in series, okay? And for as long as they are in series, the current that is passing through them is technically the same. But then the voltage is going to be, I'll say equal. The voltage should be equal. Okay, so the voltage of R1 should be the same as the voltage of R2, same as the voltage of R3. But all the 3 voltages must give us the total voltage because they are in series. Reason as to why the voltage is equal is because we're talking about the same magnitude of resistance. So what I need to do, number 1, is for me to determine, okay, the voltage of R1. So the voltage of R1 is going to be 7,56. Okay, I'll divide it by 2. So 7,56 divided by 2, I'm getting a 3,78 volts. 3,78 volts. So if this is the voltage, for me to get the energy, okay, I should be able to get the current and the voltage. I'm just calculating the power technically, okay, and then the time being taken. So these 10 minutes need to be changed into seconds. So we're going to multiply this by 60 to give us 600. So my current is 1,26. My voltage is 3,78 multiplied by the 10 multiplied by the 60. So I'm ending up with 1, 2, 1, 2. We only have 2 zeros. Okay, so it's not going to be sufficient. 1,26 times 3,78 multiplied by 600. I'm getting 2857,68. Okay, this is energy. Né? It's going to be joules. And then 9.3.2, how would the current be affected if R1 burnt and was removed? Okay, how is the current affected? So the current is just going to increase. Okay, so we can say that removing R1, okay, will reduce the resistance. Okay, removing R1 reduces the resistance, thus the current will increase. We know that current and resistance are inversely proportional. Okay, so when the resistance decreases, the current must increase. Then 9.4, can we define what EMF is? So EMF is the same as electromotive force, but the definition of it is that it is the potential difference. Okay, it is the potential difference across a battery. Okay, across a battery when no current is flowing. The 9.5 resistor R1 is replaced by another new 3 ohm resistor. Calculate the value of the EMF and the internal resistance for the battery for circuit A and then circuit B. So we're going to solve this simultaneously, okay? So one thing we know, okay, let's state the facts that we know. That if this is a 3 and this is a 3, we know that the effective resistance in circuit number 1 or circuit A is going to be product over sum. So it's going to be 9/6 plus the 3. Okay, so that's going to be 18 plus 9, which is a 27. And then I'm dividing it by 6, which gives me a 4,5. How many marks is it? Okay. So this is 4,5 ohms. So this is the effective resistance for this one. Then 3 and 3 gives us 9 ohms. So that's the effective resistance for circuit B. Then we know that the formula for the EMF is given as current into a resistance external and resistance internal. So if I look at circuit A, my EMF is going to be equal to the current, which we said is 2.4. Okay. The effective is 4,5 plus R. Let's call this equation 1. Then let's look at the circuit B. Our EMF is going to be 1,26. We said 9 plus R. That is equation number 2. Then we solve the 2, equate both of them. 1 equivalent to 2. So 2,4, okay, let's do that. 4,5 plus R is equal to 1,26 into 9 plus R. So let's open up the brackets. We know that 4,5 multiplied by 2,4 gives us a 10,8 plus a 2,4 R. Then 1,26 multiplied by 9 is going to give us 11,34 plus 1,26 R. Let's collect the like terms. Okay, so 2,4 R minus 1,26 R should give us 11,34 minus 10,8. 2,4 minus 1,26, I'm getting 1,14 R. Then 11,34 minus the 10.8, I'm getting 0,54. All right, so let me divide both sides by 1,14, 1,14. So what's our R? 1, we said 1,14. That gives me 0,47 ohms. It's fine, let me just leave it to 2 decimals. Okay, then for me to get the EMF, I can just replace it into one of the equations. So it will be 2,4 into 4,5 plus the 0,47. So 2,4 multiplied by 4,5 plus, we said 4,5 plus 0,47, which gives us 11,93 volts. Okay, 11,93 volts. So if, okay, I'm just saying if we had rounded off, did they tell us about rounding off? Internal resistance, no, they never told us. So if we were to round off, let's say these to approximately 0,5 ohms, then we were meant to get something like a 12 volts for the EMF, which is pretty reasonable. All right, guys, so that brings us to the end of this paper 1, okay? And I wish you all the best in your preparation for paper 2. Let's meet then. I sign out. Hello. Paper, we have 10 questions that we shall be looking at and we shall be exploring, okay? So with question number 1, which is the multiple choice, they're telling us that we have 4 options and we must choose the most correct option. Now we have 3 forces that are acting, okay, on an object as shown, so that the resultant force is what? 0. So each of the following vector diagrams is correct representation. So if I'm to look at this with the format of the vector diagrams, which is the head to tail, A cannot be, C cannot be. But when I look at D and B, there could be something there. An example, if this one starts from here and goes up, this one goes down, this could be the resultant. Okay, so if this one, then that. So I'm gonna take B to be my correct answer for this case, okay? I'm taking B to be my answer. Please, you help us in the comment section if you differ with what we are choosing, okay? 1.2, we have two large objects, P and R, each with mass M, and placed between the centers R meters apart. They exert a gravitational force, which is M. So we know that the formula for the gravitational force is G, mass 1, mass 2, over R squared. But then they're telling us that the mass of the second one is being increased by 2, or is increased to 2M, okay? So you're gonna have a 2M, which is like a times 2 there. And then the distance is now increased to 2R, okay? So meaning that we're gonna have G, M, and M. Let me call this M1, M2, but it is 2 times. Over, now when I get the 2R and I square it, I'll get 4R squared. When I simplify this, we're gonna get a half. So that's gonna be a half G, M1, M2 over R squared, of which this represents our force. So my option will be that case. Then 1.3, the velocity versus time graph sketched below for the motion of a ball that's projected vertically upwards, top of a building. Okay, so it was thrown upwards, okay, with a certain velocity. It reaches the maximum height above the ground, and then it hits the ground and then bounces off and then reaches the maximum height again, another height. So we know that S is always smaller than Q, okay? Because at this point, the velocities are 0, which means those are like maximum points. It's more like bouncing because of the amount of energy. The energy at Q is greater than the energy at S. So the ball reaches highest height above the ground at a certain time. Which point of the graph corresponds that? So I'm going with Q, okay? That's 1.3. And then two hard objects collide inelastically in an isolated system. Which of the following sets of statements will be correct? So both total momentum and kinetic be conserved? No, we know that momentum will always be conserved regardless. No? But when it comes to the kinetic energy, for as long as it is inelastic, kinetic energy will not be conserved. So neither total, this is wrong. Total momentum is not conserved, that's wrong. So option D is the best. So total momentum is conserved, but the total kinetic energy is not. Then 1.5, we have an engine P, which has a greater maximum power output than engine Q. Which of the following is correct when P and Q operate at their maximum output? Now, the fact that P is having a greater maximum power, it simply means that it can finish the work within the shortest time possible, for as long as the work to be done is basically the same, okay? So if the work done is not the same, which means that P can do greater work compared to Q if the time varies. Okay, so they're telling us Q does more work than P in the same time. Q has a smaller output, so it cannot be. Then we're saying that P and Q do the same amount of work at the same time. This is wrong. P and Q do not do the same work, but Q does it in a short, no, it cannot be a shorter time for Q. It's a shorter time for P. P and Q do the same amount of work, which is correct, but P does it in a shorter time. Option D is the best. 1.6, we have the absorption spectra of the same elements surrounding both star A and star B as observed from the Earth. The spectral lines from star B are more redshifted than those of star A. So how do the frequencies compare? So with 1.6, I'll go with C, because the frequencies observed from B will be lower because the wavelength is higher. And then the speed is gonna be greater. Okay, then 1.7, telling us R and S are two small charged spheres. Okay, we don't know what's happening here. So when I look at R,
okay, because they gave us the net electric fields. This is R, and then this is the electric field due to R. Since the direction is in that sort, which means there's a repulsion. And we know that P is a positive point charge. Okay, so if that's a positive, this one must also be a positive. And then when I look at S on that, it's moving this direction. So meaning that S must also be moving that direction, which is attraction, okay? So that is gonna be a negative. Okay. So if S is a negative and R is a positive, which option do we have in that case? So it's saying R is positive, S is negative. So option A is what I'm going with. Then 1.8, the circuit below was used in a practical investigation. There's an EMF and internal resistance. We must ignore the connecting wires, okay? So we have graphs K and L below as obtained. So we have an adjustable resistor, which we know I call a rheostat. So we're saying that voltage against current, we have graph K, which obeys Ohm's law. And then this one does not obey Ohm's law. Now, the fact that this is a standard graph, okay? And we know that with the rheostat, what happens with the resistor, with the resistance, it's not constant, it keeps on changing. Eh? So meaning that the voltage V2 should give us, or should represent the Ohm's law. And then the voltage V1 must be represented by the graph L. That's my understanding of this. So V1 is L, and then V2 is K. So K is V2, and then V1. So I'll go with C. I don't know what the masses have to say about that. 1.9, which one of the following is the function of the split ring commutator in an electric motor? So mainly it's to change the direction, okay, of the current. So ensures that the current in the external circuit changes direction. So option D would be the best then. And then 1.10, which one of the following statements correctly describes the photoelectric effect? So with this, I'm choosing option C, that an electron will absorb the energy of a photon and is ejected from the metal surface, okay, if the energy is indeed sufficient. Okay, so that is to do with question number 1. Question number 2. There's a crate of mass 25 kilograms that slides down a rough inclined plane, okay, at a constant speed of 2 meters per second towards point A. Okay, there's a force F that acts on it parallel to the incline as shown. There's a constant kinetic force, 40 newtons, and the incline is 30 degrees. Now they want us to state Newton's first law of motion in words. So this law simply tells us it's also the same as the law of what? Inertia. So what does the law of inertia state? That a body remains at rest. It's fine, let me write it this side. So this is 2.1. 2.1, they're telling us that a body remains at rest. Okay, a body remains at rest or constant motion or speed in a straight line, unless acted upon by a resultant force, call it the resultant force, or we can call it an external force. So unless we have something extra that is acting on it, we expect the body to continue moving in the same direction or resting the way it is, okay? Then at 2.2, they want us to draw the free body diagram showing all the forces acting on the crate as it moves towards B. So what we can see is that there is this force F that is acting in that direction. Okay, but since the crate is moving downwards towards A, we're gonna have the friction force. The frictional force is also gonna act in that direction. I'll say F friction. We call it Fk. Yeah, let me call it Fk. And then now we're gonna have the weight downwards, and then we're going to have the normal force upwards. We can have the FG parallel here if we wish, but we already have enough forces for what they wanted. So 1, 2, 3, and 4 is enough for the 4 marks. Then 2.3, they want us to calculate the magnitude of F, which is the applied force for 3 marks. So you can use Newton's second law, whereby we know that the F net should give us the MA. Now down the incline, we know that we have the FG parallel. We say the frictional force is going to be acting upwards. So if I get my FG parallel plus the FK plus the F applied must give me the mass and then the acceleration. So my FG parallel is mg, the sine of theta. My FK was a 40. I will say negative 40. The F is acting in the opposite direction, which will also be a negative F, will be equivalent to 0 because the body is moving at a constant speed, which means there is 0 acceleration. Let me substitute. The mass is 25 times 9,8 multiplied by the sine of 30. Now I'm subtracting 40. I should move the force applied that side. When I punch this into the machine, which is the calculator, okay, I'm ending up with a nice answer of 82.5 newtons. Okay, so this is our applied force as required by the question. Please just confirm with that. If I'm having the same, so we're saying sine of 30, and then we subtract a 40, 82.5. Perfect. Then we move on to the next question. And then they're telling us that when the crate reaches point A, it starts to act up, okay? The force F is removed, and then the angle of inclination decreases immediately to a certain angle, which is theta, so that the crate continues moving at the same speed. So we're maintaining the speed of 2 meters per second, but with a difference within the angle and then within the forces that are there. Now, for us to answer this, because now we're seeing this kind of scenario, then they're asking us to use the relationship between the forces that are acting on the crate between point A and point B to show that the mu k, okay, the correlation coefficient, the coefficient of friction is given as this, okay? Now, if the force F is removed, which means we are only left with the frictional force and the FG parallel that will be acting downwards. So that's what I'm going to use here and say that we can still say that F net is equal to 0 because it's still moving at the same speed, and then FG parallel is going to be mg, sine of theta is equivalent to, we know that frictional force is given as the mu k multiplied by the normal force. Let me just start by that, Fn. Then this is mg sine of theta. We know that it's going to be the mu k over the normal force, but normal force is given as the mg cos of theta. So I'll say over mg cos of theta. So the mg and the mg will cancel out, meaning that the mu k will be the sine of theta over the cos of theta. Okay. Then 2.5, they want us to get the, no, they're telling us that the coefficient of kinetic friction between the crate and the plane is 0.19. They want us to use this identity from Trig. Oh Lord, why must maths always haunt us? Okay, let's use this identity, okay, to calculate the frictional force as the crate moves from point A up to point B. Now, one thing we need to know is that we know that sine of theta over cos of theta must give us the tan of theta. But we said this is representing the correlation coefficient. So what is that going to be? I'm going to say, let me change this around and say that the tan of theta is equivalent to 0.19. So let me get the theta, which is the shift tan of 0.19. Okay, so shift tan of 0.19, that gives me 10.76. okay, degrees. So this is the new angle, okay, that we're dealing with. Now the question wants the frictional force. Then we shall go down and say that our frictional force, Fk, is given as the mu k multiplied by the Fn. That's gonna be the mu k, which is the 0,19 multiplied by the mg cos theta. I'm using this, but there is also another way to do that, okay? The mass is 25, and then the 9,8, then we're saying the cos of 10,76. When we punch this, yeah, I'm getting a 45,73 newtons. Alternatively, somebody would have used, there's another approach that one could have used. And that is to say that this FG parallel is equal to this. Okay, and you just say that the mass times the gravity multiplied by the sine of theta. So that's a 25 multiplied by 9,8, and then the sine of 10,76. Let me just confirm and see. So 25 times 9,8, and then the sine of 10,76. Perfect. I'm getting a 45,7. Oh, yeah, just the difference of a 0.01, which is not bad. Okay, so either way, you'll always get the same thing. Then question number 3, I'm telling us that there's a ball that is dropped from point A and reaches point B, which is h meters below A in time t. The ball takes a further 2 seconds to fall from B up to C. The distance between B and C is 8 h meters, 8 times the original height. We are ignoring friction as always. Then they want us to define what free fall is. So free fall is just a motion. Okay, it's a motion of an object. It's motion of an object that is under the influence, okay, under the influence of only the acceleration due to gravity, or it's just under the influence of the gravitational force. Okay, then 3.2 show by means calculations that t is a 1 second. Perfect. I love such questions where they even give us answers. No? We can never go wrong there. Okay, so for us to show that, I'll have this as my displacement. Okay, so I'm going to use the second equation of motion, okay, which says delta y should be v initial multiplied by delta t plus a half g delta t squared. Okay, so h is going to be, our initial is 0 since the ball was just dropped. So it's going to be a half times 9,8 t squared. I'll call this equation 1. Okay, so if this was a t and this was a 2, okay, let me look at the, I don't know, should I look at the entire journey or just this other section of B? I can look at the B part, né? And say that still using the same formula, 8h is going to be still a half, but then that is going to be tricky for me. Let me use the total distance, which is going to be now 9h, because 1h and 8h is 9h. Then this is times 9,8 into a t plus 2, and then I square that. So where there is h, I'll replace with that. So this is equation 2. And then I'll say that I'm substituting 2 into, no, I'm substituting 1 into 2. Okay, so it's going to be 9 into a half times 9,8 t squared is equivalent to a half multiplied by 9,8. I'll have t plus 2 squared. So I'll have 9,8, half 9,8 dies out. I have 9t squared is equal to, that's going to be t squared plus 40 plus 4-ish. Now we have quadratics here. Okay, let's collect the like terms and let's create the standard equation. So that's gonna be 8t squared minus 40 minus 4 is equal to 0. Divide through by 4. So t squared minus t. And then we have minus 1 is equal to 0. Then let's vector this out. Okay. So when we are factoring this out, we're going to have a 2t. And then we're going to have a t. This can be a minus 1. This is going to be a plus 1 is equal to 0. So the first bracket, t is negative a half. We can never have time as negative. And then t is a 1. So this is what the question wanted. So this is how I would have worked this out, okay? So if you have a better way, a quicker way, shorter way, please just help us, okay? Then 3.3. And they want us to use just the equations of motion only to calculate the speed with which the ball reached point C. So with this one, there's just a short and quicker way. Let's use the first equation of motion. V final is equal to V initial plus G delta T, since it's free fall, okay? Our initial is 0, meaning that V final is gonna be 9,8 multiplied by the total time, because T is 1. So it's 1 plus 2, which is a 3. And then this becomes a 29, okay, 4 meters per second. That's what we do. This is the shortest, okay? The other alternative is by you going through the displacement approach and you use the Vf squared is equal to Vi squared plus 2G delta Y. Okay, you can also use this, but you'll have to find the total displacement first, okay? After getting your T as 1, you can go back and substitute and find the H and then, but this is a longer way, okay? Because that's what actually question 3.4 requires. That determine the height from which the ball was dropped, the total distance. So since we know that our H was given as what from one of the equations, we said a half times 9,8 t squared, okay? So a half times 9,8 t squared, meaning that's a half multiplied by, no, this is 4,9 t squared, where the t is 1, then the distance is going to be 4,9 meters. But this is just the height, h. Then the total height, okay? Total height is going to be 9 times, which is going to be 9 multiplied by 4,9. Okay, 9 times, we say 9 times 4,9, I'm getting, we said 4,9. I'm getting 44,1 meters, okay? Any alternative is also acceptable, okay? That is how I would have answered 3.4.1 for 2 marks. Then they want us to get the height. Is that the question? Okay, the height of the ball at B. Yes. Now at B, remember the total distance is 44,1. Okay. Now what is 44,1 minus 1h? Remember we say that 1h is what? Just 4,9. Okay, we are subtracting a 4,9. That gives me 39,2 meters. There we go. Okay. 3.5, they want us to sketch the graph. Okay, I'll just squeeze it here, guys. Yeah? Sketch a position versus time graph, motion where the ground is the 0 position. Okay, so if that is the ground as our 0 position. Okay, this ball was projected up. What do they mean by that? So ground is the 0 position. If you go up, it's positive, which means the body moved in the negative direction forwards. Okay, so it's possible for us to have something like that, where this is going to be our 44,1, and then the object moves up to that point. So this is the C point, and then we can have our 39,2. The 39,2 comes after. Isn't that too far? Isn't that too far? Let's change it and say if this is 1, 2, and 3. So just this point here, which is the 39,2. And then this is going to be the point B, which is 1 second, 2 seconds, and 3 seconds. So this is the time in seconds. This is going to be the position in meters, or the Y in meters, okay? You can have it like this, or somebody would have drawn it like this, and then you indicate this kind of thing. Okay? So that is your B, this is your A, and then that is your C. Okay, so something of that nature, this or that. Then question number 4. We have a trolley A of mass 1,5 is resting horizontally on a frictionless surface. The second trolley B of mass 2 kg travels horizontally at constant speed V and collides with A. Trolleys stick together and move at a constant velocity to the right. Okay, this one is resting, right? Right. Okay. There's a distance covered in 2 seconds. Okay, state the principle of conservation of linear momentum. So we know that in an isolated system, we're going to say question 4.1. Okay, in an isolated system, the total linear momentum is conserved. Okay, so that's what you have to say. In an isolated system, the linear momentum is conserved or remains constant. And then 4.2, what do they want? They want us to calculate the speed V with which B moves before the collision. So let me summarize this nicely, and we've seen that if we have A, we have B. What are the masses? We know that the mass of A is 1,5. The mass of B is 2. The velocity initial for A is 0 since it's resting. This one velocity initial is just a V. Okay, we know that the velocity final and the velocity final is just the same. Now, they want us to calculate the velocity V, this one. But we can get our velocity final first, because we know that the velocity final will be the displacement over the change in time, which was 0,8 over 2, meaning that our final velocity is 0,4 meters per second. Then we apply the conservation of momentum. We know that mass A, initial velocity of A, plus the mass of B, initial velocity of B must give us the mass of A, the final velocity of A. Okay, since it is now one system, let me just combine everything at once and say plus mass of B into V final. Okay. Now, initially, this is going to be 1,5 multiplied by 0. This is 2 multiplied by V is equal to 1,5 plus 2 multiplied by 0,4. Going to have a 2V being equivalent. Okay. That's going to be 3,5 multiplied by 0,4. I'm getting a 1,4. And then V becomes 0,7 meters per second. Okay, so that is 4.2 that the question wanted. Then 4.3 is the collision elastic or inelastic. So without a doubt, this is, I did not say inelastic. I said inelastic. Okay, it's inelastic. Why? Remember, there is no energy within trolley A. Okay, but the energy of B initially and the energy of the combined system after cannot be the same. Energy is going to be lost, okay, in one way or the other, given the fact that the final velocities or the velocities are not maintained. This is a 0,7, which is higher. The final is 0,4, which is lower. So there was energy that was lost. So that is inelastic. We don't have to prove or give a reason. Then 4.4, they are telling us that during another collision, okay, so if there's another collision, trolley B exerts a greater force on trolley A, and the change in momentum just stays the same, okay? How is the time for the collision affected? Choose increase or decrease. So in this case, I'm going to say decrease, or because the change in time is going to be shorter.
And then they want us to write down a relevant equation to support the answer. So we know that force multiplied by delta T should give us the change in what? Momentum, the impulse. Then we're saying that delta T is the same as the change in momentum over the force. So remember, the change in momentum is the same for both, whether A to B or B to A. So if that is the same, if the force is greater, the time must be smaller, because time is inversely proportional to the force. Okay, so this decrease and then this formula is perfect enough. That is 4.4 and question 4 as a whole. Then question 5, there is water that is drawn from a water source that is 12.5 meters below the ground by an electric pump. The water is lifted vertically upwards at a constant speed as shown in the diagram. Okay. Then they want us to define the term and conservative force. So we know that this is a force, okay, in which the work done by the force is dependent. Why can't I say the work done by the force depends on the path taken? Okay, on the path taken between any 2 points. Then they want us to draw a free body diagram showing all the forces acting on a fixed mass of water as it moves from the source to the ground. Okay, so if a fixed mass of water, let's say it's somewhere there, this water is gonna experience what we call the weight. Okay, is there any other force that is gonna act on this water? Not really. I don't think there's any other force unless if. But the other one that I could think of is the fact that the water is going upwards, there should be the force by the pump. Okay, force by the pump. So meaning that we're gonna have the force pressure by the pump, and then we're gonna have the weight downwards for 2 marks. It's reasonable. As much as we might have friction by the pipes and what, but that is usually because they told us to ignore the friction and capillary effects. So if there's no capillary effects, which means it's just the force by the pump and then the weight that's acting downwards. But since the pump is greater, then the water will go up. Then 5.3, because they told us that the pump lifts the water at this rate. The pump lifts 200 kilograms of water from the source to the ground at a constant speed. Calculate the work done by the pump. Okay, so we know that the work done is going to be the mass multiplied by the gravity multiplied by, so it's more like the gravitational pull, okay, which is going to be the mass, which is 200 multiplied by 9.8 times the 12.5. So this gives us 24,500 joules. Okay. Then they want the constant speed at which the water is lifted. Constant speed at which the water is lifted. Let me jot it this side. So it's the 5.3.2. So it's a tricky question. 5.3.2. So if we are lifting 200 kilograms at basically 2.5 kilograms every second. Okay, so this is 2.5 kilograms in 1 second. How about the 200 kilograms? How many seconds are we going to need? So let's just divide this. So 200 over 2.5. This gives us let's just confirm that, please. Let's double check. Okay, so we're saying 200 divided by 2.5, which gives me 80 seconds. So it's gonna take 80 seconds to move 200 kilograms of water. Now, for me to get my velocity, okay, I'll get the displacement, okay, I'll say delta y over delta t. Now, my delta y, the distance through which the water is gonna move, is 12.5. The delta t is gonna be 80 seconds. Then 12.5 divided by 80 gives me 0.156, which is approximately 0.16 meters per second. Okay, so that is the velocity that the question is asking for 3 marks. Then 5.3, they want the average power that is dissipated by the pump. So for average power, I can as well get the work done divided by the delta T. So the 24,500 divided by the delta T, which is 80. Wow, it was a tricky question, but I believe it was a doable work energy kind of question. So that is 306.25 watts for the power. Okay, so that is question number 5. Then question number 6 are telling us that there is a bat that emits sound waves with a frequency Fs as it flies at a constant speed Vv towards a vertical cliff, okay? Then the waves reflect off the cliff with the same frequency that they strike the cliff and with the wavelength of this much as shown the simplified word. So the bat is moving. The bat emits with a frequency as it flies at a constant speed. So if the speed of sound in air is that, okay, name and state the phenomenon. So that phenomenon is what we call a Doppler effect, okay? And then we just have to state Doppler effect because we know that this is the apparent change in the observed frequency, okay? And the reason as to why there is a change in the observed frequencies compared to the frequency of the source is as a result of the change within the velocities of the sound source as well as the listener, okay? Difference in the velocities of the listener and the sound source. So that statement of Doppler effect should be well stated. Then 6.2, they want us to show that the frequency or the frequency of the source is given as this. So what we need to do is that we need to start by finding the frequency of the listener. We know that V is equal to F lambda. So we know that that's going to be V over lambda. We know that our V is 340. And then our lambda that we're given was 0.016. If you divide that, that is number 1. Now, if this is true, we can go to the Doppler formula, okay, and substitute. Okay, so then I'll go back to the Doppler formula. Let's see, let me put it here and say that frequency of the listener should be equivalent to V, okay. I'll say velocity of the listener over V, I'll say minus, this is gonna be velocity of the source multiplied by the frequency of the source. Now, we know that the bat is the source in this case, and it's also going to be the listener. So let's take it to be moving in this case. So our FL that we got was 21250 is equivalent to 340 plus, if the listener is stationary, that's going to be a 0 over our 340 minus VB multiplied by the frequency of the source. Now, remember, we're looking for the frequency of the source. Okay, then I'm just going to multiply through. So I have my 340 minus VB multiplied by 250 is equivalent to 340 Fs. But let's divide through by 340. I don't want to open those brackets. So 250 divided by 340 gives me 62.5. Okay, that's 62.5. We have 340 minus VB is equal to frequency of the source. Then when I open this up, meaning that this 340 cancels that, is going to give me 21250 minus 62.5 VB. So that's the frequency of the source that the question
technically wanted. Okay. Then next, 6.3. They're telling us that the frequency of the reflected sound detected by the bat. Now, if it is detected by the bat is now the listener. Okay, which means the frequency of the listener is 850 higher plus the frequency of the sound waves emitted. Okay, so it's 850 plus the frequency of the source, which is going to be 850 plus this whole thing or this whole scenario. So what does that give us? Okay, let's go down again. We're still using Doppler, the formula for Doppler. So this is 6.3. Okay, 6.3. So we shall say that V plus VB over V minus VB must give us, I'm just gonna say frequency. Okay, I'll just put the simplified version of it that I'm having 1, okay, plus 850 over Fs, technically. Okay, so when I substitute, I have 340 plus VB over 340 minus VB, is equivalent to 1, plus the 850 over Fs. And then we know that our Fs was that 2, let me just replace it now, and say that 21250 minus VB. Okay, so what do we do next? Just have to simplify this. Okay, let me simplify. So 340 plus VB over 340 minus VB. Cross multiply, we're gonna have 21250 minus VB plus 850 divided by 21250 minus VB. Okay, I have a whole lot of VBs now. Yep. Okay, 340 plus VB is giving me, what's 21250 plus 850, that is 2200. Minus VB. This is gonna be 340 minus VB. And then this is what are we doing? Okay, that is fine. This is 21250 minus VB. We're multiplying it by that. Okay, so when I punch this into my calculators, it's huge. 21250 times 340 is giving me 7225000 plus 21250 VB minus 340 VB and then minus VB squared. I must do the same thing here. Okay. 340 times 100 is giving me 7514,000 minus VB squared plus 22100 times 340. We're done with that. We're looking at the VB now. It's going to be 22100 VB plus VB squared. Okay, so meaning that this is gonna, it's not gonna cancel. Only one that is canceling is this one. Wait a minute. Why am I having? What am I doing? Hello. That is that. No, I think I'm messing up somewhere here. I'm doing a mess here. Okay, 340 on this, we get that. 340 on that, we have negative 340 VB. Okay, this and that is negative 2 to 100 VB plus that, okay? Then let's see. So this 340 is going to cancel with that 340. Then 21, that is going to be different. Let me move everything out to the left or to the right. So I'm going to have 2 VB squared. Okay. And when I move this on that side, it's going to be negative 2 to 100 minus 2 250. It's going to be minus 43350. Then when I subtract that, 7514. Okay. So is equal to this. So when I solve this, the end of the day, I'm getting my VB to be 6.8 meters per second. Guys, please help me with what you got in that kind of regard, okay? Then question number 7, they're telling us that a small negative charge Q placed at a fixed distance from charge sphere R experiences this kind of force as shown in the diagram. So if the force is moving towards Q, okay, meaning that there's some bit of attraction in this case, meaning that this must move. And since this is negative, then automatically this must be positive. They want us to draw the electric field around the positive. So something like that. Okay, field lines must be moving out. Then 7.2, there is sphere S that is attached to a ceiling, and we have all that information. State Coulomb's law. So Coulomb's law simply tells us that the electrostatic force, okay, between point charges is directly proportional to the product, okay, to the product of the charges, okay, and then inversely proportional to the square of the distance between them. That is what we have there, okay? Then 7.2.2, draw a free body that is looking at S, okay? So with S, we're gonna have the weight. We're gonna have the tension, and then we're gonna have the Coulomb's force there, the force that is as a result of R. All right, then they're telling us that sphere S is positive 6 nanocoulomb, that is R, and then S is 3 nanocoulomb, and then the mass is 0.15. Calculate the angle, theta. So for us to get the angle, okay, we need to know that this body, S, is going to experience this force. So let's first calculate the force, which means it's a K multiplied by Q1, Q2 over R squared. So 9 times 10 to the 9 multiplied by 6 times 10 to the negative 9 times 3 times 10 to the negative 9. I'm dividing this by 0.03 squared. This is giving me an answer of 0.00018. Okay, so that is more like the force that we're having. Okay, then if I'm to break this down, we know that there's going to be a component here. If this is a theta, meaning that that must also be a theta. So this is going to be a T cos of theta. And then this is going to be the weight. So we know that T cos theta is equal to the weight. And then meaning that T is going to be the weight over the cos theta, which weight is like, we had 0.15. We change this to kilograms, you divide by 1,000. Okay, let's see. 0.15 divided by 1,000, we're getting 0.00015 times 9.8 over cos theta. This is my t. Then I know that this force here will be having the component, the horizontal component here, which is the t sine of theta. Okay, so t sine of theta, I'll equate it to my weight there, which is 0.00018. Then where there is t, I can replace it with this whole thing. Meaning that I'm gonna have a 0.00015 multiplied by 9.8, okay, over cos of theta. I'm multiplying by the sine of theta, should give me 0.00018. You can use your simplified decimals or exponents, and then you're good to go. Then I'm gonna divide this thing on this other side, okay? And we see what we end up with. So we know that sine over cos, that's gonna give us the tan of theta. 0.00018 divided by 0.12315 times 9.8. Let me put this in brackets, nice. Okay, so if I put in the brackets, I'm getting 0.12245. Okay, then the shift tan of this is giving me 6, okay, I'm saying shift tan of the answer, I'm getting 6.98, which is approximately like 7 degrees. Okay, so that is your theta that they need. Then question 8, they're telling us that in a circuit diagram below, the battery has an EMF of 24, the internal resistance is that, and we have all those resistors. Can we state Ohm's law in words? So we know that the current, okay, through a conductor, current through a conductor is directly proportional to the potential distance, or some people call it the voltage across, okay, across a conductor at a constant temperature. Then when both switches are closed, they want us to get the current through L. Where is L? This is L. But then they're telling us that the reading here is 0.8. So if we have this current, we have this resistance, we can get the voltage here. Okay, so I'm gonna say that the voltage is gonna be 0.8 multiplied by 13 from our Ohm's law. So this gives me a 10.4 volts. Now we know that since this resistor, this and this, they are all in parallel, the voltage is going to be the same. So the voltage or the current from this formula, we know that current will be voltage over the resistance, meaning that 10.4 divided by 9.5 must give me 1.09 amps. They want the reading of A2, so A2 is like the total current through the circuit. So I have the current here as 1.09. I have the current as 0.8. I need to find the current here. Okay, so still the voltage is the same even for the 9. So I'm gonna say that voltage in the 9 is gonna be, no, I'm not saying the voltage, I'm saying the current in the 9. Okay, current is in 9 is gonna be 10.4 over the resistance, which is 9, and that gives me 1.16 amps, meaning that the total current that we're gonna have should be 1.16 plus 1.09 plus the 0.8, and this must give us a 3.05 amps. And then they want us to get the total resistance R. Now, since these three are in parallel, I need to find the effective resistance of this parallel combination. Okay. So I'll say that the parallel, R of the parallel is going to be 1 over R1 plus 1 over R2 plus 1 over R3. It's going to be 1 over 9,5, 1 over 13 plus 1 over 9. Okay, so when I flip it around and find my R of parallel, this is going to give me 3,4 amps. Okay, if that is true, then I can use the EMF formula and say that my EMF is current into the R external plus the internal resistance. Now this R parallel will be in series with the R of interest. So this is going to be a 24 is equal to 3,05 into R plus the 3,41, now plus my internal resistance, which is 0,3. I'll start by dividing both sides by 3,05. So 24 divided by 3,05, that's going to give me a 7,869. I'm subtracting 3,41, I'm subtracting 0,3 to get my R, meaning that my R is 4,16 ohms. This is what I'm getting. Please, you can tell us what you got there. Then they're telling us that switch S2 is now opened, okay? So if S2 is opened, meaning that the current will just bypass L and then just complete the circuit. So this 13 and the 9 is out. Now, if that happens, how will this affect the reading of the A2? So how does the current go via that? So we know that initially when the two switches are closed, our effective resistance is going to be 7, something, because we have this 4,16. Now we're creating it, so we have 7,8 as our total resistance there. Now, when we remove those two, the resistance is going to increase, okay? When the resistance increases, the current must decrease. So we're going to say it's going to, how will this affect the reading? Okay. So we're saying the reading is going to decrease. The reading, the current reading in the ammeter is going to decrease. Okay, that it decreases. The reason, because of the increase in the resistor, in the resistance. Then how will the brightness be affected? We must choose increase, decrease. So now when the resistance is decreasing the resistance, né? How is that so? Because now look, let's look at this. If we are having just these two, this and that, we're going to have a total of 13, something, meaning that the resistance increased. If the resistance increased, the current must decrease. And how does this affect the brightness? The brightness will definitely decrease. Reason, we know that power is directly proportional to the current, okay? We can see that power increases, power decreases, okay? The power decreases. As the power decreases, there will be less current, okay? And then the brightness will also be less. Then we have letters A to F. So they want us to look at S1 being opened and S2 is closed. So this one is open, this one is closed. So the circuit is not complete. So, okay. So if it's not complete, which quantities will be equal to 0? That is the current, which is C. Okay, then question number 9, they're telling us we have an AC generator, which polarity. So using the right-hand rule, the polarity of A is basically the north. State one way in which the induced EMF of this generator can be increased. You basically need to increase, okay, the number of turns of the coil, okay. You need to increase the magnetic strength. Okay, you need to use a stronger magnet. That's what we're meaning. You must increase the speed of rotation and so on and so forth. Then they want us to sketch the graph. So the graph is going to be simply something like that. Okay, this is time in seconds, and then this is the induced EMF.
Okay, then 9.2. We have an AC generator that produces maximum voltage. Okay, so Vmax is 340. We have the power of 1.2. Define the term root mean square. So we know that root mean square is basically the equivalent constant current, okay, that would offer the same power to a resistor as the actual one, okay? So we just need to write that definition. The 9.2, they want us to calculate the root mean square current that is passing through. So what I'm gonna do, I will use the P average being the V RMS multiplied by the I RMS. But will this make sense? Yes, we have the power, which is 1.2. For us to get the V RMS, we must get the V max, we divide it by the square root of 2. So this is 340 over the square root of 2 times the I RMS. When you do your magic and push everything that side, the I RMS that I'm ending up with is a 4,99 amps. Okay, 4,99 amps. Then they want us to get the resistance within the kettle. So you can say resistance is V squared over R, meaning that the R is gonna be V squared over the power. Now we know that our V squared, we're looking at the V RMS, okay, which is a 340 over square root of 2. This is squared. We're dividing it by 1.2, meaning that that resistance of ours is more like a 48,17 ohms. Okay, so that is what I would have done with question number 9. And then question number 10, they are telling us light of different frequencies is incident on a metal plane. The sketch below shows the relationship between the maximum kinetic energy of the photoelectrons and the energy that will be incident. Define the term work function. So work function is more like the minimum energy required. Okay, minimum energy required to remove an electron. To remove an electron from the metal surface. From the metal surface. Now they're asking us to write the numerical value of the gradient. So what's happening here with the gradient? The energy of the photons and the EK max. So EK max over the energy of the electrons. Which constant is that? It's the numerical value. Anybody to help us? What we have there? EK max, the constant is gonna be, I'll write the Planck's constant here. Okay, because that's more like the gradient that I can only think of whenever I have graphs of this. And we know that Planck's constant will be 6,63 times 10 to the negative 34 joules second. Then they want us to calculate the maximum speed of the photoelectrons when photons with energy Y, as shown, strike the metal plate. So we know that the energy, the EK max is 2,99. They want us to get what? The maximum speed. So let's just put it aside. That is 10.3.1. Okay, so 10.3.1, what I'll do is I know that my EK max is given as a half mv squared. That's 2,99 times 10 to the negative 19 is equal to a half. The mass of an electron is 9,11 times 10 to the negative 31 v squared. Do your magic. Okay, if I do my magic, I'm ending up with a v of 8,1 times 10 to the 5 meters per second. And then 10.3.2, they want us to get the value of y. So what is the energy of the photons? Now we know that this is the work function, okay? That is our W naught, the work function that we have. So the formula that combines work function and EK max, do we have anything like that? Yes. So we could use something like seeing a formula here that says that E
is equivalent to W naught plus K max, maximum kinetic energy. Now, the energy that we need is what we are calling the Y. I don't know why this question is from us, unless if I'm getting it wrong. Okay. Do we need the frequency? The frequency, that's going to take us some other time. Okay, so what I'm going to do, I'm just going to add the two, whatever the two values. So it's going to be 3,68 times 10 to the negative 19 plus my energy, my EK max is 2,99 times 10 to the negative 19. So 3,68 plus 2,99, that gives me 6,67 times 10 to the negative 19 joules. So that's what I'm getting then. Then 10.4, they're telling us we have photons of this much energy that are striking the metal plate, or the, okay. Then the number of these photons with this type of energy is increased. Okay, how the maximum kinetic energy be affected? So this is more like when you increase the number of electrons, you're basically increasing the intensity. So how does intensity affect the kinetic energy? So in this case, it's just gonna remain the same. Okay, so what is the explanation? We know that intensity, okay, does not increase. Okay, we can say that intensity, yes, it increases the number, okay, of electrons, but not the